Once again, welcome to the 36th International Conference on VLSI Design. I'm Sridevi Devi Reddy. I lead startup ecosystem piece for Zelpmog Design and Tech Limited, a listed data science company. For the past few days, we have had power-packed sessions with academicians, industry veterans, government functionaries, sharing their insights into today's incredible technology, vision for the better tomorrow, and inspiring us along the way. Today promises to be no less. We will kick off today morning's session with an inspiring and insightful keynote address by Sri Sudhir Malia, Vice President Corporate and Custom Silicon Product Marketing at AlphaWare IP. He will speak on accelerating data for a connected world, the power of optimized silicon. Sudhirji has held executive positions in engineering, marketing, and business unit management at leading global semiconductor companies. His experience spans custom silicon and application-specific products across multiple application domains, including data centers, networking storage, and AI-enabled edge technologies. Please give a round of applause as we welcome on stage our first speaker for the day, Sri Sudhir Malia.
Well, thank you, Sridevi, for the wonderful introduction. So it is my pleasure to kick off the morning session today. I was there for the last couple of days, and I attended some of the sessions out there. And I must say I was very impressed with the quality of the presentations, and I think we should all consider ourselves very fortunate that we have such a high-quality conference in India to kick off the new year. So I'm very grateful, and I'm fortunate, and I thank you guys. So this is the obligatory forward-looking statement. For those of you at the back, hopefully you can read all of this. So please let me know. So I'll give you a few minutes to read this. Just kidding. If this is all on our website, so you can you can take a look at that. But it's basically saying that I cannot go to jail for anything that I present today, right? Okay, so we'll now move to the agenda section. And so what I wanted to cover today was a few things, right? In terms of, there are a couple of topics that I wanted to do. One was an introduction to AlphaWave, which is the company that I'm with. I think it's helpful to get a context of what we do so that we can set the stage for the presentation. And so I'll take a couple of minutes to do that with specific emphasis on the India operations also. So hopefully that will be useful. I'll spend a few minutes talking about the data connectivity market, because I think that will also set the stage for what's going to be I'm talking about, which is the main part of it is how do custom chips and how do custom silicon important for connectivity. So we'll talk about that, and then after that we'll do a summary. So I've kept the presentation fairly high level. At the same time, I hope some of you will gain something new from this, right? So, and I'll definitely try to be on time for this one. So on the, this slide, we talk about AlphaWave, which is the company that I'm with. It is it's founded in 2017 by a bunch of very bright engineers who are focused on solving the problems of connectivity. We are a truly global company. We have offices in Toronto, Silicon Valley, Ottawa, London, Tel Aviv, Israel, Taiwan, China, and of course, we have a very big presence in India, right, which I'll talk about. So we have offices in Bangalore and Pune. Right? Our mission is very clear. We want to be the world's leading provider of connectivity solutions with our IP and custom silicon. And our products are DSP-based IP, that is like SerDes technologies and stuff. We do custom chips. And also, we are getting into this new line of products called optical products, silicon products. So we have about more than 700 employees worldwide, and our main mission is to accelerate the connected world. So that is really where that's the whole company is focused on. So I wanted to take a few minutes to talk about what we're doing in India. We have as we saw, we have two offices in Bangalore and Pune. And I think one of the things I've noticed about our company is that it's got a very unique culture. And the culture is based on innovation, and the culture is based on communication, innovation, and change, right? So that is a lot of that that you'll get when you at Alpha Wave India. So one of the things I'm very impressed with is the fact that the people who work here, we can get to work on some really leading edge stuff, which is developed completely in India. So it's not that you get a small piece of the stuff and work on the other, but you get to work completely in India on that. So some of the examples, we do IP for memory, we do IP for chiplets, things like DDR, high bandwidth memory controllers, and so on. Those are all completely designed in India end to end. On the custom silicon side, we also have a lot of programs that go from spec to silicon to production. And many of our engineers get to work through the entire process. So it's not like you're working on a small block, but you work from the entire process from developing the spec. We just taped out an AI chip recently where these engineers did the spec, they did all the design themselves, the physical implementation, and then go into production. So I think it's very, very interesting work, right, for the company. So I'll move now to the real topic, which is data connectivity. And I'll spend a few minutes to talk about the connectivity market, because I think that's important, right, to understand the background. This slide, I think, is nothing new, right? The main thing that we say in this is that there's a tremendous, relentless growth in data consumption. And this is being driven by the need for more sensors. There are more devices, multimedia, things with cell phones, AI, vision processing, cameras. Everything is feeding data, and there's more and more data that is being used. So again, this is probably a very overused chart. This has been this has been around for many years. So why are we still talking about it? And the reason for that is because this is not stopping, right? And it's all about bandwidth. So what we're seeing, right, if you look at the progression of things that or the connectivity world, the top slide of this chart, you may not be able to see it clearly, but the top side shows the switches market, and that market is moving from the terabit, that's in the terabit per second range. In order to feed that, you have the transceivers, which are basically running at different rates. And so you have things like the optic 100 gig moving to 200, has moved to 200 gig. And now this year, most systems are running at 400 gig. And after that, it's going to run at 800 gig. So there's a progression going on. The bandwidth is increasing. And what that does is all the silicon, the semiconductors that are in there, are also have to keep up with that. So you have the 25 gig transceivers. Now they've become 50. A lot of them have been shipping at 50 gig. Most new designs today are at 100 gig, and people have already started designing with 200 gig, right? That's the main point, right? Even with this, it's putting a lot of pressure on silicon to get more faster and more bandwidth. The next couple of slides, I want to take you through a journey of where the data is going, and you'll get an idea of why there is so much data being consumed and processed, and where is this data being processed. So if you look at this slide over here, on the left side of the slide, on the left part of the slide shows the picture of the data center. And if you look at it, like a lot of the things that you do, you have your camera, you have your cell phone. A lot of that data then goes back to the data center and it gets processed over there, right? So what that means is that this data has to go inside there, and there's a lot of computation happening inside there, right? That's where I think the bulk of the data gets consumed. So if you look at the data centers, more than 76% of the previous slide that I showed you, the zettabytes of data, is consumed inside the data center, right? And if you look at the right side, that's the next trend that is happening, is we're seeing on the edge, which is things like, if you're in an environment like Starbucks, or if you're in an environment like uh, a place like this, where you have there's these internet traffic, and then you're collecting a lot of the data, your 5G mobile phones. Instead of sending the data all the way back to the data center, a lot of that processing is being taking place on the edge. So in these things called collectors or base stations. And that's also is a new application. So there are a lot of application-specific things that are happening in that area there. So on the next part of the journey, we'll now go inside the data center, right? So this is meant to give you an idea of what's happening once the data comes to the data center, what's happening there. So on the left side, if you look at the top of the slide, you have these very high-performance switches. And all the data that's coming in from the different data centers and things come into these switches and are processed over there. And then from there on, they feed go inside the data center, right? So there's a lot of bandwidth needed at the switches that are at the entry to the data center. But once that happens, there's another trend that has taken place, which is called the disaggregation of compute, right? I think that's some of you may know it, but I'll explain it for those of you who don't, right? In the traditional compute architecture, when you had these servers inside the data center, you would have these racks of servers that are there, right? And each server would have its own processor, it would have its own memory, and it would have its own storage. And because of that, all the compute, the storage, and the memory would take place inside those servers. But the problem with that is when you have these different types of workloads like AI or vision processing and things like that, where data has to go in and there are multiple threads that are running, you may have some part of the server which is bottlenecked on the memory, some part which is bottlenecked on the storage, and so on. So now if you have to add more storage, you're wasting a lot of the other servers are sitting idle. And if you look at the big hyperscalers like Google, Amazon, how do they make money? They make money by renting out their servers, right? So for each each minute that you run the server, you pay money. So if the server is running idle, that is downtime for them. So what they've done is created this thing called disaggregated compute, where you have these specialized boxes that do one thing, but they do one thing really, really well. And so that's what we see. We see on the left side, there are these compute boxes, which include the processors. You have AI engines that just do nothing but AI. And then you have storage boxes, right? That's happening there. So on the process compute, you can use it like an Intel CPU. You can use NVIDIA now has become using all the GPUs. So that's become very popular for running AI, training, and so on. And then on the storage side, there are some storage processors and things like that. And then if you attended Victor Peng's talk, he gave a very good overview of the compute, of the different types of things, right? The CPU, GPU, FPGAs, and AI processors and things like that. But the key thing that is happening now is because these things are now all separate, when you get some data and you do some compute, and now you want to process it, the data has to go through the data center. And the bottleneck in many of these cases is not just this Intel CPU, but it's the interconnect between all of these processors. And that is why connectivity is so important. And that is why connectivity and bandwidth is what is driving a lot of the innovation in semiconductors. I think that was the backdrop of what's happening, why there's so much data, and what is the problem there. And now I want to talk about how connectivity demand is being filled by custom silicon. And this is something I'm very passionate about, two things I'm very passionate about is how we can increase more bandwidth, and the second thing, and get more data. And the second thing is how do we do more custom chips, right? Because I think customization really is the way to go for a lot of these things. So uh, this is a high-level overview of a data center chip, an SoC that's inside the data center. So no matter what kind of chip you're looking at its fundamentally at heart, every chip looks like this. You have a PCIe or CXL host interface that is connected to your Intel processor or a GPU on the left side. You have a processor that is running on the thing that does some local processing. You know, it could be like an ARM, could be a RISC-V processor, and so on, that is embedded inside the SoC. On the bottom side, you have the DRAM interface. So you can have different types of DRAM. You could have DDR type of DRAM. You could have, these days, because of bandwidth is so important, there are very specialized memories like high bandwidth memory. And on the right side is the network interface, you know, which is connected to the Ethernet, right? And so that's the building block. The block in the middle is what uniquely differentiates one SoC from the other one. And that's the one that where you run your AI algorithms. That's the one where startups do their own thing, right? You know, where they build a startup for network acceleration, they build a startup for AI, inferencing, training, and so on. So that block is what is different, but everything else around it is common across all these applications. This slide also explains why you need custom silicon, right? When we look at the connectivity, there are a lot of different things that are metrics that are used for connectivity. And the key point here is that each application has its own different trade-off, right? You know, so you have bandwidth. You know, in some systems, bandwidth is very important. So if you're in a data center, you're doing some AI training where you want to collect a lot of images and you want to do some classification and training, bandwidth is very, very important, right? Power consumption is also huge because a lot of these data centers have very high power dissipation. You want to try to manage the power. Cost is always important. So the bigger your die size, the bigger your packaging, the cost is higher. Density, the number of lanes of SerDes and so on your chip is also another factor. In some cases, like a network switch, you might need, you know, which is running terabytes of data, you might need hundreds of lanes of SerDes. In another one, which is PCIe, for example, you may need only 4 or 16 lanes, right? You know, so there's a need for different applications have different needs. Latency is sometimes important. The latency is how quickly you can go and come back, get your data back. So in things like, you know, some applications, latency is very important, like, you know, PCIe, CXL, latency is very important. And then also the robustness. So if you're in some networking applications, you're running data or some cable, you know, you want the data link to be very robust, right? And the same thing is also reach, how far your data can go, right? So this is kind of like a high-level tutorial on what the different metrics are for connectivity. But the problem then is, like, if you look at different applications, each application has a different trade-off. So do you optimize for long reach? You may have a chip that is capable of running 100 meters of wire, so you can go cable to the data center. But if that chip is only now used in an application where it's running only a few inches, then you're wasting a lot of power by using that same chip for that, right? So that is one of the biggest challenges with silicon, is how do we develop a processor that is optimized for different applications, right? And it's not that easy. And it's becoming harder and more complex. So the answer to that, you know, and it's not just me, but if you look at all the hyperscalers like the Googles, the Amazons, the Facebook, the Microsofts, a lot of these guys have realized that it is no longer an option for their specific application just to buy an off-the-shelf chip. It's customization and being able to configure, right? So if you take the same block diagram that we showed, and now we've added a lot more things to it, this is kind of what it looks like. And I took the example of what we did at Alpha Wave. to show you how basically that's configured, right? On the left, on the right side is the transceivers, which are the 100 gig or going up to 200 gig transceivers that go connect to your Ethernet cable, right? Ethernet. What we have there is configurable DSP IP. So we have a DSP block that basically with which we can configure, and then we have a lot of configurable options. So you have, if you want to optimize for power, you want to optimize for number of lanes, you want to optimize for reach, and so on. So that is configurability. So this is one way people are solving the problem, is taking one piece of IP and making it more configurable. Right? On the bottom side is the memory interfaces. And the way people are doing that, again, is in an application where you need very high bandwidth, you use something like a high bandwidth memory, right? And in another application, you may use application optimized controllers and so on, right? And then in some applications, you use PCIe, for example, which is very optimized for low latency and so on, right? So that trade-off, when you do a custom block, you can embed any of these in there. That allows you to develop a chip that is very good for that particular application, and you don't waste money because your die size is optimized, your power is optimized, and everything, right? So that's the beauty of customized and configurable solutions. I'll spend, I have two more slides where we talk about a different trend that's happening, and one of them is the emergence of chiplets. And so I think maybe this is a very, very hot topic in the industry. I think maybe some of you already know what it is, but I'll again give you a quick overview of what a chiplet is, right? So when we look at chips, right, a system on chips, the drive has been relentlessly to try to put more and more and more onto one chip and pack as much density as possible. And so that's why these chips have become bigger, more powerful, more power hungry, and driving process geometries and so on, right? But the problem that's happening right now is that the chip size is often being limited by the maximum reticle die. Now the chip has become so big that you can no longer make it bigger than that, right? It hits the limits of the technology. Once you get to very large dies, your yields become very large, small, and then you have to throw away a lot of chips, so they become very expensive. And then once, obviously, you have these big chips in very complex, small geometries, the time to market is also a big problem because these are very complex. You're talking about hundreds and hundreds of millions of gates, right? So that becomes very complex. So the goal there, the trend there is to be able to break this thing into smaller SoCs, and these SoCs are called chiplets, all right? So the example on the left side here, is we break it into small disaggregated dies, and on the right side we have the core SoCs with I/O chiplets. So that's the main that's the trend that they're doing, right? So this is an example of what we've done there. We have a data center SoC that is basically a full SoC, and on the right side it shows the different chiplets that are smaller ones. These can be then mixed and matched. And the box in the middle is the big processor, right? So the ability to break the system down helps solve that problem, but it comes with complexities, right? The key one of that is that you have to have this new IP that is being developed, which is called the die-to-die IP. Standardization is very important. There's a lot of work happening to standardize these interfaces. And then packaging is really the key name of the game here, right? That we have to have high performance packaging to put all these chips into one box. So that was the gist of this presentation. So I'll leave you with some key takeaways. The first thing is semiconductors. All of you in the room are working on VLSI and semiconductors. That is really key enabler for data connectivity. One size does not fit all. So that's what's driving to more application-specific products. And as we showed in the data, I gave an example of one data center SoC where you can see how important the custom silicon is. And finally, and last but not the least, is AlphaWave India is growing, and we have many exciting opportunities. So we're very fortunate. I am personally very fortunate to be here and talking to you guys, right? So thank you again, and that's the end of my presentation.
Thank you, sir, for the insightful keynote. Uh, Now, I would request Srini Bairi, organizing committee member from Intel, to honor our guest.
So thank you. Thank you. Thank you so much. I appreciate it. Yeah, absolutely.
Thank you, Sudhirji. Thank you, Srini. Let's move on to our next keynote on AI's disruptive impact on systems, semiconductors, and design by a seasoned scientist and business executive who has had significant roles in the world of academia, startups, and Fortune 500 companies, Dr. Rahul Razdan. Dr. Rahul heads Rastec Research Institute, a technology-based research institute which incubates ideas in the intersection of technology and society. Previously, he served as the Senior Vice President of Strategy at Flextronics, General Manager of System and Functional Verification Business at Cadence, and Alpha CPU Architect at Digital Equipment Corporation, DEC. He has built successful startups in various domains such as wireless power, machine learning, and low power electronics design. Ladies and gentlemen, let's welcome with a round of applause Dr. Rahul Razdan.
Well, welcome. Today, I've been here the last 2 or 3 days, and I'm a VLSI guy. I've never had this level of dose of VLSI. So today I want to talk about something a little at a higher level, and how this thing we call AI, just what is it, how do we use it, and what impact will it have in system designs, semiconductor design, EDA, things like that. That's the nature of my talk today. So just a little bit background. Most of my work most recently is in autonomous vehicles. So if you're interested in this work, you can check out these menus, including if you don't feel like reading long technical articles, you can just go onto Forbes. There's a large series of articles there. And then, as was mentioned, I do a lot of startups, and these are some of the startups that I'm associated with in various spaces. So if you're curious, go check it out. Okay. So, AI is this magical thing. We make it up. It's artificial intelligence, whatever that means. And what I thought is we should kind of go through some history of AI and how we've ended up where we've ended up today. So, believe it or not, way back in the 1970s, the first wave came in, and this was something called symbolic AI. And the way you should think about this is when people, especially at places like Carnegie Mellon, Alan Newell, and others, they discovered symbolic manipulation. And they applied it to things like math solving and chess programs and things like that. And there was this initial burst of capability that was made available. And believe it or not, at that time, people started worrying about things like, will this become a sentient being? Will it take over my life? And things like that. And what they discovered was that the problems that technique could solve were really limited in size because you very quickly ran into combinatorial explosion, right? So there was this AI winter. There was this huge spike in activity, and then it went away, okay? So the next wave, they said, well, if combinatorial explosion is the problem, why don't we break the problem down? And we have this notion of this rule-based methodology where we have a set of people that write down, if you see this, transform to this. And then we have a generic rule solver that tries to put this together. And these ended up being specific expert systems. And you might remember the term expert system. And companies like IBM and others were very much pushing these out. But of course, and that was another wave where people said, oh, this could be the future. If we just embed enough rules, that will lead to intelligence, right? Some form of intelligence. But you have to write these rules. It's hard to write these rules. And we went into another AI winter, right? And now we're sort of at the next phase where we have this notion of, instead of writing rules, humans writing rules, we have humans that have metrics and we have data and we have a generic paradigm of training. And that generic paradigm of training then produces an inference engine. And the applications that seem to be successful are vision, natural language processing, to some degree autonomy. And the question is this going to lead to the next AI winter or is this going to stick? That's kind of the question at hand. So I'm going to give you kind of a different view of this. One way, and by the way, I'm in the camp of it is going to stick, okay, this time. And the reason I'm in that camp is because the way you can think about the current level of AI is it's actually a new programming style. Previously, if you wanted to build function, what you would do is, the only way, electronic function, you would just build hardware. And of course, the problem with building hardware is it's hard. You have to build physical assets. And if you look at an application, this is an automotive application, things that are in hardware are typically things very much on the edge, drive-by-wire systems and things like that. And at some point, people discovered that you don't want to iterate on this hardware all the time, so let's have a standard interface called a computer architecture, and an abstraction point, and above this point, we can iterate, and below this point, we can also iterate, but the interface stays the same. And of course, this idea of software exploded in productivity on both sides. We're still living through it, right? The only problem with this abstraction level is you need armies of software designers. So it takes a lot of people to write software, to maintain it, and so on. So one way to think about the AI/ML abstraction is it's actually an automated way of building software using this training inference mechanism. And that's a very powerful way to think about this, because what that means is it's actually got many of the characteristics of how we went from hardware to software. It's just the next jump up, right? So, it's kind of interesting to say, I can just take some data and build a program, right? That's kind of a magical, almost magical thing to say. And this is some work I did a little while ago. I said, well, if that's the case, and I kind of jokingly said this in a Forbes article, well, what about comparing it to something like astrology, right? Astrology, as we're in India, we use astrology for many, many things. And putting the typical slide for marketing, you kind of compare AI and what we do with AI and astrology, and the question that comes to your mind is astrology just AI done by humans? What's the real difference, right? And if you're interested in this article, you can take a look at it. So this was a kind of a philosophical and somewhat, joking mechanism to think about this problem. But it also leads to a kind of a deeper question. What is the difference, right, when we do this sort of stuff? And the point is, this new tool that we have, it has many advantages, but there are many challenges. And the first challenge is, people talk about all these different kinds of models. If you know the terms, transformer models, or this model, or that model. So for a problem, what is the right model and why? We don't really know. We basically pick a model and we run a bunch of data and we sort of see, does it work? You know, work in quotes. And if it seems to work, we declare success. If it seems to sort of work, we sort of say, well, we're close to it. So there's a kind of this, we don't understand what, scientifically what works and what doesn't work. When we do have a model, will it converge? And converge meaning it'll actually get to a point of working reliably. We have absolutely no theory for this. There is no theory right now that exists around the convergence rates of models. People look at sort of, statistically, whether it's sort of getting better. But the state of the autonomous vehicle space is a perfect example of this. We don't know, is that on a convergence path or a divergence path, right? And really what it comes down to is, if you use a data-based approach for building this, these three things look more or less the same. If you're trying to build an AI model for addition, or AI model for vision, or an AI model for astrology, how do you know the difference between these things? It's a very deep question. This is not a trivial question. It's a very deep question, right? And then, as you may know, AI models and AI in general tends to be very sensitive to noise. And the question is, how do we understand that sensitivity? And by the way, how do we define noise? There's this kind of question of data versus noise. So this, by the way, is, for those of you in the crowd doing research and things like that, this is very rich. This is unsolved problems in this space right now. But nevertheless, we have this technique. It seems to work for certain applications. And the question is, well, how does it contrast with what we have today? And this is sort of a little chart that tries to show important ways that this technique is different than traditional software, as an example. So in traditional software, we typically have a logical theory. What I mean by that is there's an algorithm that you write, right? In ML algorithms, there's no theory. We really have something that works or doesn't work, right? Traditional software is analyzable. I can look at it, I can look at the if-then statements, I can look at the ML algorithms are not analyzable. They're basically a black box, right? Traditional algorithms, software is causal. I wrote the algorithm, input, went out, I understand the causality. ML algorithms, you could have causality or correlation, you wouldn't know, you can't tell the difference, right? Traditional algorithms are deterministic. ML algorithms are non-deterministic. They're fundamentally probabilistic in nature. And maybe the last one's the most important. Traditional algorithms, I always know the complexity of what I'm dealing with, because the algorithm is analyzable from a complexity point of view. Order n cubed, exponential, whatever it is. ML algorithms, you have really no idea the underlying complexity of what you're dealing with. So all of this kind of creates this tool, this new tool, this exciting tool, but that's different. And the title of this slide is AI, the Quantum Physics of Computing. There's an article, actually, you can read on Forbes, which sort of discusses this point, that in physics, you have this notion of general relativity in the Einstein world, and then you have quantum mechanics. General relativity is deterministic. Quantum mechanics is fundamentally probabilistic. And that kind of fundamental mapping seems to exist in the use of AI. So now we have this tool, and where does it seem to be useful, and where are its challenges, and, and where is it likely to go? So this is sort of a chart that shows at the bottom the level of function and how, in the ODD space, how fixed it is or how variable it is. So that's the bottom one. And then you can think of safety as the other column, right? And not surprisingly, when safety is not a concern, things like recommender systems, NLP systems. This is the place where AI has seen some success. By the way, for the CPU designers in the room, a branch predictor is actually AI. We just weren't smart enough to call it that, right? That's exactly what it is. When you start getting into mobility, when you have limited degrees of freedom, such as a warehouse, this is the place where the sort of autonomy aspects can be very useful. Agriculture is another place where AI methods are getting moved out in a big way. The place that's the toughest is actually the passenger car. It has the greatest degrees of freedom and the greatest safety considerations. And therefore, it's probably the last place, one of the last places that you'll see this go live. Okay? I want to talk about models a little bit. Not all models are the same. And the size of the model and the sort of what you have to deal with have a lot to do with the underlying space. So the biggest models you have out there, like ChatGPT and things like that, are all in the NLP space. You have massive, massive data sets because they're available, and you have massive data. You have massive underlying models, and these typically run on effectively supercomputers, right? They sort of have a second tier, which is an AV training, by the way, often is in that space, but not as big as NLP models. You have a mid-tier where you may be doing things like predictive maintenance, vision processing, performance optimization of various forms, where they're smaller models. You can kind of think of them as running on servers. And the space that's emerging is, intelligent edge models, where you're doing things like data filtering and digital noise. In the last 2 or 3 days, we've seen a lot of the speakers talk about the explosion in data. The kind of interesting question is data exploding because we're generating a lot of it, or it's mostly dumb data? As an example, on a car generates terabytes of data, but it's uninteresting data. The interesting data is actually quite small. And so if you have edge filtering and you're actually moving larger abstraction levels, that's actually quite useful. Okay, so let me talk about why AI is important now at a societal level. This is a chart which kind of looks at a very broad time frame of how electronics affects society, right? So, largely speaking, we've talked about 3 big waves. The first wave, this blue, is electronics was introduced, and it essentially what computing did was it optimized the G&A function of an industry, right? So G&A is finance, HR, things like that. And the big winners in that space, with the centralized computing, were people like IBM, DEC, Wang, and so on, right? And if you watch the movies from the 1950s, you'll remember, there would have been, seas of admins moving paper. And what happened with this optimization was you didn't need the sea of admins anymore, right? The next big wave was the movement of electronics to the edge. So you had cell phones, you have laptops, which means you could get to your customer directly, right? So at a broad level, there was an optimization of the sales and marketing function. And the winners were the people that did that. The people that built the devices, Apple, the laptop makers, the people that provided the interconnectivity infrastructure, Cisco, the networking people. Underneath that was the chain people like Qualcomm and others. And we're still going through this wave because things like virtualization and things like that are happening. But the next wave is, again, electronics moving to the further edge, and the pairing function of that electronics is AI, because you need something to interpret all that data and turn it into intelligence. And so it's very likely that this kind of mega wave will be the next big thing that will affect essentially every side of society. Right. So one thing I want to make is whenever you have these big shifts that I just talked about, you also get fundamental shifts in design norms and semiconductors and things like that. When we went from the shift from centralized computing to edge computing and mobility, the first one of the things that happened was power became very important because of battery-oriented devices. As we talk about the shift to this edge, one of the things that is very likely to happen is maintenance. The function of maintenance becomes very important. So don't be surprised as this starts laying out, especially in embedded infrastructure, things like cost of maintenance, managing and evolving functionality, supply chain availability. These will become much, much more important over time. And you can, by the way, see this in the auto market. You know, people like Tesla are already starting to attack a lot of this stuff. And by the way, this slide is trying to get across, in the old world, in the consumer world, the cost of the product is important, initial functionality is important, time to market is important. In these other devices, cost of maintenance is important, evolving functionality is important, and supply chain availability is important, because the devices, the systems live in the world for a much longer period of time. Okay, so these are the current hot AI applications in various vertical markets. I won't go through all of them, but they generally fall into the category of some versions of recommendation systems, data analysis systems, and autonomy systems. Okay, I want to jump a little bit deeper into sort of, even in this space, the open questions, in autonomy as an example. This is a traditional stack in an autonomous vehicle. You know, you have some kind of sensing capability, which creates inside something like a car, internal footprint then is perceived. So that's, you take a random object and you sort of say, well, that's a pedestrian, and therefore pedestrians move at a certain rate. Therefore, from that, I can figure out and predict future movement. Based on that, I do planning, and based on that, I do actuation. And this is, kind of a traditional pipeline. What I want to kind of point out is, if you compare this to humans, it's pretty bad compared to humans. Humans with under 100 watts in your brain actually do much better than, let's say, a traditional AV stack. And just 4 things to think about that humans do that current AVs don't do are these. So current AVs have an oracle model of the world. So they look everywhere all the time, as much as they can. They take all that data and then try to process all of it to figure out what to do. As you know, humans have the idea of focus. So I look where I'm looking of interest. I have peripheral vision. I don't worry about anything outside of that, right? And we have internal systems that are built to sort of optimize and manage that, and have actually mechanisms for when something is violated in that focus point. There are emergency mechanisms. As an example, if you're all focused on me, which I'm sure you all are, and somebody sneaks up behind you and touches you, that surprise will create an internal shock for you, right? That is your mind is carrying around an internal view of the external world, and when that's violated, there's a fast path to emergency. Current AV systems literally take a picture and interpret it, then they take the next picture and interpret it, the next picture and interpret it. And that's very difficult. Whereas humans actually, for the lack of a better word, do AI on movement. So you all know that if you saw a loved one or somebody you know far away, you can't see their face. But just from the gait of their movement, you can know who they are, right? So movement is actually an important parameter, which we don't take advantage of today. Perception versus observation. So there are various human experiments there are various human experiments where humans can be fooled into seeing something that doesn't exist. And the reason for that is, again, we actually do physics, we don't call it physics in their mind, and are able to act on that. So I won't go through all that since I'm kind of running out of time. These are kind of some of the additional challenges. So what's the impact? These are a lot of details, but what all of this amounts to is, on the semiconductor side, where we're going to go is on the networking side, there's going to have to be increased support for graph processors and graph structures. And kind of the traditional sort of multi-slicing stuff won't work. And on the edge, you're going to see more AI structures that are connected to analog with things like electronic noses and things like that. That's what I mean by the stuff on the right. On the EDA side, this is a slide which I'll just break out, but the point of this slide is, when you do design, system design now in the future, you're going to actually, at a high level, pick big chunks of functionality, like I want a vision system, and that vision system will have data, AI, and the semiconductor and OS chain underneath it. You're going to pick that whole thing, and that's how system design will be done. And actually, today there's no EDA support for any of this stuff, which is a big missing piece. All right, I'll just skip this. Okay, and just to wrap up, so hopefully I've shown you that AI and ML, this kind of fundamentally new technique. It has broad applicability. There's a lot of things we don't know about what its limitations are, but it will pervade through system design, it'll pervade through the semiconductor chain, and there's a need for it to be embedded in the EDA chain in the appropriate way. Done.
Thank you, Dr. Razdan, for your insights. Unfortunately, we were running out of time, so
Great.
I had to request you.
Thank you.
I now invite Sri Vinayak Godse, CEO of Data Security Council of India, to deliver his keynote on security agenda and semiconductor-led disruptive innovations. Mr. Vinayak also leads the National Center of Excellence for Cybersecurity Technology and Entrepreneurship, a joint venture of DSCI and Ministry of Electronics and IT. NCOE is engaged in cybersecurity industry building, fostering security research and product engineering, and building an ecosystem for security entrepreneurship. Mr. Vinayak was instrumental in developing the DSCI security framework, privacy framework, certified privacy lead assessor, to name a few, and conducted many of these training programs. Prior to DSCI, he worked with the global consulting practice of TCS in information risk management, and several as a telecom engineer at BSNL. Vinayak ji, the stage is all yours.
Nice to be here. This particular industry, the semiconductor hardware industry, had been very close and near to us. Because until now, when we talk about cybersecurity, we always talked about software security, network security. We had started talking about other areas, data security, all those things, but now increasingly the attack ecosystems is coming to the hardware. And as we have been working towards creating the ecosystem for development of technology and entrepreneurship in cybersecurity, we thought that there is a time now, as a country, we had been looking increasingly to create capability in hardware and semiconductor. There's a time now for us as well to focus in software and hardware security. And that's what we have started taking some action, and that led to we working with Government of India to set up this national effort for hardware security, along with some of the IITs, which I will be talking about. So the security agenda in semiconductor-led disruptive innovation is something that I will be talking in my presentation here. So So what exactly this National Center of Excellence is? It is a national effort, as I talked about, supported by Government of India, which has a physical infrastructure set up for the specific physical infrastructure for cybersecurity. We have technology lab infrastructure created for cybersecurity. We have multiple programs that we have been undertaking to initiate and help to look at the cybersecurity entrepreneurship ecosystem. We work with startups, there are almost 80 plus startups that we incubated in last 2 years of time. We engage with the universities all across the country which have focused their attention to the research of the cybersecurity, and we have been accelerating technology in the area like a SCADA security, 5G, 6G security, quantum security, forensic technology. So largely it is looking at to create an ecosystem for technology development and entrepreneurship, to look at the R&D in cybersecurity and try to productize it, look at the technology stack of a security product, create an investment ecosystem, develop a market, and more importantly, promote India as a destination for security R&D and product development, basically. And technology incubation and market development remain as a key focus and pillar for this initiative, basically. So from this, what we have been started seeing is the entirely ecosystem, the attack ecosystem is now increasingly coming to the hardware level. And for example, this equation groups attacks, which is on a hard drive firmware somewhere some years back. Then we had this hacking teams attack on firmware image. Then there is this architectural attacks, which is known as a Rakshasa attacks, basically, which has introduced a kind of a permanent backdoor to the lot of different types of motherboards, basically. Then there was this hardware Trojan, which has remained as a very important challenge for last some years of time. This particular Trojan at the gate level had been able to really infect various different systems, hardware systems as well. And because of this particular Trojan, the challenges of the hardware Trojan had become so much important to address, and they have got quite a good attention as well. Then there is this arbitrary code execution vulnerability, which was recognized by one of the GPU leading provider, basically. And then we all know, and why the hardware security become very important, and chip level security become very important, is because of the very famous, very celebrated, and more importantly, very discussed attack like the Meltdown Spectre attack, which has impacted a lot of cloud providers, which was kind of a side channel attack, and which was able to, from one application, you could able to control other application through breaking the hardware, basically, right? And this breaking app isolation at hardware level became a very important topic for discussion, and there are a lot of discussion, a lot of focus started coming in hardware security or semiconductor security after this particular attack, basically. And we see a lot of the big players, cloud providers, have started focusing their attention to semiconductor and hardware security. So when we started looking at the issues and areas of hardware security, there are a number of issues and areas that we can think about. Hardware Trojan that I talk about, device-specific, middleware security, binary-specific issues, the firmware level problem, the tampering of FPGA, HSM level specific element, the understanding side channel attack ecosystem through electromagnetic signature, feature extraction, and using that extraction to look at what exactly that can be done at a firmware level, basically, the code injection, hardware security modules. So there are a lot of areas and discussions that have start getting attention in last 5-6 years of time. And from that, firmware security become a very important branch of the hardware security, and there are a lot of things which have been now been discussed and deliberated in terms of the firmware malware, what needs to be done for firmware security, what kind of analysis that you should be doing for the firmware for security, how exactly the implants are being introduced at the firmware level, basically. Then there are other issues like using behavioral technology to understand hardware security, try to use fingerprinting technology, look at the physical verification, look at the electronic timing inspections as well. So there are various different ways and different directions this entire discussion of hardware security, the research of hardware security, to some extent now entrepreneurship in hardware security is also coming in. Also, all the OEMs, all the big product companies and the leaders in technology in this area started now looking at the security as one of the important area for deliberations. And I'm happy to note that since yesterday, I had been meeting a lot of those hardware security team in each of these semiconductor hardware kind of leading companies, basically. So then to see what is happening in hardware security. So we just try to, at the Data Security Council of India, we just try to look at what is happening in hardware security. We try to look at the research which has been published in hardware security. So some of the list that I'm just presenting here, like for example, in this year, basically last year, 2022, so these are the areas basically the researchers all across the globe have been focusing basically. Automating hardware security property verification to PUFs to be used for IoT authentication to attack registers and circuitry for 5 nanometer secure computing to vulnerability looking at side channel attack to look at the dynamic security of dynamic allocation of monolithic firmware images. So various different ways and areas the researchers, academia as well as the scientific organizations plus some of the product and leaders in technology, industry leaders basically have been working on some of these kind of areas basically. Likewise, these are the other areas like hardware security tokens, using hardware. So one part is definitely solving hardware security challenge, but other parties also use hardware capability to solve the security problems as well. So both of side, the discussions are happening at both of side. Basically, the work is going on actually in this particular area. So from that, we try to look at how can we build the agenda for hardware security in this country. So for that to understand the overall context and encapsulate for that is to understanding the role of hardware security in national security. And across the globe, this is becoming very important part. The discussions of the larger critical sector security, national security, in the current context can't really end without discussing hardware security basically. So the technology geopolitics that we are into, the supply chain security that we had been talking about, and the overall IoT adoption which is being seen. So hardware security is now increasingly featuring and coming at the forefront in terms of the national security discussion. Then, as we see that until now we had seen the interest was largely coming from the defense organization, critical sector organization or nuclear organization, but the now discussion of hardware security is increasingly being discussed in the context of health sector, in automotive, in manufacturing, in BFSI as well, in transport sector as well actually. So now until now we would, when we are doing something from Data Security Council of India, largely in hardware security, we'll see only this kind of sector until now engage with us like a defense critical sector or kind of a sensitive infrastructure organization. But nowadays, what is happening is the medical sector, the automotive sector, manufacturing sectors are increasingly looking at this area as an important area for them to look at basically. Across the globe, we had seen a lot of research initiatives and programs that have been underlain for the hardware security. There are certainly some effort which is being put at a standardization level as well. At India level, there are some labs that we have seen in IITs which are coming in hardware security, doing research in hardware security. Some of the things which are now, we see that until now the focus was largely on testing, evaluation, assessment methods, and creating test setups and looking at supply chain security. But now increasingly the focus is going for more advancement into testing and evaluation methods, trying to take this to more sectors, trying to look at the firmware level security, focus on engineering part of engineering the hardware security part into the development of the products basically. And then how do you develop this capability in entire operational life cycle of the entire design and development of a semiconductor hardware chip designs basically. So this is the area that we see that now focus is going on. In terms of the entrepreneurship, we have some of the global companies known in this area now, Absolute, Reform-Bob, Exin or Plixlium. But in India also, we have these companies working in the hardware security, exploit, secure SI, secure wave, chip spirit, and some of them. If you go to expo zone. So some of these companies, we have bought it here. They are demonstrating the capability that they have in hardware security. So this context is an important context to understand how exactly the, the discussion of hardware security is evolving largely from the defense, national security specific discussion to all the industry sector and where it was and where it is going now and what kind of research ecosystem is coming for this and where exactly the startup entrepreneurship is coming in this area. So after looking at things, what is happening, basically, we started thinking that what should we do at a national level? And that's what this national effort for CHICC, Center for Hardware Entrepreneurship Research and Development, that had been devised and conceived with the help of Ministry of Electronics and IT and with IIT Madras and IIT Kharagpur, and the ESA is working towards setting up this particular initiative. Last year, we started taking some actions in this area. So what exactly we are trying to do, and that's what we came here. We came here to discuss with the hardware industry and seek the partnership for this. So what we are basically focusing on is focusing on the research in this area, because this area requires a lot of research intervention and there are a lot of effort is required. A lot of PhD students are now started taking interest in hardware security. There are institutions like IIT Madras and Kharagpur has developed quite a good capability and focus on a research in hardware security. That's one of the key foundational effort that we'll be putting together as a part of this initiative. Then comes the effort for productization some of the research as well. So this is one of the important things that we have seen, that the research is happening, but it's at the end ending to in terms of the publishing paper or developing some prototype, some kind of prototype basically. So how can we productize and commercialize the research in hardware security is an area that we'll be focusing as a part of this effort. Development of tools, guidance and reports for somebody who is building hardware solutions, somebody is using those hardware solutions, so probably we'll be focusing our attention to create those tools for those people to use, those kind of target segment to use, and also the reports around those areas so to create more awareness about the issues and challenges of hardware security. Then comes the startup ecosystem, which we would be definitely taking some effort to nurture the startups in hardware security. We have specific acceleration program for that, and we have been working. There are already some startups in this area. Building capability is definitely one of the important part that we'll be focusing in terms of hardware security. Creating assurance report, helping some of the national security specific defense organization specific institutions to solve the supply chain security issues. And also, as we see the entire ecosystem is going to sectors, we will be also working towards creating preparedness of a sectors from the perspective of hardware security basically. So this is a basic structure and a kind of a framework for the initiative that we have been setting with the help of the IIT Kharagpur and IIT Madras. We are now working towards setting up a security lab which can help us to devise and set up this attack ecosystem, because that's the very important part to understand how all the products which have been leveraging hardware capability, how they behave in terms of security. We were also looking towards different target systems that we can look at and do the experimentation. We have the measuring equipment, and now we have been looking towards creating some kind of effort, putting some effort in terms of helping us to manage the hardware security challenges basically. And we are also leveraging the lab capability at the different IITs. I talked about IIT Madras and IIT Kharagpur, but other IITs also now joining this particular journey. We are also trying to look at, one of the key part of this initiative is also trying to understand, if research is a focus, we are trying to look at what can we do to understand the research happening in a cybersecurity space. So this is a specific application that we set up which try to now track the research work of 220 plus professors in security area. In that, hardware security is one of the important area across the India, the kind of research which is happening in a cybersecurity space. We continuously track that and put it to the level of the consumption basically. And then out of that, hardware security is one of the important area. So currently, if you just look at, there are almost 40 areas the Indian researchers are working in hardware security, right from IoT security, embedded security. PUB is definitely one of the important parts, cyber attack ecosystem, IoT forensic. So there are various areas are now explored as a part of the overall research happening in academia in hardware security or semiconductor security space. and we are trying to see and engage with all of those professors. We are trying to create that industry ecosystem as well to engage with academia researchers in this particular area. And then we see what can we do, how can we take it forward from now to the coming 3-4 years of time. So we have been also with the help of the researcher community plus the capability that we have generating here in DSCI, we have been trying to set up these kind of a capability training sessions in hardware security. We have started this, but probably will be scaling up this effort with the help of the researcher as well as the industry community working with us in this particular initiative. I would really like to conclude in terms of this agenda that we have been creating, right? So one is certainly look at the engineering minds and trying to attract them to the challenges and issues of hardware security. That's why we started now looking at hackathon or CTF specific for hardware security. Probably will be also coming up with the development challenges in the security side as well. Startup acceleration program is one of the important things that we'll be focusing on in terms of hardware security. We have been specifically putting attention to have the more number of startups in hardware security. We also are creating some incentivization mechanism where we have funds and we will work with the industry as well as the government to invest into research in hardware security area, co-create the solutions and also try to productize those solutions as well. And at the same time, the effort will be also trying to put together significant attention to develop market for the hardware security capabilities and research happening in the country basically. And for that to happen, basically, so what we are looking at as a national effort, and that's what we have come here, is a partnership and engagement with the entire ecosystem in semiconductor hardware in this country, basically. All large companies working in this area, plus the startups which are working in semiconductor hardware, so we want to closely work with them. And with them, we want to work with power sector, the AV sector, the defense sector, the health sector, the banking, BFSI sector, to create awareness about the hardware security challenges and more importantly, create an ecosystem and helping them to address those challenges by providing those capabilities, tools and instruments and more importantly, the product as well and some kind of incentives and capability building exercise. So that's what we would be trying to do from now and this is a very 1 year kind of old initiative that we are undertaken, but henceforth we will be coming closely to this particular industry, semiconductor VLSI or hardware system design industry basically, and to see what we can do together to bring attention to hardware security challenges and issue, one. Secondly, to create capability in this area. Third is to make sure that the product that we are developing from hardware semiconductor perspective are secure. Also, we would also like to learn how the hardware capability can be leveraged for solving some other security challenges we have in other areas basically. So that's another important thing. And also the creating a kind of a product ecosystem in hardware security space and more importantly help the security agencies, the critical sector organization to solve the national security challenges emanating from this technology, politics and supply chain security. So this is what the program that basically we are undertaking with the help of government and with help of with associating with the IIT, different academic institutions, and we look forward to work with this semiconductor hardware industry. So with this, I would like to conclude my presentation. Thank you.
Thank you so much, Vinayak ji, for your time and for your insightful keynote. Now, I would request Sri Venkatesh Narasimhan Garu, Senior Director, Silicon Labs and Organizing Committee member, to honor our guest. With that, we move on to our next keynote by Dr. Makoto Ikeda of University of Tokyo on hardware acceleration of functional encryption. Dr. Makoto-san Joined the University of Tokyo as faculty member in 1996. He belongs to the Electrical Engineering for Education and Research and VLSI Design and Education Center for Chip Design Platform Activities for Japanese universities. His research interests include hardware security, smart image sensor designs, and time domain signal processing. He has been involved in various international conference activities, including ISSCC for 18 years as a committee member and ITPC chair. VLSI Symposium for more than 24 years as a committee member and many other positions. He was conferred the IEEE SSCS Distinguished Lecturer Award in 2015 and 16. Please welcome on stage with a round of applause, Dr. Mokoto-san.
Thank you very much for kind introduction, and thank you very much for inviting me to here in Hyderabad. I'm very happy to be here, Hyderabad. Actually, I attended the VLSI Design Conference year 2020, which has just before the COVID spread. And again, this time I'm happy after 3 years of COVID disasters, I can come back to India for this conference. So my talk is hardware acceleration of functional encryption, which is very related, or how to say, hardware side of the security, that we have a very good overview on the cyber side security. So this is an acknowledgement. But by the way, we got a good amount of funding from Japanese government because of 2020 Olympic game. So Japanese government really keen about the security. So they put firstly amount of money to cyber security. But after all, they realized that the hardware is also the key for the security. So we got a good amount of the funding. So this is the agenda of my talk. So basically, I talk the very brief background of my talk on what kind of hardware acceleration we did. And then I'll talk about the elliptic curve-based encryption engine acceleration and some of the examples of functional encryption. And then I move to the fully homomorphic encryption that some of you might know that Google have the open source library for fully homomorphic encryption last year. So that is really fascinating me to accelerate it. And then finally, I'll talk touch about some of post-quantum encryption stuff. So why we need to have hardware acceleration of encryption engines? Some of you might assume that, oh, we can do that by your mobile phone or computing device or even cloud servers. So we don't need to have hardware acceleration. But this is, for the case of encryption, it is almost the completely digital. So it can possibly performance scaling using advanced processes. So we can learn from the history that you might know the LDPC, which is the very sophisticated algorithm, which is widely utilized for mobile communication at this moment. And that was invented 60 years ago, and at that time it was almost useless, so it's almost forgotten for 40 years. But it was really efficient algorithm, and about 20 years ago, the technology realizes that, and now it's everywhere. So I really expect that kind of thing will happen for very complicated, sophisticated algorithm or encryption algorithm can be realized in sophisticated hardware acceleration. On top of that, optimizing hardware can easily applicable to very, very tiny IoT edge devices. That can be utilized for everywhere for your daily life, so that the edge devices can be utilized for encryption or much advanced encryption like functional encryption. That is the assumption. You can see very tiny the has the illustration at the bottom. So there are algorithmic complexity and computational complexity. If you are a software designer, you only care about computational complexity, but you might assume that both are very important. For example, for RSA, if you maintain the security level, you have to increase you have to introduce the longer keys. That increase the computational complexity very high. Okay, so what is advanced encryption? Some of you might know, but there are a bunch of functions that can be realized in cyberspace. For example, I will talk about attribute-based encryption later on, but instead of using stored key, you can adaptively generate a key so that you don't need to be afraid of leaking the stored key. Or there are searchable encryptions that you don't need to decrypt your data to doing searching operations and so forth, and so forth. So this kind of functionality is not easy to realize at this moment with even utilizing supercomputers. But if you can accelerate by sophisticated hardware, it could be realized for your daily life secure. Then what is homomorphic? That is next step. So instead of using the data by the plain text, you can do all kinds of operation in cyberspace so that you don't need to decrypt your data even on your cloud side, so that your cloud service provider even cannot steal your important data. So for the homomorphism, there are additive, multiplicative, and also fully homomorphic. And fortunately, RSA having the multiplicative homomorphism in nature, but you can realize the additive or fully homomorphic using these kind of algorithms. So let's move on to elliptic curve base. So maybe most of you, if you are familiar with the encryption, you know what is elliptic curve based encryption. So basically, the algorithm is just the geometrical operation over the elliptic curve. But important thing is all the number is not a real number, but the number on the finite field, like a tooth extension or primary field. So basically, you know the algebra, like shown in the bottom center, and it's only the middle school mathematics. But important thing is these are in the finite field numbers. So division is very difficult. So instead, we can convert the coordinate showing on the right-hand side, so that instead of using affine coordinate, you can use projective or Jacobian coordinate so that to reduce the number of divisions. So why this is safe? So this is called discrete logarithmic problem on elliptic curve named ECDLP. So it is very difficult to extract k from k times g. What is k times g? We call that scalar multiplication and shown in the middle top. So you can easily decompose that onto the multiplication, doubling and addition. So usually we can use binary manner or using Montgomery ladder manner. Binary manner is suitable for the sophisticated or faster operation. But this having a leakage of the key information or K. So instead, we usually use Montgomery ladder if K is very important. So to realize that was the software, there was mathematics, But to really implement on hardware, we need to the explore the hardware or architectural investigation, how many the functional unit you use, or with the pipelining stage, and so on and so forth. And in addition to that, we need to do so-called scheduling, depicted in the middle, so that how efficient that kind of the operation can be realized within with maintaining the data dependencies. So we have done a bunch of that, and at this moment, for the case of around 200-bit to 400-bit operations or data paths, 7-stage pipelining would be the optimum, and we can realize almost the 80 to 90% of hardware efficiency showing on the bottom. So at the same time, as I mentioned, for the case of RSA, you have to utilize 48-bit key. For the case of elliptical, we have to utilize 256 up to 380 bit. So the question is how much the functional unit, bit width of functional unit you have to utilize. So for the case of software, it's only determined by 32-bit or 64-bit based on your CPUs. But for hardware, we can freely choose up to fully radix down to 32-bit or even the bit serial operation. So we can explore that, like showing here. It is very important to see that for the fully radix down to, say, 64-bit operations, it can be having the data has a trade-off between the area or hardware resources and the time consuming. But below that, because the number of memories are the limiting factor, so there are no shrinkage over the hardware size, but the latency increases. What does this mean? So maybe software designer don't care about anything about the hardware resources, like how many memories you use. But for hardware, memory matters. So that's the reason we have to be carefully designed. So a software implementation like a 64-bit or 32-bit is not an efficient implementation, learning from this. So we explore that, and we have implemented some of the specific ones. One of which is very high performance with higher hardware resources. The other extreme is showing on the right top with very small amount of hardware with relative latency. For that case, we utilize SRAM instead of using flip-flops, so that SRAM having the data access overhead, but still we can shrink the hardware resources down to very small, so that we can implement that onto the smaller IoT devices. By the way, this consists only 10 kilo gate. We have implemented and we have measured. And for the case of smaller one, we can realize about less than 0.1 milliwatt operations. And for the case of the power hungry or high performance one, it goes up to 1 watt operation with only 1.5 million gate. Some of the CPU guys assume that it's so power hungry, but as I mentioned, we optimize our hardware so that the almost 80% or 90% of hardware is operating all the time. So that's the reason this is very power hungry. But for the case of power efficiency, for power hungry one can realize only 3 microjoule per operation. For on the other side, for the smaller one, it consumes about 70 microjoule. So much the power efficiency if you use the high performance the implementations. So this is a comparison that we have done and with the other state of the art. We have realized a much faster operations with much smaller amount of energy, even comparing with the ASIC, FPGAs, and the CPU implementations. So for the functional encryption, one of the mathematics we need to utilize is so-called pairing operation, which realizes by linearity showing in this equation on top. This is also the operation over the elliptic curve. So that's the reason we can easily adapt the experience on the elliptic curve-based encryptions. And we have started this about 5 years ago, and at that time, the fastest the implementation on the CPU is something like 200 microseconds for one pairing operation, and the FPGA can realize 100 microseconds per operation. And that realizing the searchable encryption around 10 seconds. So it's still too slow at that time. So at least one order of magnitude improvement is required. So that was a strong motivation for us to realize in ASICs. By the way, for the pairing operation, although this is based on the elliptic curve, but still we need to think of the security level as well as the applicability. So at that time, 5 years ago, BN curve was the optimal choice. And using 254 or 256-bit key, it is said that the 128-bit security level was maintained, but after a few years, it realized that the security level degraded down to 110 to even 100 bits. So it's almost useless at this moment using BN curve with 254 bit. We need to increase the length of the keys. On the other side, VLSI curve is now emerging for the much safer with much hardware efficiency choices. How we realize the pairing operation? We basically calculate so-called extended field. This is something like extending our real number to the complex number. So we added the dimension to 12th degree. So you can easily follow the equation like this. So again, mathematically, it's very simple, but the implementation takes quite a long time with a very large hardware with the longer clock cycles. So we again explored what will be the best optimal design, and at this moment, we chose all the operation based on 2's extension field and realized the 12th stage pipelining would be the best at that time. But because pairing operation requires the relatively complicated operations, so instead of using all hardwired implementation, we put controller or sequencers for controlling everything. We implemented and realized about 3 or 4 times the performance improvement. Again, this is very hardware efficient implementation. So it goes up to 3-watt operations. Again, very power hungry or very heat implementation. So what next? As I mentioned, if we migrate to the advanced process, we expect that the performance will be scaled. So for this case, we implemented using TSMC 12 nano process, and fortunately, we could realize almost 1/3 of 3 times performance improvement with almost 10 times the power efficiency improvement. What else? For the pairing operation, instead of having single pairing operation, so-called multiple pairing might be required for functional operation. So for that case, instead of having the single core implementation, we could use multiple core realization, which can accelerate the multiple pairing operations. So we have done such kind of designs. Again, we have the sequencer inside the core itself, and also we have the sequencer outside the core to control all the cores. So that to accelerate everything by changing the configuration depending on the requirement. This is a comparison. So again, using the advanced process, we can realize about 10 times improvement, as I mentioned, for the single pairing operations. So now we can realize 10 microsecond operation per each single pairing. And for the multiple pairing, we can realize much performance acceleration comparing with the other by multiple core implementations. Then going to further functional encryptions, we pick the attribute-based encryption as an example. What is attribute encryption? So instead of using stored key, we can generate the key to encrypt or key to decrypt on demand instead of using the explicit keys. And key generation can be determined by so-called attributes, just depicting here. So if you are the employer and having some state, then the system grant you to decrypt your data or something. There are several types of attribute-based encryption. One is key policy, and the other one is ciphertext policy. So we chose the latter one, and there are several steps to realize that. One is setup to hold the system, encryption, and key generation, and decryption. So among there, we carefully analyze what kind of operation required. Of course, this entire encryption system is based on elliptic curve. So elliptic curve based the operation like scalar multiplication is portion of the computation, and then pairing operation and the other elliptic curve based related computation like hash curve map onto the point of the elliptic curve. So we have implemented, for this case, onto the FPGA and comparing with the software implementation. And for the setup, we have only 4 times improvement. But for the case of encryption, decryption, we go up to 7 to 9 times performance improvement, even using the FPGA. So we are really expecting to realize much better performance improvement by ASIC implementation. So fully homomorphic, it's almost running out of time, but we also having doing for real fully homomorphic encryption. But as an example, I showed the example of pairing algorithm realization, which is just adding one exponentiation terms over the RSA. So it's relatively simple in terms of algorithm. But as I mentioned, because this is basically similar to RSA, we need to utilize at least 2048-bit or more longer key for maintaining the security level. So implementation matters for that kind of very long keys. For this case, we put all the data paths with 2048-bit. So it was huge amount of the logic unique as well as interconnections. But fortunately, compare our implementation shows the much faster the performance, even comparing the FPGAs, because FPGAs basically all the operations are based on DSPs, which is 48-bit or 32-bit. So instead of dividing all the operation into such small pieces, we can realize all the mathematics into full radix. That's the source of the performance improvement. So post-quantum, so you might know that the last July, NIST have finalized after, 5 years or 6 years of discussion, for the finalists or the possible candidate for standardization of the post-quantum encryption algorithm. 4 out of 69 initial proposals have been decided. And there are two types, key exchange and the digital signature generation. And the crystal skybars were the only selected the algorithm for key exchange. And fortunately, we have been doing trial design for crystal skybar for past 3 or 4 years. And so we have presented this one at the last ASCCC in November last year. And what we can do is we can generate a key for this one because this is a key exchange mechanism. And we can, it's not an encryption, but encapsulation of the key. And we can do decapsulation of the key so that we can fulfill the crystal Kyber's algorithm. We have designed, compared, and the comparison results shows that even with the state-of-the-art ASIC implementation, our design have more than the 2 to 10 times in performance improvements. So, in summary, we have been designing the bunch of hardware acceleration of crypto algorithm. And basically, of course, we skip all the security measures like the side channel attacks and algorithm level security and so on and so forth. But we also have been collaborating with other universities, and almost all the chips have been demonstrated as shown here. For the elliptical one, we put this one onto the surveillance camera so that the surveillance camera having all the data be digital signature attached. And for the case of pairing operation, we put that engine onto the searchable encryption software, and they are connected by PCI Express, and we demonstrated the performance improvement. For the Pioneer, the engine, we have the kind of USB dongle, so that once we plug in that device, we can utilize the additive. So we can do the accumulation of numbers in the cyberspace. And finally, of course, for the crystal Kyber, we have the preliminary demonstration put over the FPGA so that we can demonstrate much faster operation comparing the CPU operations for key generation, encapsulation, and the decapsulation of the post-quantum encryption. So this is all my talk, and thank you very much for kind attention. And
Thank you, Mukesh Hand, for taking time out for us, coming all the way to Hyderabad and being part of this summit. I would request Shri Prasad Haldule, Principal Engineer Marvel, to honor our guest, please.
thank you very much. Thank you very much.
Our next keynote is by Dr. Madhav Pulipati. He will focus on alternative computing paradigms. Dr. Madhav is a firm believer in the concept of alternative computing paradigms as the course of technology roadmap for India to catch up or even lead the global discourse in the ground of Beyond More. He heads Photonics Valley Corporation, an organization aimed at facilitating the evolution of such alternative computing technologies. Currently, he is in pursuit of cultivating ecosystems for constituents such as design houses, manufacturing units, and supply chain industries. He has a doctorate in postmodernity. Please welcome Dr. Madhav with a round of applause.
I know that after Professor Ikeda's detailed lecture, it would be an oxymoron to my lecture, my address, in the sense that it is going to be completely different. It's going to be a bird's eye view, macro picture, not meticulous picture. Though I would like to connect my presentation to his presentation. He was talking about post crypto encryption. I advise Professor Ikeda, while going back to Japan, not only you are taking these accolades from us, but you please visit one of the stalls over there in the exhibition under AMPIC. They are developing photonics integrated circuits for accommodating quantum key distribution through phase transformation methodology, not entanglement. Please have a look at that. You will be additionally benefited for coming to India. With this, let me start by quoting a statement by Gavin Barchelard, who says that we are undergoing a process of transformation, or he calls it as an epistemological break. That is, for the past 45 years, we have been seeing the conventional, traditional computing technologies progressing into single-digit nanometers. Now, we don't know whether we'll be progressing in the same line or we are trying to come up with alternative methodologies. So today I'm going to talk something about alternative ways of thought processes, in the sense that we are attuned, we are educated, we are Sanskritized, we are encultured to think the way our fathers think, to think the way the leading opinion makers, scientists think. But are there any other ways to think? Can we also break away from this monotony of conventional wisdom? So this is briefly the points which I was trying to make today. I am going to make today. Contextual rationality. And I will be ending up with TPS, which is our initiative. Contextual rationality in the sense that what we are going through now at this point of time. If you raise yourself from the slides of Professor Ikeda and raise yourself above India, raise yourself to a global level, raise yourself about technological deterministic levels, then you will find what is happening all over the globe. It is a bird's eye view, what I mean to say. That is the contextual rationality I'm talking about. There is a huge debate going on. I think it's an age-old debate, a decade-old debate. It's a boring debate. Whether we are in the status of beyond Moore or more Moore. I think everybody knows about Moore, who has come up with Moore's law, according to which computing evolution progressed more or less for the past 40 years. And he was simply saying that, miniaturize the components which go onto the chip so that more components can be added, so that the computing capability of the chip will be doubling up every couple of years. It's very simple. So now we reached 5 nanometer, 3 nanometer, 2 nanometer. That means, are we going to end up with our computing decimation, or we still can do something down here? So more proposers, proponents talk about, no, there is nothing like limitation of the Moore's law. We can transform, we can go further. Beyond Moore, yeah, Moore is done. Computing is done. Conventional wisdom is done. Let's go with some alternative technologies. Let's search for the alternatives. That is beyond Moore or more Moore. And the whole world is grappled with the data centrism at this point of time. I talked about surveillance capitalism, control societies, in the sense that now the way the metaverse is going to happen, the way social media is progressing, there is not going to be a huge amount of time before every aspect of human life is observed, is noted, is recorded, and hence can be manipulated. So surveillance capitalism is the name given by the Harvard University, and control societies is what this capability of observation can lead to a deterministic governance. Then technological determinism, everything is technology now. All aspects of our lives are controlled by the technology at this point of time. And we are onto this fourth industrial revolution. Yes, we are onto this fourth revolution, which is going to give rise to the control societies. Then the changing geopolitical situation. We are going through really anti-globalization spree at this point of time. For the past 20, 30 years, people were pushing globalization. Glasnost, perestroika, liberalization, open the gates, no walls, global village. Now probably we are entering into the era of anti-globalization. We are constructing walls. We are looking inwards because of several major changes in the geopolitical situation like pandemic and other situation. This is the contextual rationality. This is the present day situation, a macro picture again for today. Though Indian context, where do we stand? Where does India stand, basically? So, because of the colonization, because of several other reasons, we missed 3 industrial revolutions. We did not go through the industrial revolutions in the sense that we did not participate as an active participant, and we were always at the receiving end of the industrial revolutions. But now, fourth industrial revolution is onto us. So where do we stand with reference to the fourth industrial revolution? Whether we can participate in that, in what way, whether do we have any chance? Because we weren't having any presence in the previous revolutions. And no manufacturing infrastructure, ecosystem, demand for, yeah, ESDM, electronic system design and manufacturing. I think for the past 2 days, people have been throwing statistics at you about ESDM and semiconductors industry in India globally, so I don't need to say much. Geopolitical situation is pushing India probably to become one of the manufacturing alternatives. That could be a possibility. And everybody knows that we have Indian semiconductor mission, which is aggressively pushing for the establishment of semiconductor units under several categories like CMOS, display, compound semiconductors, silicon photonics, blah, blah. So we are having state governments and central governments aggressively pushing for the establishment of semiconductor manufacturing in India. The challenges which we face for India is no ecosystems, no differentiated technologies, no legacy, no R&D background, no connect between academia and industry. This is one of the very important for technology revolution, but we don't have. And the last one is the colonial mindset and structures. What I feel, what we think that before changing ourselves, before transforming ourselves, probably we need to overcome the colonial mindset. Colonial mindset in the sense that for a couple of hundreds of years, we were under colonial regime and we were forced to think that we are inferior. Probably that is making the brain drain into the comfortable countries from India. Now the thinking is that we need to overcome this colonial mindset to do something on our own. Yeah, this is where actually my presentation begins. I think I'm left with 12 minutes, that's fine. We are talking about alternative computing paradigms. For the past 40 years or 50 years, we are progressing with some kind of a philosophy, computing philosophy, which talks about traditional methods of computing. But as I said a little while ago, that we may be going beyond Moore. In that case, what needs to be done? This is beyond Moore scenario. I'm going to talk about beyond Moore scenario. Because for the past couple of days, speaker after speaker, philosopher after philosopher, executive, corporate executive after corporate executive, might be talking about more. How do we make computing more attractive, more useful, more agile? But we never thought that, okay, this is not the only way of thinking for computing. Can there be alternative ways? So we are talking about alternative computing paradigms because these alternative computing paradigms are very important for India for 3 reasons. One is they require no legacy dependency. These alternative computing technologies do not have any dependency on the traditional or conventional computing technologies, so it can be a takeoff afresh. Then they offer level playing field. Even though you miss 3 industrial revolutions, now you have a chance. You have a chance to crack at the 4th industrial revolution because you don't need to depend upon what are the inventions of the previous 3 revolutions. And these alternative computing paradigms definitely provide low capital intensity for manufacturing in the sense that, let me progress and explain that last point. And as we know that semiconductor industry, manufacturing or design, they exist in ecosystems. Eco- they cannot function independent of each other. So the whole point is how do we build ecosystem for alternative computing technologies? Then how do we manage industry and academia continuum? Because we are definitely having silos. Industry and academia and industry are absolutely not connected. That is the biggest problem we need to address. Then global connect. We cannot stay in isolation in this world because somewhere something else is happening in the alternative computing paradigms. We need to get connected because we need to avoid what is called reinventing the wheel. That doesn't happen with the emerging technology. That should not happen with the emerging technologies. Then other connects like industry, technology, capital connects are also important. The most important thing is non-hierarchical incubation, like alternative computing paradigms require parallel thinking, rhizomic thinking. That means there is nothing like great nation, great research institute, or poor nation, poor, nothing. Everybody is important and we need to have non-hierarchical incubation. Yeah, this is the actual alternative technologies I'm going to talk about. I'm going to talk about photonics, quantum, and neuromorphic. These I feel as the alternative computing technologies. People may differ, people may come up with some other technologies or alternative technologies, that's fine. Because alternative technologies emerge from alternative thought process. If you have a thought process that we need to move away from the conventional computing technologies, that's it. You will come up with some kind of an alternative measure. So I am totally connected with photonics and quantum. With reference to photonics, I know everybody talks about photonics, photonics is the future and blah blah. But for me, there is only one sentence. Photonics has established in communication space and it is progressing towards computing. What is meant by communication space? As we know that we are entering into nanometers, we do have a limitation because computing cannot progress further after 1 nanometer because the simple atom's circumference is 2 nanometers. You cannot go beyond 2 nanometers or 1 nanometer. So what do we do? Conventional thinkers, conventional computing technologies propose that parallel processing. If you cannot improve the chip, you tie a bunch of chips into parallel processing or MCMs and make this bunch of chips to act as if it is one chip and act on the task. So this parallel processing has emerged. I think you must be very, uh, one simple example of parallel processing is octa-core, quadra-core, or the biggest example is, example of parallel processing is high performance computing, where billion wave parallelism is happening in the sense that billions of processors are acting upon the task at the same time and they require to be connected. They require to be coordinated to act upon the task. So the connectivity is becoming really, really big issue. Billions of processors getting connected with electric connects. That brings in latency, that brings in power consumption, that brings in quantum tunneling. So many problems that will be bringing. So this parallel processing requires some kind of a transformation. Photonics is the way probably because you connect this processor through photonics, they will bring in speed, they will avoid the latency, and most importantly, they reduce the power consumption drastically. And here in our stall, one of the greatest innovations is happening. I think you have missed that point. There is a company called Lightspeed Photonics, which has come up with free space photonic communications in the sense that between the two nodes, photonics can be connected through an optic fiber, but they have come up with free space. That means photonics like Wi-Fi, photonics in the air. So the two nodes can get connected through photonics without any wire. That is the future. So billion wave parallelism is going to stay here in the supercomputing arena before quantum computers take over the supercomputers, and that is going to be the way. So photonics have started already offering viable solutions in the communication space, but they are also progressing towards computing space in the sense that in 4 domains, like data communication, telecommunication, astro communications, and quantum communications, photonics integrated chips are happening. It's no more an enigma, no more a doubt. They are happening. But in the mainstream, for them to happen, programmable PICs are yet to get emerged. I think we are traveling there. And again, I will point out to that T-Face stall where there is a company called Ampic which is doing the same thing in India. Yes, quantum photonics. This is, I want to spend few seconds on this. Like, everybody knows that the quantum computing is completely out of blue. It doesn't have anything to do with the traditional computing. And the algorithms, the methodology, the philosophy, quantum philosophy itself is completely different. But there are 100 different ways of exploring quantum computing in this world at this point of time. The dominating is superconducting material-based qubits, and other is quantum dots. The other one is ion trap, topological. But we adopted, we brainstormed, we think in India that quantum photonics, that is materialization of quantum computing through photonics is the most viable way. Because other ways of developing quantum computer requires the functioning of quantum computer at absolute Kelvin temperatures, that is minus 273 degrees. Then you cannot have desktopization of a quantum computer. You cannot have quantum computer here and you operate, because it has to be stored at a place in a building where it has to be cooled to a temperature of minus 273 degrees. For that stage to a desktopization stage, it's a huge journey, and this journey can be overcome with photonics, because photonics based quantum computer operates at room temperature. And quantum communications and quantum computing and quantum sensing, these are the three major areas. Quantum communications is nothing but photonics communications. Quantum basic qubit is nothing but couple of subatomic particles in an entanglement status. That is qubit, that is the circuit. That's it. Let that be photons. 2 photons, that is what our approach is. So quantum photonics, whether it is the future or not, we are thinking that it is the future. So now what we are trying to do to promote alternative computing technologies in India, we have come up with few platforms for VLSI itself, by thinking that VLSI dovetails ESDM, Electronic System Design and Manufacturing. So VLSI is an essential item for the development to have meaningful ESDM happen in India. Under the VLSI, we have come up with 3-layered approach. One is skilling platform with the institutions like TASC and TWorks. If anybody knows about Hyderabad or Telangana, we are at the forefront of technology revolution, and we have come up with so many ecosystems and so many institutions for the propagation of technology. These are some of the institutions which are trying to collaborate for a skilling platform. Then there is an incubation platform, T-Face. This is a virtual platform. It is a collaborative platform. It is industry intervening platform. This platform is giving rise to the startups in the alternative computing technologies like quantum photonics, and quantum technology. We are coming up with a VLSI Innovation Lab. I think this is very contextual for the VLSI conference itself, because most of the startups, everybody talks about entrepreneurship, everybody talks about nurturing the wealth creators. That's how nation should grow. But the thing is, we don't create enough infrastructure for the startups to function and grow properly. Now, a startup, generally after designing, they'll be going for the MPW runs. After MPW run, what? Characterization and testing have to happen. Where are the facilities in India for the startups? No, absolutely not. Then you have to look beyond the India. Here, we decided to create an innovation lab, especially for the startups, to serve them on characterization testing services with the industry support again. This is the T phase. I listed out elaborately how do we function. The 2 key points are industry intervention is happening, industry mediation is happening. Then we are positioning it as an incubator of incubations, because a startup can live anywhere in India or abroad. As long as they are dealing with alternative computing technologies, they can get accommodated here, because this is virtual cloud-based incubation. At the moment, 30 startups are available and 50 in interdisciplinary cyber-physical systems. So we have 80 startups at this point of time. So I think I'm meeting my deadline. What we are trying to do is that, let's say, stop to support the wealth creators. Let's start cultivating our own wealth creators. These are the guys who will be adding to our GDP, who will be creating employment, who will be creating further industrialization in India. Then diffusion of technology. Microsoft's CEO Satya Nadella was here last week. He was talking about technology diffusion. If a nation, he was talking about some technology diffusion algorithm of Dartmouth, and he was quoting a scientist saying that he developed an algorithm for the evolution of the technology. He says that whichever country adopts technology, the current happening technologies, and diffuses them into the society, that country is going to make the difference for the globe. So technology diffusion, I was talking about the same. And it's not enough if we educate our kids in the technology and do not consider non-technocrats into the technology space. The whole society has to become technology society. That means diffusion of technology will result in a knowledge society, technology knowledge society. This is how we can progress probably in the alternative computing technologies. That is going to be our mantra. I think brain gain will happen. Brain gain means reversal of brain drain. That will happen once we create the happening discourses down in India. Thank you.
Now, I would request Mr. Balpreet Singh, Director of Engineering, Intel, to honor our guest. Thank you again, Dr. Balpreet, Dr. Madhav and Balpreet ji. Next keynote is on Vega microprocessors by Dr. Neetha Maria Selin, Joint Director, Hardware Design Group of CDAC, Trivandrum. She has close to 2 decades of strong working experience in embedded system design, circuit design, PCB design, and FPGA-based product development. Dr. Neetha has played a key role in the successful implementation of many projects in the hardware design group. She is leading the design and development of cost-effective Vega SoC-based development boards. She has designed and realized multiple ATEs for space applications and is currently involved in the design and development of multi-protocol data acquisition unit. She is also working towards enhancing R&D industry collaboration and is mainly focusing on the proliferation of Vega processors and systems within India. Welcome, Dr. Neetha, for taking out time and traveling to Hyderabad to attend our conference.
Distinguished delegates from industry, academia, participants present here, a very warm good morning to all of you. First of all, let me thank the organizing committee for giving me the opportunity to present in this very prestigious platform, the 36th International Conference on VLSI Design and the 22nd International Conference for Embedded System Design. So, as we have heard from our Honorable Minister, Sri Rajiv Chandrasekhar ji, in the inaugural session, I will be mentioning about the major activities undergoing at CDAC towards the development of Vega microprocessors, Digital India RISC-V microprocessors towards Atmanirbhar Bharat. So first of all, I'll give you a brief introduction to CDAC. CDAC is a premier R&D organization which comes under the Ministry of Electronics and Information Technology, MIT, and it carries out R&D activities in IT, electronics, and associated areas. It has got centers in almost all the major cities, in the metro cities. We have 12 centers across India. And talking about the history of CDAC, one of our founding members, Dr. Vijay Bhatkar, he is an eminent computer scientist. He is also known as the architect of national initiative of supercomputing facility. In 1988, India was denied to import supercomputers to India. So the then government, thought of starting up a facility to develop our own supercomputers, and that was how CDAC was constituted. And from there, we have got a great legacy of 35 plus years of experience in R&D in the supercomputing field that contributes to the major thrust areas of CDAC. The first one is the high performance supercomputing. You know where India stands in the field of supercomputers. We have a series of supercomputers, Param series of supercomputers, and the latest Param computer has a compute capability of 3.3 petaflops. Then we are also there in the health informatics. You might have heard about the software eSanjeevani. Everyone might have used it during the pandemic. It was also developed by CDAC. And the other area, core area from where we come is the VLSI and Embedded System. We have products in professional electronics, expertise there. We are also pioneers in cybersecurity. We have a portfolio of tools, hardware and software tools in cybersecurity. We provide training to the defense and police personnel. We have a cybersecurity lab set up at Technopark CDAC Trivandrum. And we have various software technologies. So this is the history of CDAC, the expertise in CDAC. Moving on, we come from the hardware design group, the core area of a group in CDAC Trivandrum. And the main focus of our group, the main activity which we are currently undertaking is the microprocessor development program. We have the capability to develop a microprocessor from scratch. We have the tools, infrastructure, the expertise, manpower. We have the facility to develop, we design a microcontroller, we verify it. We have done the HICC implementation. We have taped it out. We have a silicon in hand. We also provide the full infrastructure, hardware and software infrastructure ecosystem for implementation of microprocessors. The other areas are, we are experts in ASIC design. 10 years back, we have developed an ASIC called NADA ASIC, which has gone into our hearing aids. And we have sold around 1 lakh pieces of hearing aids through our technology partner, Keltron. And we are also experts in FPGA implementation. We have FPGA-based development boards, which we are providing to the academic and industry for product development. We have also developed several ATs for space applications to they automatically test their checkouts. A small team is also working on analog and mixed signal IC design. We have the mixed signal Sigma Delta ADC 16-bit differential ADC. We have a PLL ASIC. We are also experts in high-speed PCB design. We have several embedded system products. We develop products end-to-end. Even we are into the mechanical design. We have a facility for high precision assembly and testing. Not only we develop the products, we deploy it, we take it to the end, give it to the customer, make it available in the market, transfer the technology. We have end-to-end solutions in all these fields. So moving on to the Digital India RISC-V program. It is one of the concrete steps to realize the mission of Government of India, Atmanirbhar Bharat. The MIT launched this Digital India RISC-V microprocessor program to enable the creation of microprocessors for the future in India, for the world, and to achieve industry-grade silicon. So this program will enable us make India not only a RISC-V talent hub, but also a supplier of RISC-V SoCs for It can be used for various applications, servers, mobile devices, automotive, IoT, microcontrollers across the globe. Now, why do we need a Digital India RISC-V program? Can you think of a phase in your daily life where a microcontroller or a microprocessor is not involved? It is there in all your daily life appliances, public utilities. It is there in various communication devices. Moving on to the national importance, it is there in the strategic field. Everywhere it is there. What will happen if one fine day they say that we won't give you any microcontrollers or microprocessors? All the controllers or microprocessors we are procuring it from outside. What will be the fate of India if one day we stop receiving it? So with that view, with that goal in mind, India government launched this Digital India RISC-V program because it is an essential component for India's ascent to technological supremacy. So to have a control over the manufacturing process, to control over the change, India government launched this program. The goal of this program, mission goal, is to develop a RISC-V architecture-based indigenous microcontrollers. We have dual-core, quad-core processors, and to develop reusable IP cores, which goes into the microcontrollers, to set up a resource center for microprocessor and IP core development, to develop ecosystem, board support packages, drivers, IDE, etc. And in the end, finally fabricate a 2 gigahertz quad-core SoC and product demonstrators. So India can become self-reliant in microprocessor development using indigenous designs, advanced technologies and components with requisite hardware-software products. That is the goal of this program. So what is CDAC doing in this program? We have developed a series of microprocessors under the name Vega processors. CDAC has successfully developed Vega series of microprocessors and related IPs. We are providing the complete ecosystem to enable fully indigenous product development that meets various requirements in the strategic and industrial commercial sectors. These high-performance processors are based on the open source RISC-V architecture. India is also a member of the RISC-V Foundation, so we are aware of the current activities going on in this RISC-V Foundation. Coming to our Vega processors, we are offering 5 variants of our Vega processors. The first variant will be a 32-bit single-core, 3-stage pipeline in-order processor. The second one is a 64-bit 6-stage pipeline in-order processors. All the other 3 variants are out-of-order superscalar processors, single-core, dual-core, and quad-core variants, 64-bit. The first variant, we have a silicon in hand. We have named it as Tejas 32 SoC, and it has been tested for a CPU performance of up to 125 megahertz. We have set up a stall there in the exhibit area. You can see the IC, silicon IC there. The block diagram, it is a single-core SoC. It has got other peripherals like UART, I2C, PWM, GPIOs, SPI, timers, etc. So these are the key features. We have got an inbuilt RAM of 256 KB. There are 3 numbers of UART, 4 SPIs, 3 timers, 8 PWMs, 3 I2C interfaces, 32 numbers of GPIOs. It operates on a core voltage of 1.2 volt and I/O voltage of 3.3. Frequency, it has a performance of we have tested it up to 125 megahertz. And it can be used for all embedded class applications. For example, like smart meters, remote sensors, wearable devices, toy and electronic education equipments, all the legacy 8x16 embedded applications, and many more. You can think of any embedded application our processor will support. So this is India's first microcontroller SoC, and it has been successfully fabricated. And the 64-bit variants, we have taped out 1 variant at SCL Chandigarh. That product will be a truly indigenous product fabricated in India. The chip which we have in hand was fabricated at Siltra, Malaysia, 130 nanometer technology. The 64-bit variant, which will be fabricated at Chandigarh, is the 180 nanometer technology. Then we have the 64-bit dual-core and quad-core variants, Dhanush 64 and Dhanush 64 Plus, which are scheduled to be coming up in the coming years. Based on this Tejas 32 SoC, we have developed hardware development platforms also. We have 3 form factors available with us. The first one is the Aries development platform. It has got an SPI flash of 2 MB, all the other peripherals. Apart from that, we are offering an onboard ADC also, which has got 4-channel inputs. And the supply voltage for the board is 7 to 12 watt, and it operates at a frequency of 100 megahertz. The other development platform is the Aries Micro development platform. And the only difference compared to the previous one is that the supply voltage is, it is a bus-powered model, and it also supports a supply voltage of 5 to 6 volt. The other development platform is the Aries IoT development platform, which has got an onboard Wi-Fi module also integrated onto the board. And it has got other IoT sensors like digital proximity sensor, ambient light sensor, gesture sensor, accelerometer, 6-axis digital accelerometer, gyroscope, gas, humidity, temperature sensors, and other peripherals like Wi-Fi, push button, LED, etc. So the processors can be used for various applications, like as I already mentioned, for smart metering, internet over everything, reference boards, multimedia processing, AR, VR, then low power embedded application, GNSS, etc. So what are the key benefits of this program? It has got very important strategic advantage. India will own the IP for high-end microprocessors, and this mission project is dedicated for the total implementation of interaction with academy and in industry. We will be giving out silicon-based deliverables directly deployable in products, and comprehensive hardware and software ecosystem for microprocessor-based design, product design. And through this, we can achieve self-reliance with clear financial and strategic advantages. Many of the countries have been working in this field for many decades. We have just started. So this will be pave the way to Indian designed and manufactured electronic chips, leading to a success in the Make in India initiative, hence Atmanirbhar Bharat. And we are also providing opportunities to develop custom SoC, development and deployment, co-development of electronic products based on Vega processors. We have initiated talks with industry partners, academic institutions. We are providing the boards. We are collaborating with them. We have signed MOUs, EOIs, and we also provide affordable proven IPs. All the IPs which go into the SoCs are indigenously developed. And we provide a faster product to market through dedicated support and comprehensive ecosystem. We have a website called vegaprocessors.in. All the details of the processors, the ecosystem which we offer, the IDs, the libraries, everything is available. We provide the full ecosystem with the Linux drivers, libraries, IDs, everything is there. We have a team dedicatedly working on the development of IDs, full ecosystem for the processors. We have a YouTube channel called Vega Processors. You can see multiple demos which we have implemented using our Vega processors just to showcase the capability of our processors. You can visit us there. We have a blog also where we frequently update the ongoing activities going on in the development stages. These are some of the useful links. We have a website, YouTube channel. We have a discussion forum, groups.io. We have a blog. Then we have a LinkedIn account. Now I'll just play a video on short video, 2-minute video. Thank you. That's all from Pines.
Thank you for your time and amazing presentation. Very informative. Now I would request Dr. Usha Mehta, Professor and Head of Department of Electronics and Communication at Nirma University, to honor our guest. Moving on to our last keynote, last but not the least, is by Nagabharat Dhaka, co-founder of Skyroot Aerospace on embedded systems in mission-critical applications. Bharat heads the operations of Skyroot Aerospace, overviews the avionics and GNC development at Skyroot. During his tenure at ISRO, he worked as a flight computer engineer at VSSC and has built hardware and firmware for multiple key onboard computer modules that implement the launch vehicle's functions. Bharat has also worked in the semiconductor industries with expertise in FPGAs used in space and defense applications. The stage is all yours, Bharat.
Hi everyone, I'm Bharat. I'm one of the co-founders of Skyroot Aerospace. We are a Hyderabad-based space launch startup. So today my presentation will be short. I'll be giving a brief intro about what we do at Skyroot and our recent launch we have done. And I'll be briefly explaining the key subsystems in a launch vehicle and where do embedded systems fit in for which functions in a launch vehicle application. And I'll be throwing some light on few of the key developmental approach changes that have been happening in this sector over the past few years. And I'll end with that. So just to introduce about Skyroot, we are one of the leading space tech startups in the country. We are on a mission to make a space launch affordable, on-demand, and reliable for the satellite operators around the world. And just to give you more pointers, we are the first private company. On November 18th, 2022, we became the first private company to launch a rocket to space, not only in India, but in entire South Asia. We are the first space tech startup. We are the first space tech startup to sign an MOU with ISRO to be able to utilize their test facilities and launch facilities for our future operations. And we also thankful for the Union government who bestowed two national startup awards, one from the Department of Science and Technology and other from the DPIIT. We are currently a team of 200 plus people collectively working towards a singular mission of our upcoming milestone, which is an orbital launch to space where we put a satellite around the Earth by the end of 2023 is the target. just to throw some light on our launch that happened on November 18th, the rocket is called Vikram S, named after Dr. Vikram Sarabhai, and S stands for suborbital. So this is a single-stage suborbital launch vehicle which we launched to space. Systems and telemetry, telecommand tracking systems generally contain most of the embedded systems that are onboard avionics that go into a launch vehicle. So just to throw more light on what is the purpose of and few key modules that go into the guidance, navigation, and control application. One is the one of the most key module is the mission computer, which is can be considered as the brain of the launch vehicle, which implements all the sequencing activity, the guidance algorithms, the navigation algorithms, which enables the launch vehicle to know its position. Because launch vehicles cannot solely rely on a GNSS system to know its position. It will have something called inertial measurement unit, which has the gyroscopes and accelerometers, through which a navigation algorithm can compute its own position from the liftoff to the orbit, even when there is a GPS blackout. And mission computer essentially computes all this stuff and informs other subsystems to act upon it, like the control electronics, which controls the actuation systems, or the thrusters, which control the pitch or roll of the launch vehicle. So all the commands of when to turn, when to steer the nozzle, by how much to steer the nozzle so that we can steer the vehicle in one direction. All these commands are generated in mission computer and transmitted to the control electronics so that they can execute the function. And command execution systems are the ones that generally execute the commands like stage separation, stage ignition, because most of the launch vehicles have to be highly mass efficient, and they are implemented in a multi-stage system. So as you mostly be aware, anyone who has seen a rocket launch will be aware that you must have seen the stage separation activities and the second stage getting ignited. So all these sequencing of activities will be executed by command execution systems, which generally contain high current relays and a microcontroller that receives the command from the mission computer to execute its stuff. So coming to telemetry, TTC systems, what we call TTC systems, these are the systems that, as I mentioned, helps the ground stations know the performance of the launch vehicle. So a launch vehicle is actually a totally autonomous system where from liftoff to orbital insertion, it acts on its own. Actually, it doesn't take any command or any insight from the ground station. It self-computes its position and it knows how to steer itself. But telemetry and data acquisition systems are needed basically to know the health of the system in real time, because any launch vehicle is heavily instrumented with all kinds of sensors like to measure the strain, pressure, temperature, vibration, acceleration, all this stuff, so that we can assess how well the vehicle went, and if any malfunction happens, either in a critical subsystem or in non-critical subsystem, we will know what went wrong in a mission so that we can correct it in the next mission. So all this data is transmitted to the ground station through a telemetry link, generally operates in the S-band region, 2.2 to 2.3 gigahertz spot frequencies. And other application is the telecommand. As I mentioned, launch vehicles are totally autonomous, but the only use case of telecommand, which is essentially a command from ground to launch vehicle, is to destroy the launch vehicle. Only in cases when launch vehicle goes haywire by some reason and it's not following the correct path, that's the only instance a command will be sent from ground to a launch vehicle. For no other purpose, any communication will happen from ground station to a launch vehicle. And tracking systems are essentially used to track the vehicle from the ground. We need an active transponder on the vehicle, which can receive the signal and transmit back, so that even at a far ranges, even at 1,000 kilometer, 1,500 kilometer range from Earth, a ground station can track the vehicle because of this active transponder on board. So I'll just come to throwing some light on what are the key changes or evolution in the developmental approach that has been happening over the past decade and maybe in the future also. So increased reliance in software. When I say previously, most of the things were implemented in hardware with discrete components. As the trend has been following, most of the stuff now for telemetry systems, software-defined radios are being used. Even we are using them. So everything but for the final amplification and mixing happens on a single chip, either in the software or on the integrated IC itself. And increased use of commercial COTS components, like launch vehicles traditionally used to, any aerospace application traditionally used to use the mill grade components and space grade components. And cost consciousness, as more and more commercial applications have come over the past decade, and cost consciousness will obviously be a factor, and to how to achieve the same reliability and at a lower cost is thanks to automation of industries and automotive sector being one of the other critical systems. Industrial grade components also have been proven worthy to be used in aerospace applications instead of mill grade components. So this way, using of COTS, industrial grade components, and proving the module level or subsystem level for the environmental qualification levels of the launch vehicle has been the trend so far, which reduces the cost of the development and also cost of the production of these components, modules in general. And increased use of model-based design, like model-based design approach has been a trend past decade, and it will grow even larger. So the need for redoing stuff, once you model a simulation, a plant model, an algorithm, everything is modeled in, say, in a MATLAB Simulink. The need for rewriting those algorithms in C, CPP, or that need has been reduced due to real-time simulation setups and this HDL coder techniques that are being used by many people. So what this enables is to reduces the cycle time. We can iterate quicker, we can change at a system or algorithm level, can easily percolate down to the firmware level in a quicker way. So model-based design development helps in rapid iteration cycles that enables any developer to go to the market sooner. And increased use of agile development methodologies. So when most of you must be familiar with the standard waterfall approach, where we formulate the requirements of a system and then go to development, and that has been like broken quite a while for quite a while. The agile development methodology is as like along with the requirements that the prototype development happens and the firmware code happens. By the time the final requirements are frozen, we generally have a pseudo like close to semi-functional, quasi fully functional code also will be set up, firmware will be set up, a prototype board will be already ready. So this way, an agile development methodology, which is generally prevalent in other sectors, which was not so in aerospace sector, has become a norm even in aerospace sector and even in the launch vehicle development, which reduces the time of development significantly. As I mentioned, increased use of simulation and testing has to become a norm. Increased use of simulation and testing will only help in making the first flight as successful as possible. As I come to the next slide, because always fly as you test and test as you fly is the golden saying in aerospace application, and that's not very easy when it comes to a launch vehicle, because the only time when the full system will be tested in any launch vehicle is the final flight. Everything else, everything before that has to be emulated for the scenarios, and each subsystems can be separately tested. But the full system can only be tested once, and it's very expensive systems, and hence the mission criticality because of the cost criticality of the experiment. And what I'll just throw some light, I'll end with this basically, or throw some light on what are the key challenges, what makes, not just technically, but what makes any such attempt capital intensive is not just the rocket being costly, it is also the developmental effort also is capital intensive, because to emulate the scenarios, to emulate the environments, like lot of environmental test equipment has to be bought, like the vibration test beds, acceleration test beds, EMI, EMC, and the thermal chambers will need to be bought to subject the modules, onboard avionics modules to these extreme environments on ground. And the hardware in-loop simulations, which essentially emulate the flight behavior, also needs an expensive equipments like 3-axis rate tables, which essentially keeps this initial measurement unit on itself and rotates and emulates an environment of flight for the sensor, so that we can test the mission computer working well in the real environment, close to real environment, and we can test many cases with the perturbations. So these kind of hardware in loop simulation setups also are extremely capital intensive, and hence in our developmental effort, it becomes very much critical when it is capital intensive, and the government support is where it becomes crucial. And thanks to government reforms in the 2020, and ISRO and other government agencies helping us out, we were able to utilize this capital intensive developmental testing infrastructure available in the public sector for our developmental activities, which is helping us to fast pace our development and achieve more with less capital. And last but not the least, FAPC, like what is the size, weight, power of cost optimization is a standard need in across all applications, and that same thing applies to launch vehicle applications also. And every efforts are being made in this domain to reduce the mass, because if we reduce the mass and cost, we'll be able to make more effective launch vehicles. If avionics systems is of a lesser mass and lesser cost, the entire cost and mass of the vehicle will reduce. Thereby, the payload carrying capacity of the launch vehicle will increase, and the per kg cost we can charge to a satellite customer can be reduced to be cost competitive. So that's pretty much it, and I thank the organizers for giving Skyroot the opportunity to share our purpose and the work we do on this platform. And I request everyone to wish us all the best for our upcoming milestone of orbital launch in this year. Thank you very much.
Thank you, Bharat. Thank you so much. You are a motivation to many people, young and old. We wish you all the best for your future endeavors. Now, I would request Mrs. Padmini Gopalakrishnan, Senior Director, AMD, to honor our guest. Next, we move on to a panel discussion on evolution of Indian EDA marketplace. Leading the panel is Mr. Sumit Goswami, Senior Director at Qualcomm. Sumitji has 2 decades of experience in semiconductor industry and is known for building high-performance teams and delivering cutting-edge SoCs. He's currently responsible for driving tools, flows, methodology, and physical design execution in Qualcomm. He played various leadership roles as part of Qualcomm India engineering team, which includes high-performance CPU, GPU, multimedia design, customer engineering, and RF PMIC SoCs. He's a senior IEEE member and published 50+ papers across various conferences and chaired several prestigious conferences. During his career, he worked on all aspects of SoC design, starting transistor level design to system design, and taped out 100+ SoCs powering mobile, automotive, server, laptop, graphics, and IoT platforms. The other panelists are Dr. Shivananda Koteshwar, Group Director, Synopsys, Mr. Sridhar Rangarajan, Group Director, Cadence, Mr. Dipanjay Gope, CEO, Simyog Technologies, Mr. Suchir Dikshit, VP and Country Manager, Siemens EDA, and Mr. Vinayakam Subramanian, Director, ANSYS. I would like to once again thank all the audience for being patient listeners. I hope you have had enough key takeaways. This is the last panel between you and your lunch.
Thank you for the nice introduction. So the last 2 days, we have gone through very interesting program schedule where we talked about semiconductor industry at large. We looked at various numbers, looked at various charts and graphs. We understood how the industry is moving. So one key aspect of all the design industry is that the automation running behind. So the EDA as an industry is kind of fueling the growth of the entire semiconductor. So in this panel, we'll be just zooming into that and see that how it is helping. And some of the EDA companies are here for long. So if you look at it, it is kind of this foil is kind of a summary that what we learned so far in the last few days. Now, what are the key growth driver of our semiconductor industry at large, right? So one is the high performance computing. A lot of biggies have talked about it. Data center is the next area of growth. Many people talked about it. Now, if you look at the essential technological component behind that, other than all the development infrastructure, money, and all those part apart, it is the more performance, what we need. More performance at the constant power density and constant thermal. The reason is that the data center size is same. How to squeeze in more performance on the same data center is your target. So that becomes a technical challenge for the industry. Second one is the mobile computing. So when we say mobile computing means a battery powered device, which is giving the right set of performance for the device, right? So whenever today most of you are carrying the mobile on your phone, that can do a lot of things which we never thought of before. Now, if you again translate it to a technology component of it, it is the more power performance at the constant energy. So that energy piece becomes critical on it. Third is the autonomous sensing and the computing, which is the IoT part of it. It is targeted to reduce the leakage and the variability. And the fourth one is, of course, the automobile part of it. A lot of automotive discussion happened, and we know this is the talk of the town right now. And in automotive side, the reliable computing, it should not fail. The feed rate should go down. DPPM should be absolutely at the best and all those things. So if you kind of characterize the industry growth, these are the fundamental technology growth out there, which is kind of driving this entire market. And now, if we know that these are the things we need to drive, that EDA tools are the key ingredient, because we are doing the manual design in past. So now if you further summarize it into a few bullets, that what are the key top targets? And PPAST is the kind of the key now. PPA was always a technical term. So if you summarize performance year over year or generation over generation, I need greater than 10% performance. If you look at the power side of it, power efficiency should improve by 20%. Area should be 30% of less. We all talked about Moore's law, multiple times we talked about Moore's law. Schedule has to be constant because time to market is key. And then the thermal, more and more becoming important because the energy it's required and the power density we are introducing is immense. So these become further technical challenges for the EDA industry. So they further break it down into the areas like logic technologies, verification techniques, performance boosters, I mean in the logic side, then PPA scaling, 3D modeling, this is the new techniques all the companies are trying to do right now. And of course, machine learning, this is the next big buzzword, everybody trying to map, and then EDA industry is also running towards it, saying that what ML can solve, what are the problems they can solve. Emulation and the system predictivity, right? So the system level is becoming a lot more important. So if you look at the EDA as a market, we all talked about that huge size of 500 billion plus semiconductor market. If you look at the zoom into the EDA market, which is like 12 billion across the globe, and at the closely about 7% plus rate, it is growing, and we hope that by 2026, it will be reaching in 18 billion plus, and the largest consumers of the EDA growth is in the APAC side. So these are the few backgrounds. So what we are going to discuss in this panel is the followings. So we have the eminent panelists from all the EDA biggies, all the big players, and also we have a representation from the startup ecosystem as well as academia. So what we thought that we'll be discussing in this, that what are the challenges, opportunities we have in Indian EDA marketplace. India, I remember almost more than 2 decades back, I was in one of the such conference, Zoom was full. I was showing some layout objects, and I got a question that, hey, your horizontal metal 2 and vertical metal 1, what if they shorts? Just looking at the layout. And I just compelled to ask the question, okay, how many of you are seeing physical design for the first time? In the entire crowd, I saw only 2 hands was up. From that days to today, there is a phenomenal change, right? So now it is all over. People understand the EDA technologies, people understand semiconductor design. So what we are going to talk, in this entire panel is that from the MNCs, I would like to understand from that what is the contribution you guys are making here. When I say contribution, I more want to zoom into the India operations, what you are focused on. What is the support network? Because you have all the semiconductor houses around. What kind of support network you are extending here? Because of you, the big semiconductor houses are successful today. Third is that the research pipeline in the fundamental space. What are the future? To build the future, you need to invest on the fundamental research today. On the EDA side, how is the landscape? And the emerging areas in the EDA, which may not be a reality today. Nobody thought about 3D IC maybe 10, 15 years back, but now we are super serious about it. What else you are looking at it? And from the startup side, would like to know from Dipanjan that what are the funding opportunities, business opportunities, and the survival opportunities. If we predominantly look at the EDA industry, it is governed by all the big companies. So today, I want to hear from the startup point of view also, starting in India, creating an EDA company, taking it out to the bigger market, how does it feel? What is your game plan? So we have eminent panelists whom I know personally for many, many years. Even morning sync up also, when we got together, it was like friends are coming together and chatting, rather than formally we are getting introduced to each other. Let me introduce one by one, and one of them, the first speaker is going to be Dr. Shivanand Koteshwar. We popularly call him Shivu. He is currently with Synopsys India as the EDA group site leader and the R&D head responsible for releases and technology engagement from this region and accountable for the digital implementation worldwide. Shivu is a versatile technology leader with 27 years of record in challenging tapeouts, design team setup, and strategic operation management. Before Synopsys, Shivu was the site head and general manager and instrumental in setting up the MediaTek India operations. Shivu is the trustee in the Belaku and the Orinco Academy. Shivu is an adjunct professor in Dayanand Sagar University, ISBR. Shivu also serves as a BOS member for Mount Carmel, BMS, BNMIT, MSRIT College. He is a founding director of the Amartya Academy School, a professor at PES University, and an advisory board member for MS Ramaiah University. So from the description, you can figure it out. He has a wealth of experience to talk about how the EDA, and I know Shivu for many, many years. So Shivu, what's your view, and what Synopsys playing the role in India ecosystem on these topics?
So first of all, I really want to congratulate the team for putting this event together. I think it's one of the best I've seen. I was just walking through the booths just before this, and out of the 5 questions somebody asked me in the booth, I could not answer 2 of them. Very technical, very specific questions. I'm very, very happy to hear that. Usually in the booths, you get people walking in and just asking, what do you guys do? It was earlier, but today they're asking very specific technical questions. The quality of interactions is very, very good. Thank you very much for doing that. Getting back to the questions you put together here, let me try to summarize our journey so far. We've been here more than 25 years in India. Bangalore was the initial center, but today we are spread across India. We were 67 people when I joined Synopsys, and today we are 3,500 plus people. We have 4 primary business groups within the company. One is focusing mainly on the EDA tools, one is on the IPs, one is on the software integrity team, and one is on the hardware side. And we have a good presence of all 4 of them right now in India. And we have grown very organically. There has been quite a lot of acquisitions in the last 20 years in Synopsys. And we've integrated these teams very effectively in India. And we continue to do these acquisitions. Whenever we have done the acquisitions, we've got the right leaders, be a part of Synopsys and continue in the journey of research what they were working on. So a very organic growth the company have had. And today with the headcount we have, I think we are still maintaining that 30% of the headquarters headcount. And that's what we've been running with. And as I told you, each of these business groups have extended their teams in India and grown from a small team to where we are right now. So we've seen a very good cross-pollination between the US teams, the Europe teams, the other Asia-Pac teams, and the India team. So we've grown. One is the growth which has happened due to the development and due to the people we had in the company. The second growth was primarily driven by the customers. Whenever our customers grew in the region, whether it was Qualcomm, Intel, MediaTek, AMD, any of our partners, when they grew in India, we grew with them. The problem statements we had was primarily the problem statement of the customers. And most of the product specs happen through the high-value problems from the customers. So more and more we hear from the customers, more and more directions we get as a company on working on the next technology node for the features for the products. And I think that has been the success factor for the company also. Making sure that our ears are to the ground to make sure that we hear from the customers and grow with them. The most challenging things we do is primarily the most challenging thing the customers do. We want each and every customer of ours be successful. I didn't mention many of the small startups we work with, nothing against any of them. I just want to mention that most of the EDA companies here are primarily being driven by the customer problems which they are facing right now. We are not only looking at the problem statements of today, we are also looking at the problem statements which might hit us 5 years down the line. And we have put together a team working on those areas also. So I think that's how we've been working with the ecosystem right now. Coming back to the research pipeline in Indian Academy, like most of the other companies, we have worked primarily with most of the IITs to start with, but now we've extended to other private universities also. Primarily, it is driven by the professor in that particular university. It's not just the tier 1 logo, which attracts a company to work with the university. It's actually a professor from that university who reaches out to Synopsys and says, hey, we need help in these areas, or can you help us with the problem statements? There are universities, private universities we are working with right now, wherein we are just talking about the problem statements for the PhD students over there. Right? That itself is a good input for them because that's some of the gaps they are seeing. Many universities are working on fundamental research, but when it comes to applied research, they need help in identifying the problem statements. Most of the universities are working very heavily on the material sciences, but they need help in the core EDA. So they reach out to us, and we're working with many of the professors right now. Some of the deeper relationship we had with IIT Kharagpur and IIT Kanpur and IIT Mumbai also, where we've worked with some sponsored research areas. We worked with professors in sponsoring some PhD students also in some of the areas. I think that's going really well. In future, what we are trying to do is we have built a fantastic relationship outside India also in some of the universities. Now we are trying to connect those universities with Indian universities so that the university student, for example, if somebody is doing a PhD here, he gets an opportunity in both the spaces to do a double PhD, for example. So we are looking at expanding those support system also, because sometimes it's not just the tools which is required for research areas. It is the entire infrastructure and the ecosystem which will be required. And this ecosystem is already built in other universities outside India. So connecting this to universities also is a big role we can play as a EDA company. So we are working on that areas also. A lot of times people think that universities especially, they think we need to reach out to the company for the tools. Tools is just one of them, right? We have IPs, we have the entire support system, we have the connect with the ecosystem. So we would be actually a single point of contact for many other areas which you guys are working on. This is a good forum where I can ask each and every one of you. It would be great actually if you can connect us with all the new IITs which is being formed. I know they need a lot of help. if there is an opportunity where we can connect, I think VLSI conference can be a good forum where we can actually connect to the newer NITs and IITs being formed. If they need any help in any of these areas, we definitely would like to partner with them and actually take the relationship forward. I would answer the emerging areas later after we complete it.
Sure.
Thank you.
Sure. Thank you, Shivu, and it's great to know and the support and help synopsis and you are personally providing. So this is very important, right? We talked about skilling and the skill development multiple times, and that's where the experience part of the skill development comes from some of these measures. So great to know that, and this is a great platform to even network with some of these stalwarts in the EDA industry. If you love algorithm, maybe you want to catch all these panelists outside. Moving on to our next panelist, Ruchir Dixit. So Ruchir is currently the Vice President and the Country Manager of Siemens EDA. Ruchir has over 20 years of experience in the semiconductor industry, having executed at multiple levels of responsibility in design and development of ASICs, FPGAs, and the PCB boards. In all the years, Ruchir has either directly worked on or worked with customers over 200 IC tape-outs. After spending close to 10 years in the IC development roles, Ruchir moved into the EDA and applications. In this role, Ruchir had held various leadership roles. In these roles, Ruchir has worked on the many customers worldwide and helped them to define the problem and then work to create the solutions. Ruchir spent 11 years in Mentor, US, and then moved into India in 2005 to start building the customer-facing organization of Mentor Graphics in India. Currently, Ruchir is the treasurer and the executive council member of IESA, and also the chairperson of the Bangalore chapter of IESA. Ruchir is an intrinsic member for all the key decision-making bodies, both in the national and the international levels. Over to you, Ruchir, and would like to hear your perspective on this particular subject.
Thank you so much, Sumit. It's such a privilege and pleasure to have the opportunity to talk to you and share the stage with such accomplished people. It's a very hard task to follow the rock star of semiconductor, Shivu. You are. It's a hard act to follow. So before I start, I want to dispel one myth. EDA actually are not after each other's blood at all times. We can actually share the stage, be friendly to each other, and work towards sharing our views and helping the community. So if you have those misconceptions, please take them out. Talking about our history when we started, so I'm very pleased to share with you something that you may not know. When we decided to put the first stake in the ground in India, we chose Mana Hyderabad, the only EDA company who started in Hyderabad. From there, now we have reached a stage, as Shivu said, we have people in several cities in India. And we have grown just like all the semi companies in India and every other company in India grew. Started with work that came to India for cost arbitrage, but at this point, we have evolved to a stage where we define, design, and drive product lines out of India. And that's a phenomenal success, and that has happened something similar to what Shivu just talked about. Our customers told us what we should be working on, and we worked on that, and that partnership helped us evolve, and that partnership helped our customers solve the problems that Sumit had just outlined in one of his slides. So when I look back, and when I think of what EDA is, it reminds me of a quote that one of our leaders in the industry had said. He always says that EDA is where electronics begins. And that short phrase is such a profound phrase because all the things that we do today, all the electronics that we realize today, there is no way any of it can be done without EDA. And if EDA does not keep up, electronics doesn't happen. So I'm proud to be a part of this group here, which enables all of the transformations that we have brought to the world through the work that we have done. As far as research and collaborating with research in India is concerned, I don't think we are any different from what Shivu talked about and my fellow panelists will talk about. Right? We all look for people in the ecosystem who are willing to try out new ideas, who are willing to go after problems that our engineers in the industry have not encountered yet, because that's where research is, like looking 3 years out, looking 5 years out, looking 10 years out, because research takes time, and a product coming out of research will take longer time. So we focus with all the colleges. As Shivu said, most of it is professor-driven. A professor who is interested to work on a problem with us, we work out with them. I just want to talk about something that you said, Sumit, and the challenges that we face today. 10% faster, 20% smaller, 30% less heat. When I started my career in '96, the problem statement was exactly the same. Everybody wanted the device cheaper, faster, better, more reliable. So what has changed? Fundamentally, the problem definition has not changed. And as Shivu deferred to the last part of the question, emerging areas in EDA, I'm going to stay at a level which is higher than talking about I can give you something in 10% less time. Or I will deploy ML technologies to solve this problem. So we'll come to that, but what we are focused on is at a level where we can bring some transformational change in how we design, how we realize, and how we utilize.
Thank you, Ruchi. So with that, we'll move on to our next panelist, Sridhar Rangarajan from Cadence. So Sridhar is a group director with Cadence Design System, having around 20 plus years of experience in reading and architecting EDA tools and solutions. In his current role, he is responsible for driving and delivering optimized EDA solutions using AI to improve design efficiency and the faster design closure. Before joining Cadence, he held various leadership positions in Siemens EDA, IBM, Synopsys, and Sun Microsystems. Sridhar has around 15 patents and several publications in conferences and journals. His research interests include CAD for VLSI in physical design, combinatorial optimization, big data analytics, machine learning, and graph algorithms. So Sridhar, Ruchi, and Shivu talked about how they evolved as a company. I want to little bit change gear and ask you about the AI, since this is your interest. We have been hearing about the machine learning AI in all various fields. Right now, it's the buzzword, as we said in the beginning, that every industry talking. What's the role of AI in the EDA industry? And since you are doing the fundamental research, is our algorithms AI friendly? On the AI space, if I need to innovate, what are the areas we need to put more focus on? So we wanted to know your perspective. So I would request you, if you bring the AI perspective on the topics rather than setting up the company history, that will be great.
Thanks, Sumit. Thanks for the introduction. I'd like to thank the VLSI organizing committee for giving me the opportunity to take part in this discussion. Before going to the AI part, I just want to say the EDA in India has grown tremendously over the last 20 years, right? For example, as Ruchi talked about and Shivu talked about, there are a big design ecosystem in India. Obviously, the EDA companies developed the support system along with that, and then later on move into the R&D part of it. If you take for Cadence, for example, the EDA India site is the biggest R&D center outside US, kind of, right? So we are around 2,500 plus people working on all the aspects of the EDA, R&D, application engineering, support, and IP development, kind of, right? So if you look at EDA, it's nothing but computational software, right? It involves computers and mathematics mainly, right? And then if you look at India, we have a tremendous talent. The knowledge base is there. So automatically you see EDA companies coming and establishing the R&D center, and then we have the talent pool available for that, right? So apart from coming to the AI part of it, if you look at it, there are places in EDA where AI has been applied for a while, right? Especially in the DRC space and some of the analysis space and all those things. But the EDA problem, if you look at it, these are complex problems, especially in the place and route area, right? So most of these things are not able to learn using the gradient descent-based method approach, right? So that's why if you look at it, in the placement and routing, the gradient descent approach kind of never panned out much. But having said that, with this reinforcement learning, and then some of these new techniques coming into the AI, especially in terms of RL and then attention networks, those kind of things, there is a tremendous opportunity there. You might have seen some papers on this area, especially RL-based placement and all those things. So there is a tremendous opportunity in the AI space. I see which can be applied in the EDA areas. I see the next decade is going to be mainly in this EDA space is going to grow much in the ML side, right? The traditional algorithms is going to stay because there are efficient algorithms which is going to stay there. But there all can be definitely areas where the new techniques can be applied and then improved upon, right?
Okay. Yeah. Thank you, Sridhar. Moving on to our next panel is Vinayakam Subramanian from ANSYS. So Vinayakam is a subject matter expert in the power integrity, signal integrity, and the reliability simulations over 15 years. He loved to solve multi-physics challenges that require combining technologies across various domains. He joined ANSYS in 2006, has taken several diverse roles across the field application and the product engineering, and currently working as the Director of Application Engineering based out of India. So Vinayakam want to know about this aspect of the multi-physics challenges. This was not the term which was popular maybe, let's say 20 years back, but nowadays it is becoming very, very relevant given that the diverse applications are going into the market. So on the EDA space, how this is dominating and what's your views on the multi-physics? We would like to hear from you.
Yeah, thank you, Sumit. So I want to step back a little bit. So this is still my first job, right? I joined here as an NCG. So when Sumit said the topic of the panel is evolution of Indian EDA, that was close to my heart because my career sort of started and evolved with Indian EDA. So I joined back in 2006. At that time, we were only doing one physics, which was power integrity simulations, voltage drop simulations. It was just a handful of employees in India. Most of our team was in US at that time. So we used to, anytime we had a deep question, we had to go, okay, let's go and ask the US team, right? Now, fast forward 17 years, in 2023, today, ANSYS India semiconductor team is the largest team now for semiconductor in our global vertical. And it's not largest because we are doing more testing, more low-end stuff. It's actually because we have the product expertise that we have built over the years on all the new and emerging technologies. So when EDA and the simulation evolved, we evolved from single physics to multi-physics, which is we started with power integrity. But then we realized that it's not just power integrity. We need to look at reliability for ESD, electromigration, et cetera. We expanded into that. Then ANSYS acquired Apache, and they had thermal and mechanical simulations. So we realized that power has impact to thermal, right? They are connected together. Power is solved using our KCL, KVL, but thermal is solved using computational fluid dynamics, right? Different branches of physics, but we need to connect them together, and that's how we sort of evolved into the multi-physics simulation workflow. This happened actually 10 years back, but it's good for us now because the 3D IC mega trend is really showing the need for the multi-physics simulation. So with 3D ICs, chips are stacked very close, more and more power is getting consumed, so we need to look at the impact of power. Power is impacting thermal. Thermal is impacting the structure of the 3D IC, the stress and the warpage. So all those evolved together. And I have been privileged, blessed to be part of the core India leadership, where as and when we added these multiphysics, simulation technologies, we built the talent here. We built teams for each of those technologies here in India. That really led us to today, where today people outside India, within our company, they come to us saying, okay, for this new application that my customer is asking, how do I do this, please help. They come to India team for it. So that's been really delightful for me personally to see that evolution. And specifically, in 2015, we acquired this technology from Gear Automation called Seascape, which is big data elastic compute. Until then, people were thinking about Tickle, Perl, or just a few machines, splitting the workload into a few machines. But then this completely changed the game for us. We had to think about hundreds of machines, 200s of machines, and doing it in Python. And that entire center of excellence, we built it from ANSYS India. So now ANSYS India has a team of product specialists dedicated that champions that new architecture and elastic compute analytics. So it has been a great journey, and I hope Indian EDA continues to evolve with this momentum. Looking forward to that.
Thank you, Binakam. Thanks for your views. Now, going into our startup man here and the representation from our Indian academia on the EDA space. So Dr. Dipanjan Gop. So let me introduce Dr. Gop here. Dr. Dipanjan Gop is right now the Associate Professor in Electronic Communication Engineering in IISc Bangalore. He is also a co-founder and CEO of Simio Technologies Private Limited, a spin-off from IISc focused on EMC simulation. Dr. Gop was founding member of Nimbic, which was acquired by Mental Graphics back in 2014. Dr. Gop received his PhD and MS degrees in electrical engineering from University of Washington, Seattle, and BTech in electronics and electrical communication engineering from IIT Kharagpur. So Dr. Gop, want to hear from you that how was your journey to setting up an EDA company over here, surviving, acquiring customers, and taking the product to the market? How easy it is in India or how tough it is in India compared to your past journey on Nimbic when you did it in US?
Yeah, thank you. So, in terms of, let me talk about the opportunity first, and we'll talk about the challenges after that, right? So, in terms of EDA, what we see, and maybe it's a little bit of a biased view because of my background, is there are many new users of EDA that's coming up. Previously, it was the semiconductor companies. Now, it's the systems companies. It's coming because of like the amount of electronics and electrical in a system level. So, at Simio, for example, we saw that as an opportunity, and I think that opportunity will continue to be there. I think Sridhar talked about computational software. So what we have seen is sort of a merging between the PLM domain and the EDA domain, right, and intersecting. So apart from other things like HPC, EDA on the cloud, AI, I see in terms of an application perspective, the system is something that could drive the EDA world, right? And in terms of our, experience, it was Bangalore today, or India today is an awesome place for a startup, right? We are really pampered to an extent, right? Everybody, at least that's in the last 3-4 years. So it's been a lot of encouragement from the ecosystem you see here, From that startup coming from India, selling to the world, I don't see a problem today, right? It is not an issue. The issue in EDA, I think that more in terms of a startup, right? And that's, I think, more, same in India and USA, is the oligopolistic nature of the market. What that means is that, if you look back, right, I think you will see 3 top guys from 1980 on, and obviously, startups need VC funding, right, in order to scale high. So what the VCs come and tell us is that, you're going to be acquired someday. It may be a good news for you, but what is in it for me? Unless you become a standalone company for a big VC, it doesn't make that much of a sense, right? So in other computational domains, you see a Google, you see, you see many other startups coming up, VMware, et cetera, coming up and completely taking the top spot, and that hasn't happened, right? Because of, I think we all make point tools. You always have to start somewhere, make point tools, and the customer is looking for an entire flow, right? So that's one challenge, but I do think with a lot of these new things coming up, HPC, AI, cloud, and systems, things are going to probably change.
Thank you, Dipanjan. So with that, I think thanks for all the panelists you heard about different areas, what they are working, how do they set up. So I have some specific question now to the panelists, and it is open, one of you can sign up. The first question here is that if you look at EDA industry, sometime in 90s, synthesis technology came up. That was a breakthrough, we considered. And after that, physical design was comparatively simple than what we deal with now. Synthesis was a major breakthrough. Physical synthesis considered as the second breakthrough, when the gap between the logic synthesis and physical synthesis, physical design started diminishing. After that, sometime DFM, on and off, it's not great. HLS, still, we are talking about it. Wanted to know from you guys, what is the next big thing in EDA industry we could expect? Anybody can, maybe Shivu want to go first?
I can give a shot for that. I think two emerging areas for all of us. One is on the silicon life cycle management itself. I think SLM is a big thing for all of us. This year, we've had a wonderful start in that area, where it's becoming very, very important for us, not just help companies tape out the chip, but also ensure that the entire life cycle of this chip, we are able to monitor the health of the chip. Because again, the customers are putting these chips in automotive vehicles, where you need to make sure that even before it fails, because of aging, because of many other reasons, you get to know in advance so that you can take some precautionary actions. Second is if it is getting into a cloud in a server, when you're promising 5 nines, 99.999% of uptime, you want to make sure that you are able to meet the SLAs. So I think it's very, very important that you are able to manage this through doing this. So we are working very heavily and investing very heavily on the SLM part of it. I think that's one of the first areas I would recommend. Second one is the multi-die systems, because with the uncertainty of the, we saw the supply chain challenges last year, and I think it might continue for quite some time. So multi-foundry system also is going to become a norm moving forward, wherein you'll have the core in one fab and the peripherals in a different fab. So multi-die system has been there, but I think it has got a lot of relevance in the last 1 year, and I think we will continue to look into this. I would say, apart from the cloud and apart from all the incremental updates we do in day-to-day in our technologies, these two areas will be definitely one of the areas which we should focus on. Just on the last part, which I missed last time, on the other areas which we would look at is, see, most of us have been a tall and thin person in our technology areas. We've gone so deep looking at each product in our areas. And at the top level, at the architect level, we have looked at being a short and fat person, right? We know bits and pieces of everything. Today, customers are not really care about what each tool can do in the flow. Customers are asking, can you help me tape out this with these kind of parameters? Right? These are the requirements I have. So as long as the system, right, the set of tools can achieve these targets, customer is very happy. Where we need help from the universities, from the startups and many other areas is, if we can partner with us and help us gain expertise and come out with solutions at the system level, I think that's what we need to focus on. From the tool-specific areas, however we can push the boundaries of the physics, we've done it. Where we need help right now, where we are also investing as a company, is actually on the systemic level and trying to look at the problem from the entire system and trying to solve the problem from the whole system level. I think that's other area where we'll see a lot of momentum this year. And that's also an area where we are looking for partnership with universities and professors and even startups in that areas. We'll be more than happy. Please reach out to our sales team and the SARA team. SARA team is the Synopsys Academic Research Alliance system, where they work very, very closely with the professors on the research areas. These two teams will be more than happy to partner and take it forward from here. Thank you.
Thank you. Thank you, Shivu.
Yeah. So I think I agree with you. To add to some of those things, PPA is the bread and butter of EDA. That's going to continue, right? All EDA tools are going to make sure that PPA is keep pushing on, right? What I see is EDA is good in automation. There is going to be more and more automation happening there to improve the productivity of the tools and other stuff, right? To give an analogy, I take this truck example kind of, right? Previously, there used to be a driver driving the truck. Then we have currently driverless truck coming. But eventually, we are moving towards a control system where a single person monitoring and controlling a bunch of trucks, right? I think in the EDA industry also, we are slowly moving towards that, right? If you see currently in the physical design side, we have an intelligent chip explorer kind of where a person can explore a lot of things without iteration so that he can spend time on other important things. And eventually it's going to be like cockpit kind of stuff, one guy managing and designing multiple designs in a single environment kind of, right? So that's where the automation keeps going to go, right? And then the third point I like to make is, as some of the panelists talked about, it's the cross-domain optimization, right? EDA being computational software, and a lot of system companies coming into this semiconductor side doing, so there's going to be a lot of cross-domain optimization happening, especially with mechanical and electrical involved, CFDs, computational fluid dynamics, those kind of things in automotive. So that's going to give a big role here going forward.
Thank you.
You know, sorry, you want to go first? Please go ahead. You know, this question reminds me of a quote that is attributed to Henry Ford. When he made his first car, it is said that his quotes were, if I had asked my customer what they wanted me to make a faster horse. So in EDA, while we are making the faster horse, we are also trying to see, at least from the Siemens EDA side, what is the next car that is going to revolutionize and transform our industry? So yes, you know, machine learning for logic verification, check. 3D IC, because more than more is relevant, check. All of those things will happen. 10% productivity increase will happen. And we all will work on it to keep pushing that envelope till we cannot push it anymore. And if you focus on two things, last night, Professor Lee talked about, there is a limit to how much we can keep pushing the physics. There is a limit that's going to come. And we are looking at doing something before we hit the limit. And then just before this panel, we heard from Skyroot, the ability to model a design because you cannot manufacture and test it before it is launched. So what we are looking at three pillars. There's, of course, technology scaling. People who are chasing more, we are with you to help you chase more. We'll be there with you. If you are trying to go more than more, 3D IC, yes, we'll be there with you along with the rest of us. Then the question is, you know, Sumit, you talked about, logic synthesis came about, right? That was a transformational step that allowed us to go from 1,000 gates a day to hundreds of thousands of gates of design per day, right? So we are looking at that. You mentioned HLS. I believe the time is now right for us to seriously think about HLS. And I'm emphasizing this because I know there are a lot of students here in the audience who have not yet joined the industry. So you have the opportunity to not be tied down by all the baggage that the rest of us in our generation have been tied down with, because Verilog is all we have known. Synthesis is all we have known, but you have the opportunity to change it. The third is designing at the system level, right? When we design electronics, we always make a digital twin of the IC or of the PC board before we manufacture it. What we are talking about is having the ability to do a digital twin of the entire system. Because remember, everybody's system is somebody else's component. You build a piece of silicon, it has to go on a board. The board has to go in a subsystem. The subsystem has to go into an enclosure. The enclosure can go in a satellite launch vehicle or it can go in the car. So we are looking at that, giving the ability to the designer collaborate with its partners to build and conceptualize a system before anything is manufactured. I'll be more than happy to talk to people, to you, if you have any specific questions on what we're doing, but I leave it at that because we are between you and lunch.
Thank you.
So the panelists already talked about the 3D IC megatrend and how EDA has to stay ahead, right, to enable the computations. I just wanted to add a small corollary to it. Recently, I got a request from a person about extracting, a structure they were designing. Generally, I would ask, extraction, okay, it would be at like 25 degrees Celsius or 125 degrees Celsius. So this person said, it's at minus 269 degrees Celsius. So that's 4 Kelvin. So they were designing for qubits. So that's also something that's emerging, quantum computing, superconducting applications. So that's something also we are investing development into, and we see future applications coming forward for that.
Yeah. So Dipanjan, I have a different question for you, more as academicians. Recently in Indian academia, we don't see there are a lot of interest on pursuing EDA as a PhD topic. So is there any change happening? We do see that whenever we go out that the rate is not that high as what it used to be in the past. Wanted to know your views on that more as an academician. How is the EDA considered as a research topic in academia?
I think, yes, today I think, if you say that you're doing data science, then, students are really interested about it, right? But, let's talk about, like, let's say from India, right? In computational software, we have really done well. Earlier it was Wipro, Infosys, and now I don't see why we cannot do more in EDA, because all that we need is sort of, computational expertise and so on. In terms of students, we see, I'm blessed to be part of ISC, so we see, very good students. I think maybe it's a cliche, but the tier 2, tier 3 needs to be enabled, and the opportunities like what we see needs to be projected well, so that they can see what the kind of impact they can create in everybody's life.
Thank you.
I just want to add to that. I work with multiple universities. I think we all who've been in the semiconductor industry for such a long time know that we've had a wonderful career. But somewhere we shy away from actually communicating this to the younger crowd. Yeah. Most of the kids don't want to take electronics. It's a very sad part. There is so much money being put in this industry from the government. A lot of startups are coming up this area. If you don't have right talent at the right time, it will get affected. So I think one of the things we all need to do as a community is to actually sell our semiconductor jobs very effectively in this community, because they still think it's not cool to do semiconductor job. But we all here know it's one of the coolest and most challenging job we can ever have. So something is missing. I think we should take it on ourselves and try to fix this.
Yeah, EDA jobs as well, sure. We hire a lot of NCGs, right? So I can state one story. We are partnered with a college in Delhi. We go to them often to hire candidates. Typically, I'm in the application engineering background, so I have to hire from EC background, right? In 1 year, I specifically found people who were purely doing EEE, but they knew that, ANSYS is hiring for CMOS, VLSI. They put in extra effort, they learned the CMOS part of it, and they did well in the interviews. And they are doing very well as part of my team now. So I'm stating that because it's not the norm, right? I would like to see that to be the norm. We would like to see more engineers coming into EDA, coming into semiconductors. We look forward to that. There is great challenges that we are solving from Indian EDA, and we would like you to be a part of it.
Thank you. Probably for the interest of time, my last question to Ruchi, more as an IAS reader. So Ruchi, how is the funding situation, business situation in the EDA space because as a part of IESA, you look at the overall semiconductor industry in India, their growth, future roadmap policies, everything. What's your views on the EDA in India, specifically on the business and the funding perspective?
I know that I may end up saying something which might ruffle a few feathers. But EDA and startups in EDA is hard. And you'll agree with me, right? It's really hard. And there are multiple reasons why it's hard. Number one, the four of us who are sitting here, we have armies of people who are trying to look for discontinuities in every single flow that we have built that is being used by our customers, and we're trying to plug those holes, right? For a startup to compete with the might, Shivu talked about 3,500 odd in India. We have about 3,000 odd in India. You said about 2,500 in India. That's almost 10,000 people in India who are trying to look for these continuities. And it requires a lot of courage and a lot of conviction to, Simyog, what you're doing is amazing. It's awesome, right? We just need a little bit more of that. What I do believe is that for a startup, EDA startup in India, personal opinion, not Siemens' opinion, do not go after the plus 10% or the plus 20% or plus 30% that Sumit had laid out. Look for something which is fundamentally broken, which is not on our radar, where you can go in and address a specific problem that nobody else cares about for multiple reasons, and which is what you're doing. So if a startup can identify that, then there is scope for that startup. And when that happens, there is funding available. What ISA has to teach the community, the investor community, which we are working on, is to not equate this industry, not just EDA, but also semiconductor, as an app industry, right? We will not make a unicorn in 6 months. We will not make a unicorn in 1 year. So going out to the community of investors, educating them about the time it takes to be successful, but once you're successful, you're very successful. So ISI is working on that. We'll continue to focus on it. We'll continue to do events and bring EDA startups also to come and present to the investors that we bring on board. But it is hard.
Thank you. So we thought of taking audience question, but for interest of time, we need to stop right here. We know that, thanks for staying up before the lunch. I think we are between you and your lunch. So I would like to thank all the panelists to come to the stage and express their views. EDA definitely, it's a foundation of all the semiconductor design process, and thanks to that, today we are successful. So thanks, panelists, for expressing your views, and thank you. Yeah.
Thank you so much, all the panelists, for taking out time and being with us today. Now, I request Mr. Santosh Yachireni, fellow at AMD, to honor our guest, Mr. Shivanand Koteshwar. Thank you so much, sir. Now I request Mr. Narsimhan Agaram, Senior Director, Qualcomm, to honor Sridhar Rangarajan. Now I would request Dr. Padmini, Senior Director, AMD, to honor Sri Dipanjan Gope. Now I would request Dr. Usha Mehta, Professor Nirma University, to honor Sri Ruchit Dikshit. Now I'd request Sumit Goswami ji to honor Mr. Vinayak and Subramanian. Now I am stealing this pleasure of honoring Sumit ji myself.
Hello, so I'm the co-session chair for the 5A Embedded System Design session. So my name is Chetan Kumar V. I am basically assistant professor in BITS Pilani, Hyderabad campus. So my research area is mostly related to VLSI circuits and systems. So we'll start with the session. So the first paper is DR array-based reconfigurable architecture for mixed radix FFT. So the authors are Kallapu Rishita, Dimitros Tathis, Srinivas Bopu, and Ahmad Hemani. Okay, so the speaker for, the presenter for this paper is Kallapu Rishita. So Kallapu Rishita is from Hyderabad. She received BTech degree in Electronics and Communication Engineering from G. Narayanama Institute of Technology and Science, Hyderabad. She completed her MTech from School of Electrical Sciences, Indian Institute of Technology, Bhubaneswar. So her research area is related to VLSI circuits and systems. So I invite Kallapu Rishita to start with her presentation. Thank you.
Good afternoon, everyone. Today I'm going to present on our work DR array-based reconfigurable architecture for mixed radix FFT. I will be starting with the overview and then proceed with the methodology and the implementation examples of FFTs, concluding at the last. So FFT is used nowadays in many applications of DSP and in some communication applications. Like for example, if we take the OFDM receivers, FFT is being used in them. And we have like a fixed radix, mixed radix FFTs and all. So mixed radix FFT basically, it gives the flexibility to choose radix for each stage of the FFT and all. So in order to implement these FFTs, we have some hardware, like what are all the different possible hardware implementations that we can see is a general purpose processor, HICC, FPGAs and all. So if we go through the general purpose processor, we can see some performance issues, and if we go through HICC, we have some flexibilities. So in order for any DSP application, it is better that we go through a reconfigurable architectures, and in that we have fine-grained and coarse-grained also. So FPGAs come under this fine-grained architectures, but if we see this FFT thing, this is a ward level application, and going through FPGAs might lead to high area overhead and expensive routing and all. So CGRS, which are the coarse-grained reconfigurable architectures, have come into picture for various ward level DSP applications. So to define our problem statement, here we are proposing an efficient hardware solution to implement a mixed radix FFT through this reconfigurable architecture. In the left side here we can see this is the base architecture which we are taking as reference to develop our FFT reconfigurable architecture. If we see, there are multiple cells here in parallel, and here one DRRA cell that we refer here is a combination of a register file, which is a memory block, and also a DPU, which is the basic processing unit. So in this base architecture, actually, they are simply performing some basic level DSP calculations like an addition, subtraction, MAC, convolution, and all. So this is the reference with which we are actually developing an FFT-specific reconfigurable architecture. So the scope of our work is like, here now we are changing few things, like we are designing a processing unit in our design. which is flexible for both radix 2 and radix 4. And we are designing a twiddle factor generation unit. And we are finally, with the help of all this interconnecting this things of processing unit and memory and all, we are showing some examples of how we are implementing different lengths of FFTs. So like there are also works done based on the CGRS to implement FFTs, like smart cell, CREMA and all. And as twiddle factor logic is important part of an FFT, there are also works done like a reduced ROM tables method and CORDIC algorithm they have been used. ROM tables method actually increases the memory that we need if we move on to a larger endpoint FFT. And if we go to CORDIC, the latency increases for each twiddle factor generation. So we'll see a different method in our work here. These are the basic equations, and left side gives the radix 2 and right side gives the radix 4 equations. So whatever we need to compute are the data samples and the twiddle factors as shown in these equations. At a time, we will take data samples and the twiddle factors, and the processing unit is computing these equations internally. So this is a single cell architecture, like we saw single cell architecture for basic DRRA cell. This is a modified one in which the register files, if we see, there are 2 register files instead of 1, because as we are dealing with complex numbers in the FFT, and there are like 8 ports for address reading and writing part, and there are AGUs, like DSP applications generally follow a specific address pattern. So in order to generate that address pattern, there is a AGU blocks here. And then there is sequencer to control and configure all these blocks here. There is a switch box, as there are multiple cells and there need to be a communication between one cell to the another. There is a switch box here to provide that. And there is a twiddle factor generator to generate the twiddle factors at the necessary time and to provide it to the DPU. Like DPU receives the information, the data samples from the register file here, and the twiddle factors from the twiddle factor generator here. So if we see the DPU part here, at a time it can take 4 complex numbers and 2 twiddle factors and process according to the equations that we have seen for the radix 2 and radix 4. Internally, all this multiplications and addition calculation goes on in this processing unit, and then 4 complex numbers will come out as the output. Currently, this DPU is supporting radix 2 and radix 4 here. And when we come to AGU, like I said, for DSP applications, we need a specific pattern of address that needs to be developed. This AGU actually gives an output of addresses. It actually depends on what is the endpoint FFT that you are computing, what is the radix on which you are computing, and how many number of cells that you want to compute in parallel. Based upon all this, the address patterns are given sequentially. So coming to the sequencer is there to configure all the, control all these blocks to give all the necessary things required for all these blocks. And then there is switch box. So at a time, there are 8 inputs required for the DPU and 8 inputs for the register file. So there are 16 multiplexers which are providing this 8 and 8 totally output, so that these can be given to the inputs for the DPU and register files again. Basically, in FFT, we need to provide the output of first stage as the input to the next stage. So that's why after the DPU computation is being done, we are writing back the results again to the register files. So that's why there is an input to the register files also, there is an input to the DPU also, and the multiplexers here are giving those inputs. And coming to the twiddle factor generator logic, the table here shows an example of a 32-point FFT, and we can see like it is a radix 4, 2, 4 for all the 3 stages. And we can see a specific pattern in this twiddle factors, like for first stage and second stage, there is a specific pattern in this thing. So we are basically trying to implement this pattern in our generator block, twiddle factor generator block. So there is some naming convention here, like a seed value and a base twiddle factor. So the base twiddle factor is the initial value that we are providing, that W32.1. So with which we are multiplying the seed values. So here we are using a consecutive feedback method so that the output comes and we are again multiplying with the seed value, and this process continues till all the necessary twiddle factors are being generated. Coming to the, this is the FSM that is being used to, for the twiddle factor logic. And here we can see in the architecture also, at the right side, like we are using a feedback mechanism here, and we are continuously multiplying it with some seed values, which are actually stored in the registers that we can see here. And this mechanism goes on. And there is one more multiplier at the right side, complex multiplier 3. We are using this because when we move from stage 1 to stage 2 of FFT, we need the base twiddle factor, which is a new base twiddle factor for the second stage. So we are using this multiplier here for that one. And as I said, we will be using registers to store the seed values and all. And the generation of these twiddle factors also depends upon, like, if we are using different number of cells, like that particular cell should give the twiddle factors corresponding to that cell only. Like that, it depends on that also. Here I am showing examples, different implementation examples here. For a 16-point FFT, how an address generation scheme actually works. Like here, in the third point, stage 1 addresses from which data samples are being picked up for this example is showed. Like this pattern repeats, and this pattern is actually generated by the AGU that we have seen, and there is this twiddle factors correspondingly generated at the same time, like the data according to the addresses and the twiddle factors. Similarly, at the same time they comes. And for stage 2 also, there is some specific pattern here which is generated by AGU and all. If we come to the 4-cell configuration here, we see the 64-point FFT example here, and we can see there is a different how a switch box comes into picture in here. Like the DPUs here is taking information from all the register files. So switch box plays a role here in connecting these register files and the DPUs so that we can pick information from any register file. This is the 2-cell configuration case. Similar to the 4-cell, here also switchbox plays a role in connecting. And if we see on the right side diagram, we have a way how in which clock cycle, which data samples we are picking to execute which butterflies and all. So finally, we implemented all these blocks using in Verilog and VHDL, and we have put the number of cycles that are required for each endpoint FFT with different possibilities of different radiuses, different number of cells. By using all this, how many number of cycles we are taking to execute an endpoint FFT, we have put it here. And then we have also compared our results with the previously existing CGRAs of smart cell morphosis, Remus 2MB and all. And then we have the synthesized results also, which we implemented this, synthesized the results on the Kintex UltraScale Plus FPGA board. Finally, I would like to conclude by saying that we actually designed, modified the previous DRRA cell in terms of the processing unit, which is specifically designed to compute any FFT with radix 2 and radix 4 in each stage, in any of the stages included. And we have a modified switch box and register file, And we have added twiddle factor generator logic, which is actually taking less time and less memory. And then we have different endpoint implementations that examples that are being shown here. And we observe that our method comparatively takes less number of cycles, and we finally showed the synthesis results on the FPGA board. These are my references. Thank you.
What are the challenges that you have faced in reconfiguring?
Sorry?
What are the challenges that you have faced in reconfiguring the FFT?
The twiddle factor generator block is completely new in here, which was not there. Previously, there were many works based on Cordic algorithm and all. So yeah, this was a new one, and we.
And how many number of cycles you have reduced comparatively?
It depends upon the point of FFT that we are computing. If we see initially for 16-point FFT and all, it's almost same. But as we go on to 1024-point FFT, we can see nearly more than half reduction in the number of cycles.
Okay.
So any more questions from the audience? So again, just to add, there are much more comfortable seats in the front, and these were occupied by pioneers the last 2 days, so you may not get a chance again. So those who are at the back maybe can come and occupy these sofas that are available here. Any other questions from audience? Okay, so I have just one question. So what was the overhead for reconfigurability when you compare it with the normal FFT architecture?
What is the?
Overhead, area overhead, or how many more cells were used when compared to normal FFT?
Actually, we searched about this about in the previous works and all, but the architecture is not the same. Like we couldn't get the RTL and all. They use a different FPGA board and we use it different.
Okay, so you did not get a chance to compare?
I saw the numbers, ours is less comparatively, but I couldn't exactly put up the comparison here because of the different architectures.
Okay, thank you. So let's thank the speaker again.
People see nothing, what people see nothing, what people see nothing, people see nothing.
Gotkalkar, Ashish Vanjari, and Mehir Modi. Bhaskaran is going to be presenting the talk today. Bhaskaran earned his Bachelor of Engineering degree with specialization in electronics engineering from PSG College of Technology, Coimbatore in 2006. He started his career in Honeywell Technology Solutions, working as an operating system engineer and low-level drivers for flight management systems. He has worked on software as a software engineer at Texas Instruments, developing low-level drivers for Sitara and C2000 product lines. Currently, he's actively involved in developing boot-ROM firmware, peripheral bootloaders, and secure software for C2000 real-time microcontrollers. Please.
So good afternoon, everyone. Today I will be talking about live firmware update in the context of real-time control systems. So basically, we'll see what is live firmware update. So we all know that like any embedded systems or any product if we take, if we want to do the firmware update, either like we take the system down, perform the firmware update, and then reboot the system. That is one approach. Second is we would have come across the OTA, which is like while the system is running, we will download the software, update the software, and then go through a reset to bring the system back. So that's how we typically do. So the context of this paper is like when we perform OTA, can we do the switching to new application without going through a reset? So that's the challenge we are addressing here. And we have seen this problem statement from customers from the server power supply systems, like where it will be running 24/7, and we can't take the system down. So even if you go through a reset, at that moment, there should be some other backup which will be supplying the servers. So it's like probably you would end up duplicating the systems, ending up with a costly solution. So this is something which will help us to switch to the new firmware within a short span of time. So the switching to new application without going through the reset of the device is what the problem that we are addressing here. So further again, to define the scope, the context we are talking about is in the real-time control systems, where it will be more of interrupt-driven systems, and there will be some idle time in between the interrupts. So we should be able to switch to the new firmware within that short span of time. And again, like if the new application is entirely different, then it is going to be difficult to perform the live firmware update. But if there is a delta change, any bug fixes, future addition, then we can take this approach to switch to the new application within a short span of time. This can be applied for other systems as well, maybe with probably corresponding tweakings or any modifications applied to that. So I will start explaining how we are doing this. So basically, in over the firmware update, it's typical to have dual banks or multiple banks where you'll be running the application from one of the banks, where you can update the new firmware in other bank. So the basic assumption we have here is like we'll have dual banks. So and again, going back, the context of this subject is for the devices where we have internal flash memories. Considering that we have 2 flash banks in this presentation that I'm going to talk about. So the way we have arranged is like, so we have the actual application, and we have something called a custom bootloader. So this custom bootloader will help us to manage this live firmware update. It's one part of the whole sequence. So what is a combination of this custom bootloader? One is the bank selection logic. So when the device boots up, it will jump to a fixed location in the flash memory. So we should have some logic to decide which is the latest image, and then switch to or start running that application. So that's the bank logic we are talking about. The next one is the SI kernel. So it is not something to do with the higher application RTOS kernel. So basically the utility which helps us to download the image over any of the peripheral medium, and then help to update the firmware. That's the kernel we are talking about here. So in addition to that, we will have some few metadata, so which is like the start address where the application should be start running from, and we have a key value and the revision number. So these two elements helps in identifying which is the latest image. So we have a magical number in the keys. So if the key is written, only then the image is valid. Otherwise, we should ignore that. That's the first level of check we do. And then when both the keys are valid, so then we look at the revision number. We can have either like the latest image is either the lower revision number or higher revision number. So accordingly, we can decide which application to run. So in addition to the dual flash, one other challenging aspect is that when you have the interrupt vector table with multiple vectors, so when you switch to a new application, we need to update all the vector pointers. So that is one thing which will be challenging. So it has to be done during the initialization of the new application. And this is a high-level view, like how the overall over-the-air update happens. And we need support from the host with the necessary tools to make it happen. And I think I talked about the custom bootloader part. So in addition to this, we would need additional support in the compiler and hardware to make this switch easier. Even without all these features, it is possible, but with more effort from customers, like to switch from old application to the new one. So when it comes to compiler, when we have two images, let's say the old image and new image, the new image can be like either like a feature deletion or modification, or we would have new feature added. So accordingly, the text portion or data portion or the function pointer, some of these would have changed. So the idea is like to, we can do this like, in the new application when you compile, you need to place all the reused elements or the common elements between the old and new in the same addresses so that it makes the switching process easier and within a shorter span of time. So in order to achieve that, typically we either use the hash pragma, like to define which address the variable or the function should go. But probably we can take help from the compiler where it can support a feature to place the reused elements in the same locations so that the initialization or any other configurations that we need to do while switching to the new application reduces. So, and again, coming to the application flow, so basically, when you talk about, let's say the application is running, the current application is running, let's say from the bank 0, and we got a command to switch to the new firmware. So basically, the application triggers the kernel part, which is part of the custom bootloader. So at this point, the actual application will be running. It will be servicing the interrupts, and it will be, the actual application is still running. So the kernel runs in the background. So whenever there is an idle time, the kernel downloads the image, programs into the alternate flash bank, and then it performs certain installations before we really jump to the new applications. One of them could be like how to initialize the new variables in the application. Let's say you added 5 variables in the new application. So we may need to initialize them. That is one of the things. Second is like how do we handle the vector table. So the vector table can be initialized as part of the new image initialization, or the other option would be like while you're running the old firmware, during the idle time, you set up the vector table. For this, we would need support from the hardware, like a shadow vector table where we update the new pointers, and then at the moment where we want to switch, it seamlessly translates or switches to the new vector table. So all those configurations need to be done when the old firmware is still running. So this will help to reduce the amount of initialization that we need to do as part of the new application. And here we also talked about retaining the variables in the same address. So this will help us to keep the context of the application in place. So when the new application starts running, it need not do the complete system reinitialization. It will use the same context, probably initialize the peripherals or some of the necessary things, and then quickly jump to servicing the application. Yeah, in the top, I don't know if it is visible, like, so one of the other things is like it can be possible to have a flag which will indicate to the new application that either now we are switching from the old firmware to new firmware, or is it a complete power on reset. So that will help to help the new application to decide whether it need to go through the complete reset or just the delta installation. So here we have shown the results from one of our system solution. So the top one shows like the process involved, like downloading the typical firmware as part of the OTA. And then the middle one, we are seeing the warm init. So that happens when you are executing the previous application itself. So you are getting ready to switch to the new application. So typically we get few microseconds to switch between the new application in the real-time context. So we need to get all the things ready and look for the idle time where it is the right moment to switch to the new application. And when new application starts running, it can do bare minimal initializations and then start servicing the application. So, and the bottom image shows the actual switchover. So we can see that we are running the old firmware, and then within short span of time, we activate and switch to the new firmware. You can see the translation in the third waveform here, where the duty cycle is changed from the old and new firmware. So with the combination of hardware features, software, and the compiler, we can make this switch from old firmware to the new one seamless. like we have seen here. Yeah, that's my presentation. Thanks.
As a remote configuration of the bootloader, how memory will allow as a program wise, if it is a Docker container mechanism, I can understand. So without that framework in place, how you take care of a multiple configurations or multiple instances, multiple write, these scenarios?
Will you be able to rephrase? Sorry, I think I didn't get the question correctly. Sorry.
So there will be instances of a case where multiple modifications, multiple bootloader specific instances, if I have to do within a time. So multiple areas of work I am simultaneously need to be loaded onto the bootloader. How I can do, if not a Docker or container architecture above memory?
So while you are running the old application, maybe the design can be such that you will jump to a fixed portion in the new application where it performs the necessary installations without impacting the older application, and then it can come back to the old application. So this happens in the background so that all the modifications or changes, whatever you need, it can be set up in the background.
Background, okay. Loadable kernel modules, you can instantiate, but multiple you cannot do, right? You can do single. If I have that kind of modifications, multiple instances are coming. How will you take care of it?
Yeah, it can be addressed only in the single module, yeah.
So just add up. So would a separate hardware controller help this process? So I think most of it is now being done in the compiler. So would a separate hardware controller for switching or loading the separate flash bank would help in the process?
Yeah, if you don't have the enough bandwidth as part of your CPU, probably that would be an alternate option. But then again, that flash bank, the alternate flash bank where you update the new image, should be shareable or accessible by the other controller. So it depends on the system architecture, how it is put up.
Okay, so any more questions? If there are no questions, then we'll thank the speaker and
Our next paper is titled Write Intensity-Based Selective Address Remapping. The authors are Ashwati NS, Deep Buinia, and Himangi Kapoor. Ashwati NS will be presenting the paper today. Ashwati is a research scholar at the Department of Computer Science and Engineering at IIT Guwahati. She's working under the supervision of Professor Himangi Kapoor. She completed her MTech from Government Engineering College, Barton Hill, Kerala, and BTech from Government Engineering College, Palakkad, Kerala. She's working in the broad area of computer architecture, specialized in memory scheduling. Welcome, Ashwati.
Good afternoon, all. Thank you for the introduction. So, our paper title, VLSI, Write Intensity-Based Selective Address Remapping. Mr. Deep Buinia and Professor Himangi Kapoor are my co-authors. So, this is the overview of my presentation. I will start with an introduction to non-volatile memories and some of the related works which tries to enhance the lifetime of non-volatile memories, followed with a motivation and the proposal VLSI. I'm presenting some of the experimental setup and some of the results, and finally, I'll conclude my presentation. So, as we know, over the years, transistor size and cost are reduced, which leads to an increased transistor density. So, the Moore's law explains that every year the number of transistor per chip doubles. So, this increased transistor density helps modern chip multiprocessors to include many processing cores, and which helps to or which allows the concurrent execution of data intensive workloads. So, in the if the pressure on the processing core increases, we can also connect that the pressure on memory subsystem also increases. So the traditional memories like DRAM may not handle or fulfill the requirements needed for this data-intensive workloads. So non-volatile memories, emerging non-volatile memories are considered to be an alternative for DRAM, which have a advantage of which can provide non-volatility and high density with low leakage power consumption. So phase change memory, resistive RAM, spin transfer torque RAM are some of the examples for non-volatile memories. Even though they have several advantages, they have some disadvantages like low write endurance. It's approximately 10 to the power 8, while DRAM has an write endurance of 10 to the power 16, and which have high write latency, also high write energy. So directly replacing DRAM with NVM is not a good solution or not a possible solution. So some of the related works which tries to improve the lifetime of NVM. As I mentioned before, writes are more costlier for NVMs. They tries to improve the lifetime either using a write reduction technique or wear leveling algorithms. So write reduction techniques tries to reduce the number or total number of writes to the NVM cell through either encoding or compression techniques. While wear leveling algorithm not try to reduce but try to evenly distribute the writes to the whole memory. The wear leveling can be either in intra or inter line. So when it is interline, the wear leveling is performed across the blocks, while if it is in intra line, the wear leveling is within the cache line or within the memory block line. And the wear leveling algorithm, the reallocation in the wear leveling algorithm can be performed either in a table-based manner or an algebraic-based method. So our VLSI algorithm is a wear leveling algorithm which tries to distribute the number of writes in an NVM cells. So the motivation behind our work is that, as we know, the memory patterns are not constant or consistent, even across the not across the application or even within the during the execution of application. So memory writes, we conducted experiment using spec benchmark, and the memory, we found that the memory writes are skewed in particular location. So from the figure, it's like we can take an example that BZIP2 benchmark, which is denoted with the blue color, which has certain location, the number of writes are into the range of 10K or 15K, or sometimes it is 0. So the locations have varying number of writes. So heavily written locations have lesser lifetime because write endurance is very less. So wear leveling techniques tries to swap the addresses to distribute the writes, and the distribution can perform either in a random or sequential manner. But the overhead in terms of storage and energy when we do wear leveling, it's an important question. So instead of either randomly swapping the addresses to distribute the writes, we can check the write load and only swap certain locations which have heavy number of writes. So the overview of our proposal VLSI is that write variation aware address remapping, which remaps the address based on write access count, and it divides the memory banks into segments and remaps within a segments. So we are basically trying to remap the heavily written locations within a segment to lesser written location. So as I mentioned before, we will divide the memory into segment. This I have taken an example. So we divide in an equally sized segment, entire segment into equally sized segments. And when we do mapping or swapping, we need to answer two questions, that which location can we swap and when do we need to swap. So for that we use two thresholds. So hotness threshold we use to classify the memory locations either to hot or cold. Hot means the location has large number of writes in terms like if we consider a location have write count more than the hotness threshold, we termed it as hot location, and other locations are termed as cold location. And when do we swap these hot locations with the cold locations? We use a bank write threshold. So if the number of writes to a particular bank reaches this bank threshold, we trigger the swapping, and we trigger the swapping between hot and cold locations. So this is way we are performing, and we swap within the segment to reduce the searching time overhead. And I can explain through VLSI using a working example. We have taken an 8 blocks, a bank with 8 blocks and divided into 2 segments. So initial content of memory bank along with their write count. Initially the write count are initialized to 0. And after, we have considered a bank write threshold of 15 for an example, and a hotness threshold as 3. And after 15 writes, the content or current status of the bank is shown on this figure. So here the red color cell indicates hot list and green color cells are in the cold list. So we will swap the hot locations with the cold location within a segment. And after that, we will reset. This is the way we are swapping. And after that, the whole locations are again renamed to code list. And we have used a translation table for the future access because the addresses is changed to, for the future access, they have to check the translation table to go to the correct location. So in this way, we perform the VLSI. And we have used a GEM5 integrated with NVMain for the experiment. And we have taken a bank write threshold as 512. And we use PCM, phase change memory, as the type of non-volatile memory for our experiment. And for the performance evaluation, we consider a baseline technique which have no remapping or swapping, and the 2 existing ones, security refresh and segment swapping, was security refresh, which swaps the addresses using a random key. And this is an algebraic-based method which will swap all the location or sequentially swap all the location. So the storage, so the overhead associated with swapping is very high in security refresh. The second technique is the third technique is segment swapping. Here the segment with high number of writes are swapped with segment with low number of writes by keeping track of the write counts. Here this entire segment is swapped. So there can be a situation that some locations in the segment may not be write intensive. So that location also gets swapped. So the write overhead associated with swapping is more in segment swapping. And we have used 3 performance metrics for the evaluation. First one is lifetime improvement. So we consider the average number of write and intra and inter-write variation within a block and across the blocks for the calculation of lifetime improvement. And total energy, we consider both the regular read-write energy as well as the swapping energy. And the third is for percentage of write overhead, which calculates the number of or more overhead writes to the total writes. And I've shown this figure as a motivation. So before applying the VLSI, the variation in the write count is very high. So after applying VLSI, we could uniformly distribute the writes. And you can see the difference in the y-axis. Before it was 10K, now it is in the range of 1K or like 2.5K. So we could uniformly distribute the writes across the cells. And the second result is on lifetime improvement. So existing policies, even they could spread the writes, the number of swapping writes are more. So the lifetime improvement, we could achieve a better lifetime compared to the existing policy because VLSI tries to reduce the number of writes as well as tries to distribute the writes. And the second result is on energy, the total energy consumption. And we analyzed over baseline technique and we calculate the energy on swapping and normal regular read-write policy. The VLSI, the proposed one increases the total energy by only by 1.1 over baseline, while the XR and SS, the existing policies, increases by more than 10%. And the write overhead, again, this is analyzed on baseline policy. The number of swaps is more for the existing SR and SS, so the number of write overhead is also more. While VIPSR only swaps hot addresses with the cold addresses, so the write overhead is on 0.11, while for SS it is 21 and SRS it is 15.9. And we conducted a sensitivity analysis to find the value of hotness threshold, and we vary the value from 2 to 16. If the hotness threshold value is more, the location get labeled as hot very late. So the write overhead associated with those locations will be small. Like the overhead writes in terms of swapping will be more, but which incurs a large number of writes, so which degrade the lifetime. If the hotness value is very small, then the location gets swapped regularly or frequently. So the swapping write overhead will be more. So we took a value as a medium value of HT equal to 8, so that both lifetime improvement and write overhead we could maintain between lifetime improvement and write overhead. So as a conclusion, the limited write endurance of high energy of NVM need to be resolved to use it as an alternative to DRAM. So wear leveling helps to improve the lifetime of non-volatile memory. The proposed VIPSR algorithm tries to swaps the hot location with cold location within a segment. So we could improve the lifetime by 168 and 148 or the existing policy, and with a minimum energy overhead of 1.1 and write overhead of 0.1. Thank you.
Yeah, I have a couple of questions actually. One is, what is the optimal value for the HT? I think you've shown some graphs. Optimal value for the HT that you have chosen. And then this wear leveling is not a new technique, right? Is it VIPSR is the new one? What is new here? Wear leveling has been going on for a while in NVMe memories, right?
Yeah.
So, and then how often you do remapping? So this is my question. I mean, so it's a three-part.
So how often, like we have used a bang write threshold. We have used a bang write threshold to trigger the remapping. So once the bang write count reaches the bang write threshold, we will swap. So that is the interval, and that we have taken according to the existing policy. Like we try to maintain the what the existing policy have done, and we try to maintain a relation with that. And so first question I don't know.
The first question is, wear leveling is going on for a while, right? What
Yes.
is new here?
So we try to divide into segments so that like the searching time will get reduced, and also we labeling among hot location and cold location, and we will swap only the hot and cold location, not other locations. We are not wear leveling across the memory block or memory bank. We are trying to maintain like not completely maintain the swapping or remapping overhead. Try to reduce the remapping overhead along with wear leveling.
Understood. Last question is, what is the optimal value for HT?
So we, according to the bench, because it is a memory pattern dependent value, so we conducted a sensitivity analysis on 2 to 16. So it was increasing, like we have to consider both lifetime improvement as well as write overhead. We can't, like we have to maintain the trade-off. So we got HT equal to 8 as the, according to that 512 for the bang write threshold.
Hello.
Yes.
So from your report, I could able to see your energy overhead is 1.1%, right?
So more.
Yeah. So any thought process how to optimize that, because that is the hit you are taking?
Like it is according to the baseline policy, because baseline have no remapping. So like if you some like even though we have this much, that is very less actually. 1.1 is according to the existing policy, that 1.1 is very small, and we could achieve a better lifetime than the baseline.
But in the case of use cases where The magnitude of current is example of power is in, say, 100 plus milliwatt or watts, right? So 1.1%, it's a significant high. So how to address that, or any work it's going on, or any
not
thought
yet
process?
started, but we will think about that.
Okay. Thank you.
Yeah. Thank you.
If I remember correctly, I think you have used the PCM.
Yeah, PCM.
For this.
Yeah.
So any thought why you choose PCM? Because we are having a multiple other emerging memories. Also, PCM is not that mature if I talk about the fabrication wise. Like MRAM is much more mature, and like people like fabrication industry has started doing the PCM is still very novel. So any thought over it? Why you choose PCM in place of other memories?
PCM actually, okay, MRAM we didn't consider. Actually, we compared against the ReRAM technique because ReRAM is not as much as mature like PCM. So like among...
But actually, MRAM is much more mature than PCM also.
Okay.
Almost all the bigger fab like TSMC, Samsung, Global Foundries, everyone started doing the MRAM fabrication, but PCM and RM is still
about
very
to start.
novel, and we are not having that so-called very good numbers. Only I think some R&D phases only we are having, not some kind of a industrial numbers. So I think if you go for other memories,
better
especially
results
for
can
MRAM,
achieve. Yeah,
that would be better.
Sure. Thank you.
Okay. Thank you, Ashwati.
Yeah, thank you. Thank you.
Our next paper for this afternoon is titled Design of a Multi-Core Compatible Linux Bootable 64-bit Out-of-Order RISC-V processor core. And the authors are Sajin S., Shubham Sunil Garag, Anuj Fegade, Dipshika Gusain, and Kurivila Varghese. And the speaker for the presentation is Sajin, who has completed his B.Tech in Avionics from the Indian Institute of Space Science and Technology, Trivandrum in 2015, and did M.Tech in Electronic Systems Engineering from the Indian Institute of Science, Bangalore in 2022. He is interested in computer architecture, embedded systems, and digital VLSI. He is currently working in the avionics entity of Vikram Sarabhai Space Center, ISRO, for the last 7 years in the area of design of launch vehicle electronics. Please welcome Sajin.
Good afternoon. I'll be presenting our work on design of a multi-core compatible Linux bootable 64-bit out-of-order RISC-V processor core. These are some of the points which I will be trying to cover during this presentation. Directly coming to the presentation, as all of us are aware, RISC-V is an open source instruction set architecture developed by University of California, Berkeley. There are a lot of industries as well as academic institutes working on RISC-V based processors, and I have listed few of the open source processors which can basically boot Linux, both 32-bit as well as 64-bit. Some of the common things which you can see is most of these processors are open sourcely available processors are simple scalar pipeline processors with in-order execution of instructions. Except if you are seeing boom-like machines, it is having a dynamic execution of instruction in an out-of-order way which helps to achieve higher throughput compared to in-order execution. And one another similarity in these processors are most of these processors are designed using comparatively new hardware design languages like Chisel or high-level HDL like BlueSpec Verilog. With that brief overview, let me come to the problem statement which we are trying to do in this project. This is basically to design a 64-bit RISC-V superscalar processor core. It should be having an out-of-order execution pipeline. It should be capable enough to boot Linux, which means basically it should have the supervisory as well as the user privilege level support. It should be compatible to extend it as a multi-core processor, support like a standard bus interface like AXI. The design should be using a traditional HDL like Verilog, and the HDL design should be parameterized so that the user should be able to realize that or able to generate different instances of processor core based according to his requirement like area, power, performance without changing the HDL code. And I will be also covering some points like verification of the design processor core, how we have done that, and how we design an SoC around the design processor core and tested and implemented it on Xilinx FPGA-based platform, and how we designed a dual-core processor and an SoC around it. Coming to the microarchitecture and the specification, this is a 64-bit forward out-of-order superscalar processor. It basically supports RV64I instruction set as the base instruction set. In addition to that, it supports the another optional extensions like integer multiplication and division, atomic operations, single and double precision floating point operation, and usual RISC-V is having a 32-bit instruction length. In addition to that, to reduce the code size, it is having the compressed instruction set of 16-bit also. So it supports the compressed instruction set also. And we are having the supervisory and user mode privilege levels to support the, with the SV39 virtual memory subsystem specification. Basically, 64-bit of RISC-V is having 2 virtual memory system specification, SV39 or SV48. We support SV39 in this one. And the fetch rate is 16 bytes per cycle. Decode, rename, dispatch, and retire rate is like 4 instructions per cycle. And coming to the microarchitecture shown, which is basically inspired from the boom, and it is having a front-end portion as well as an execute or back-end portion. In the front-end portion, we basically fetches the instructions from instruction cache and identify the 16-bit and 32-bit instructions. Since it's a mix of 16-bit as well as 32-bit instructions, we identify it. And similarly, we are having the branch prediction algorithm based on G-share algorithm there to redirect the PCs. And whatever the identified instructions will be written to a instruction buffer in a common format like a instruction common format, and that will be decoded using the forward decoder, and we have an explicit register renaming to avoid the dependency, data dependencies, and that will be, the renamed registers will be returned to the distributed reservation station for the out-of-order execution in the pipeline. And another thing which we can see from the textbook out-of-order processor, one of the differences, instead of where there will be having the instruction-specific execution units like one integer execution unit or floating point execution unit, we have divided the functionality into small functional units and clubbed together so that same time maybe some 2 floating point operations can be happen or integer operations can be happen. Coming to the other specification, we are having a 16 KB byte 4-way set associative VIPT iCache and fully associative ITLB with a 3-level hardware page table walk based on SV39 specification, and 16 KB byte 4-way set associative Snoop enabled cache coherent data memory system we are having. So we are having a physically indexed, physically tagged 16 KB byte D cache. And the data memory management unit is having a dual port data memory management unit to simultaneously support the load and store operations. And we have also implemented the physical memory protection and physical memory attributes as per the RISC-V privileged specifications. And it follows the AXI for bus architecture. This is the pipeline overview. The microarchitecture can be basically divided into 9-stage pipeline, where the fetch, pre-decode, checking constitute the front-end portion. And decode, rename, dispatch, issue, execute, and retire comes in the execute stage. So the pipeline is similar till the execution stage for almost all the instructions, and it will be different from there onwards. So one of since the processor should be supporting multi-core compatibility, one of the requirement was to design an hardware cache coherent data memory subsystem. So that we have designed a cache coherent data memory subsystem using MESI write invalidate snooping based protocol. This is done using the D-cache as well as the snoop control unit. Basically consists of a D-cache as well as the SCU. So each of the data cache is having a individual cache request port. Whenever the data cache required to generate a bus transaction, either in the case of a miss or another cases, it will request through the cache request port, which will be arbitrated by the Snoop control unit and will generate a Snoop request back to all the caches using a common Snoop request bus. And this, to this request, each of the data cache will give the response through the Snoop response port, which will be again validated by the Snoop control unit and broadcasted back to the caches through the cache response bus. This is the design of the data cache. We are having the dual port in order to support one port exclusively for the processor and processor read and write operation, another port for the Snoop control unit, the snooping operations. It is totally controlled by an FSM. and similarly, the Snoop control unit hardware design is also there, which is having a first come, first serve based arbiter for selecting the cache request. And then that is also controlled by an FSM, SU controller FSM. Now, RISC-V specification basically support 3 types of interrupts, like external software and timer interrupt. And we support all 3 interrupts in both the machine mode as well as the supervisory mode. We use the memory mapped PLIC and the CLIN module for generating the external and software or timer interrupt respectively. So the PLIC is followed in order to prioritize the different external interrupts and external peripheral interrupts, and to generate one interrupt to the internal HLIC, which is the hard level local interrupt controller. And the software and timer interrupt are generated using the core local interrupter, which is basically following the Sci-Fi specification of the CLIN module. So the system control unit is having the control and status register files along with the HLIC, and it is also having the fence and atomic reservation logs, and the performance counters like time cycle instructions are implemented in the system control unit. So using the processor which we have designed an SoC around it in order to test and validate it on the FPGA. So this is the SoC design basically. So we have included the NAND flash controller, DRAM memory controller, and the general peripherals like GPIO, timer, SPA, and etc. in order to test. The corresponding memory map is given. And the boot ROM is loaded with a firmware which basically support multiple boot modes, where we can load the programs through an UART interface to the SRAM and execute it from over there, or through DRAM, we can load it to DRAM and execute it from there also. And similarly, boot ROM also support to copy the program from flash memory in the FPGA board to the DRAM and execute it from the DRAM. So this runs at we have implemented this design in Xilinx Virtex 7 FPGA based VC707 board. It runs at a frequency of 32 megahertz. And most of the IPs, the peripherals are implemented using Xilinx IP cores, which is available in the IP catalogs. We were able to get a benchmark score of 3.468 core mark per megahertz and 1.74 for Drystone, which is comparable to that Boom V2 as well as similar processor like ARM Cortex A9 and all those things. Now, being an out-of-order processor, it is very difficult to verify the functionality using the typical way of writing a test bench and seeing the waveform and all those things. So what we have done is, at the time of RTL design itself, we have included the debug messages along with that, so that when we do the behavioral simulation, we will be getting the corresponding logs. So that can be easily used and searched and can be used to find out what is happening for one instruction or throughout the pipeline. So that is the verification methodology which we have followed. Now, as I have said, one of the design requirement was to basically to have a parameterized RTL design, so that we should be able to generate different instances of processor core without any modification in the core RTL. So that is what so we have designed the core RTL in a parameterized manner. So we will be able to customize the parameters like fetch rate, return rate, and the BTB, the branch target buffer depth, and the global history register length, and all those things. Similarly, the depth of instruction buffer, reservation station, these all things are programmable with just a configuration file. So once we finalize the configuration, whatever we required, we can that configuration file can be given to a shell script which we have written that will generate the Verilog header. So along this Verilog header and the core RTL, without any change in the core RTL, we can use the Verilog header generated and synthesize for a different instances of processor. So suppose if we want a high performance core, we can increase the depth of the reservation station and the instruction buffer and everything. And if you want a lightweight code, we can reduce the values and similarly generate the different instances of processor. So this is a comparison where we are able to generate a high performance core with one specification, and a lighter core where we are having the resource utilization and 90% less, but the performance is also have come down in the similar way. Now, another thing was Linux booting. So the right side is I have shown the software stack defined in the RISC-V privileged specification. So we need to have a supervisory binary interface as specified in the privileged specification. So right now there is Berkeley bootloader as well as the OpenSBI, which is two open source implementations of RISC-V SPI. So we have chosen a very minimal embedded Linux system where OpenSBI is used as the supervisory binary interface. So what we have done is we have combined the OpenSBI and the Linux, which is custom built as a single binary image, and that can be loaded by the zero-stage bootloader, which is situated in the boot ROM, either using the UART to the DRAM and execute it from there. Otherwise, we can save it in the flash memory in the VC707 board and copy into the DRAM and execute it from there. So this is the general Linux build procedure which we have used. We have used the build root toolset to generate the custom Linux image for the processor, and we have designed using the by giving the Linux configuration as well as the file system configuration and the device tree source file which designed for the corresponding SoC. So the single binary image consisting of OpenSBI and Linux is programmed into the flash memory, and that so that will be able to, we can boot it from the DRAM. So this is the successful boot of the processor into the Linux user space. So we can see that it's getting into the user space and printing the messages like RC Linux and all those things. This RC stands for our lab in Department of Electronic System Engineering, Reconfigurable Computing Lab in the Department of Electronic System Engineering. Now, we have also shown that our processor core should be multi-core compatible. So we have designed a simple dual-core processor around it and a simple SoC around it. And we have implemented that design. So the corresponding dual-core processor as well as the SoC design block diagram I have shown here. This is implemented in Xilinx Kintex Ultra-Scale FPGA board, and it also runs at a 32 megahertz frequency. We are modified the firmware in the boot ROM so that we can load the program to the SRAM through the UART interface. So at that time, we need to have a synchronization between the two cores. So that is done using the one of the register which we have put in the memory mapped core CFG, as well as the heart ID which is available in the as a control status register. So we have designed the matrix multiplication and the quicksort application as multiprocessing application, and we were able to get a 1.66 and 1.54 times faster compared to that of the single core processor with this test application. And the resource comparison, when we implemented it in both the single core as well as the dual core in Kintex Ultra Scale FPGA is also given, where the dual core was almost taking the double as that of the single core. So we were able to design a customizable 64-bit out-of-order superscalar RISC-V processor, and that processor can be extended to multi-core processors without any hardware modification. So the customizable design allows basically us to generate different instances of processor according to our own requirement, and the main bus using the XI can be easily connected with different hardware peripherals, and we can use with custom memory map. So future direction which we are working is the ASIC implementation of the design. Similarly, the design enhancement with vector coprocessor and all the, and supporting the RISC-V vector extensions and all those things.
Yeah, so I have a couple of questions. So you have showed results for 2 variants, right?
Yes.
So have you tried out any other variants of
So
customization?
we have worked out. Right now, whatever I have shown is, I mean, like we are having the resource utilization problem with the FPGAs which we are using. So with that, whatever we could achieve. So obviously, we can get higher performance by higher number of specification, whatever I have given here. So whatever we could get with that FPGAs, that only I have shown here right now.
Okay. So you mentioned that like your core novelty would be to implement a customizable RTL implementation.
Customizable RTL so that any of the industries can be easily, because if you are seeing most of the open source processors, it is either using BlueSpec Verilog like Shakti IIT Madras, and either otherwise using Chisel and all those things. So it is very difficult for people to learn the Chisel, like, because learning curve is too much high. So that immediately using for an industry or academic people will be difficult. So that's why we have planned to do it like this.
But as far as I know, Chisel code can be converted to RTL code,
Yeah,
right?
yes.
So what would be a disadvantage of that over this?
No, the thing is like, if you want to optimize the data path and all those things, if you want to take the core and directly write something over there and modify, so that will not be immediately possible. So that can be done so that industry can be easily taken. We will be releasing this soon in the GitHub. So once people can take it and immediately do their own work and so completely working with a traditional HDL way. That is the what we are looking for in this case.
Okay. If there are no questions, then thank you. Thank you, Sunil.
We are now coming to the last session for embedded system design, last presenter. And the title is voltage-based Schmidt-Trigger sense amplifier with improved offset and reaction time for high-speed SRAMs. And the authors are Gaurav Saraswat and Anuj Parashar. Gaurav is going to be presenting. Gaurav Saraswat has a BTech degree in electronics and MTech degree in microelectronics and VLSI design. After his MTech, he joined Qualcomm India Private Limited as a memory circuit designer in Bangalore. Currently, he is working as a senior R&D engineer in the memory design group, Synopsys India Private Limited in Noida. Welcome.
Paper titled Voltage Boosted Schmidt-Trigger Sense Amplifier. So I'm going to present on the paper titled Voltage Boosted Schmidt-Trigger Sense Amplifier with improved offset and the reaction time for high-speed SRAMs. So me and my manager, Anuj, has worked on this, and we are from the memory design group, Synopsys. So the basic agenda of this PPT is like, first we will establish the problem statement, and then we'll touch upon the basic sense amplifier, which is a very conventional one, voltage latch-based sense amplifier. Then we'll go with the another sense amplifier, which is Schmidt-Trigger based. Then we'll talk about our proposed VBST-SA circuit, which is voltage boosted Schmidt-Trigger sense amplifier. Then we'll talk about the results of that and the important part of it, like how we will implement that particular sense amplifier into a memory instance, and then we'll conclude the reference and QAs. So we all are talking about very high computing necessities, and we are improving the speed of our processors day by day. But in parallel to that, for getting the highest throughput, we need to increase the speed of SRAMs also. My fellow presenters have already shown that how important the SRAM memories are, because for each and every block on SoC, like CPU, GPU, modem, audio processor, video processor, everywhere you need memories. So there is a requirement that we should work on the high-speed SRAMs. So when we talk about the SRAMs, approximately around 50 to 70% of area is already taken by the SRAMs on a particular SoC. So the yield aspect of that is also very important, because that will directly translate to the money. Yeah, so, but when we talk about very high-speed SRAM, then the sensing of the data is very essential in that. These days, even in the, the yield should be very good for this, and the sensing should be in the, when there's a very high noise environment, there also faithfully it can sense the data. So when we talk about the sensing of SRAM, sense amplifier is the basic element block which is used for sensing. So let me touch upon the two of the important parameters of a sense amplifier. So one is offset and the reaction time of it. So whenever we talk about a very good sense amplifier, in that case, we need to have a very low reaction time and a very low offset as well. So the basic definition of reaction time is, so when my sense enable signal comes, so after how much time my data is available at the output. So that is the reaction time, and offset is defined as what is the differential input I need to have for the sense amplifier so that faithfully it can detect the signal, and also it can faithfully give you the output, like it's a 0 or 1 written in the bit cell of a sense amplifier. So the scope of improving the offset and the reaction time in the sub-technology era is very limited. We can have like only device sizing changing or some design changes. Let me tell about the device sizing. So if I try to do optimization through the device sizing, then if you go to improve the reaction time, you will have a very bad offset. And if you improve the offset, then in that case, your reaction time will go on a toss. So this is a very tricky. So we thought about to have some new design thing so that we can optimize the offset and reaction time together. So in this paper, actually, we are proposing a novel scheme of VBSTSA, which has shown the improved offset and the reaction time when we compared it to the conventional VLSA with minimal area impact, so that we can improve on the read margin and also the memory access time. So this is a conventional voltage less sense amplifier. I hope everybody has seen this particular circuit. So this is still very, very much used in the industry and also like across all the tech nodes also. So in this, I can explain the operation of this particular sense amplifier in two phases. In the phase one, when sense amplifier is actually not operational, in that case, my SIN signal is 0. So my P3 and P4 transistor is off. P3 and P4 transistor is on, and my bitline and bitline bar is directly connected to the internal node of XT and XB. And T1 transistor will be off because SIN is 0, and there is no connection of common node CM to the ground. So now, as soon as my read operation start, word line triggers, so that my pass gate of a bit cell is connected to like the pass gate of the bit cell is now on, so that my bit line and bit line bar are connected to the internal node of bit cell. So based on the data stored in the SRAM bit cell, either bit line or bit line bar will start discharging. So as soon as a sufficient differential is generated at the input, it enters into the phase 2 where sense amplifier become operational as sense enabled signal goes to 1, so that P3, P4 transistors are off now, and bitline bars are disconnected from the internal node of XT and XB, and parallelly T1 transistor is on, and the common node is also went to supply level VSS. And after that, my resolving transistors N1 and N2 will start resolving the data. So this is how the operation of a basic VLSA work. So here I have shown the one equation where the reaction time can be seen that reaction time is actually inversely proportional to the transconductance of the resolving transistors N1 and N2. So directly, if I see that if GM of these two transistors improve, we can reduce the reaction time. This is the basics of Schmidt trigger sense amplifier. So here we have added a NMOS part of a Schmidt trigger circuit, which actually used for modifying the switching threshold of an inverter. So through this, actually, what we are achieving is that the inverter, which is actually holding 1, will be weakened compared to the inverter where the inverter is pulling down to 0. So because of that, there will be a lowering of VGS of that input NMOS, and eventually the change in the VT because of some variation will be lesser, and hence the offset, which is a statistical term like Monte Carlo, through Monte Carlo we calculate this. So that will be reduced. Because of that, Schmidt trigger shows a quite better offset compared to a conventional VLSA. All these references are also mentioned here. You can go through if you want to be in detail of it. So this is my proposed circuit. So here, actually, with the Schmidt trigger action, we are improving the offset, but because now you can see there will be a stacking of NMOSes, N3 and N1, N4 and N2. Because of that, slowness has been produced and the reaction time increased a lot, especially when we work in the lower voltage domain. So now, because our proposed sense amplifier circuit actually helps to mitigate that slowness and improve the reaction time significantly. So to start with, let me touch upon the read operation of it, so we all know that we normally use a negative bitline based write assist scheme in our SRAM memory to improve our write operation. For that, we need a negative voltage generator, which is this negative boost circuit. So it actually generates a negative voltage at the node out. So in a write operation, my sense enable signal will be 0. So my MW MOS will be on, and this out is connected to my write driver. So this is a conventional write scheme. I haven't touched anything in this, but yeah, during the read operation, I have reused this particular negative boost circuit to optimize the area as well. So now, when my sense enable signal will turn on, so during that time, Schmitt trigger action actually will improve the offset of this particular sense amplifier. And just before sense enable signal, we turn on this boost enable circuit so that a negative voltage is present at the node out. So as SEN signal comes, MW will be off, so it is disconnected from the right circuitry, but it enables the T1 transistor, which is a tailgate, and because of that, a CM, common node voltage, will go down to the negative region, and the transconductance of these two transistors, N1 and N2, is actually proportional to VG minus VCM minus VT. So as you are going into the negative direction of that, of VCM, so you are actually changing the GM of N1 and N2, and because of that, reaction time improves a lot. So in the result section, I'll share this. So these are the result sections. So for all these simulation, we have used 22 nanometer CMOS technology. The simulator used is HICC. We have used the worst PVT condition for the analysis, which is flow, global corner, SSG, and with temperature minus 40. Voltages we are varying a lot. And wherever we are doing the Monte Carlo simulation, there we have used 1,000 sample points. So through the first graph, it is very much observed from this. So VBST assay with Vout 0 is almost equivalent to ST assay. So VBST assay and ST assay is showing around sigma of 7 at 0.5 operating voltage. So approximately around 48% of lesser sigma we have seen compared to the VLSA. And also in parallel, because of the stacking of two NMOSes, the slowness has been produced, and we can see that reaction time of conventional VLSA is much faster compared to VBST and STSA. For lower voltage domain, it's approximately like doubled. So the reaction time is very bad. So because of now we are using the proposed VBST assay, so we are applying negative voltages to our sense amplifier. So I have used from 0 to minus 200 millivolt in the step of 50. That you can change, you can achieve this particular thing by changing the cap size of the boost circuit. So through that, you can change it. That we can see from this curve, first curve, that as I am applying negative voltage more and more, I'm improving the reaction time, which is very significant when we are operating in the lower voltage domain. And approximately when we are applying around 200 millivolt, then approximately around 4 times of improvement we have seen in the reaction time. So which is actually huge if we talk about like sub-technology nodes where we are using a FinFETs and also that is very significant. Also, because we are applying the negative voltages in parallel, the reliability also be important. So we run the Monte Carlo simulation with those negative voltages applied. So what we have observed that sigma is pretty much same, and we have not seen any failure. So yeah, so because of this, we can say like through the on the reliability side, on the yield side, we are not losing anything. So this is the implementation of the proposed design. So here, actually, the boost circuit normally got activated during the write operation only, but we are triggering it during the read operation. Read operation. So we have changes. We have enabled this through the 2:1 mux, and also we have introduced some delay element in the SEN and the read negative boost enable signal. So through the WR pin, which is a write enable signal, we are controlling that. Is it triggered through the write enable boost enable signal or through the read boost enable signal? Read boost enable signal is actually tracked because this is normally happens at the end of the operation, and you can't trigger it very early because otherwise you will lose on the boost cap generated through the negative boost circuit. So the timing is such that just before the SEN signal, that should be triggered. So during a read operation, that are triggered, and after that write enable signal will be 0. So my boost enable signal will be triggered through the read boost enable, and after that it goes towards the column mux through the bit cell. And in parallel, you can also see that there's a write path as well, and which is also controlled through the SEN signal. So this is how we have implemented this in a memory instance. Let me talk about how much impact this is making on an overall access time of a memory. So access time of a memory is defined as clock to queue. So when my clock is triggering, after how much time your queue, the data is available. So this consists of basically 3 parts, clock to word line to sense, and sense to queue. So compared to VLSI, we have improved the offset and the reaction time. So because of gaining in the offset, you can optimize word line to sense now better. And also you have improved the reaction time. Because of that, now SEN to Q also reduced. And if I talk about the basic improvement at a memory instance level, so if I take a high speed single port RF memory compiler, so for a medium density instance, that corresponds to approximately 10% of access time. So I've reached till the conclusion. So we have proposed a better offset reaction time, giving VBSTSA compared to VLSI. And to the best of our knowledge, we are the first to propose the idea where the negative boost circuit is used for the sense amplifier in the read cycle. And also, like we have shown the results with the 22 nanometer CMOS technology. And also we have observed that 48% of better offset and 4x time of improvement we have seen in the reaction time. Similarly, we have also proposed how we will implement this particular VBSTSA at memory instance level to get the most of it. These are the references we have followed.
Yeah, any comments on the area overhead that you have? I think the number of transistors almost is 3 times than the original.
So actually, if I talk about the area, so we are not throwing much area. All are very small sizes transistor we have added. Yeah, so there will be around 30% of area has been increased compared to VLSA. But if we compare with the STSA, there's not much change because that is already intact. The biggest part is the capacitance that takes a lot, but we are using reusing that, which is already present in our memory because of negative bit line writer scheme.
So do you have any analysis on what is the memory, what is the area overhead for?
So there's no area overhead if I compare with the STSA, but with with the VLSA, which is a very conventional one, 30% of area overhead is there.
Okay. So any comment on the complexity for generating the negative boost circuit?
Actually, negative boost circuit is actually very widely used. That is already silicon proven. We are using that for our negative writer assist scheme, negative bitline based writer assist scheme. Also, for that particular scheme, we normally generate more than 200 millivolt negative voltage. So because of that, I have restricted my analysis up till 200 millivolts. So that is very faithfully, even on silicon it's proven, and that too with a smaller attack nodes also, like 5 nanometer, 3 nanometer also it's working.
Thank you, session chairs, for conducting it wonderfully and more importantly on time. So, as a token of appreciation from the organizing committee, here is a small memento for this session.
Like our first paper in the 6A session is titled Transport-Free Placement of Mixers for Realizing Bioprotocol on Programmable Microfluidic Devices. Authors are Mastaka Hirai, Devraj Kundu, Shigeru Yamashita, Sudeep Roy, and Hiroyuki Tomiyama. So the presenter will be like Devraj Kundu. Like he received his bachelor's degree in computer science from Maulana Abdul Kalam Azad University in 2014, and a master's in computer science from University of Calcutta in 2016. He's pursuing a PhD from IIT Roorkee, and his current interests include algorithms for computer-aided design of advanced microfluidic biochips. So please welcome Debraj.
Thank you, Mr. Kochuri, for the introduction. I'm going to present our paper, Transport-Free Placement of Mixers for Realizing Bioprotocols on Programmable Microfluidic Device. So the agenda will be, first I will give a short overview, then I will discuss the background and the proposed methods, and finally the results. So here is a very short overview which says that programmable microfluidic device is a very new platform in microfluidic biochip where mixing is a very important problem. And it has achieved, like our paper has achieved 58.93% reduction in the number of flushing. And in the subsequent presentations, in slides, I will discuss what is the importance of this parameter actually. So here is an example of PMD at the extreme right. It is a grid of cells. It is a network of control channel and flow channels. So the problem here is, as you can see, there is a graph, sequencing graph, which is referred as mixing graph. It is a sequence of mixing steps, and the objective is to map these nodes, each of these nodes, into that PMD chip. However, this PMD device, programmable microfluidic device, has a limitation. What is the limitation? You see, if some fluids is in between the cells, and we need to transfer the fluids from one set of cells, from a set of cell to another set of cell, then we cannot achieve that with accuracy. So during the placement, we have to come up with new ideas such that we don't require any transportation of fluids at the intermediate step. And this paper actually focused on this objective. So here we can see how the chip works. At the extreme top right, there is the input, and at the extreme left, there is the output, and the fluids can be transferred from one cell to another cell. Before this work, there is only one work which tries to have the same problem statement. The work is titled as No Transport Mixing, and it also aims to map a mixing graph into PMDs such that there will be no requirement for the fluid transfer. However, these mixing modules can be realized as array of cells. For example, this paper, NTM, they have considered only 2x2 mixers, 2x2 grids of cells to As you can see, their 2 by 2 cells has been considered for a mixer, and a sample and buffer can be mixed to get any particular ratio, concentration. Another important problem while mapping a graph into, mixing graph into a PMD is that we need to flush out some residual fluids to give the space for the new placements. So, and we refer this operation as flushing. In this work, we proposed, along with like 2 by 2 mixers, we also says that a 2 by 3 mixers can also be placed, can also be mapped in PMD, and maintaining the same constraint, that is of no transport mixing. So the advantage of 2 by 3 mixer is that PMD actually can, in PMD we can realize different kind of mixers, like 2 by 2, 2 by 3, 2 by 4, maybe 3 by 3 kind of mixers are also possible. However, mapping of those modules into PMD is a very hard problem. So here we have considered 2 by 2 and 2 by 3 mixers only. The heuristic function that we have considered for the placement priority is shown here, where for a given mixing graph, we are defining this priority value for all the nodes. Considering this equation, where, for example, here M2, for M2 node, we need to calculate the priority of M2 considering the all the child nodes in its subtree. Okay. Here is an example. First of all, I need to say, like, for a given sequence graph, we need to transfer that graph based on the placement value, the priority values that we get from that equation. Maybe M1 can be implemented first and then M2, but based on the priority values, here we can see M2 will be placed first, then M1. So at first, at the central position for the root node M0, we will assign a place. Then for, we know that from M2 and M1, 1 unit of fluid has reached to M0. So we will assign M2 and M1 correspondingly at those locations. Next, the child nodes of M2s are M5 and M6, but we can't place both M5 and M6 directly. So we first place the M5 module, and for the similarly for the child nodes of M1, which is M3 and M4, we are placing only M3. After that, we perform the mixing steps, and then we know that M2 requires M6, 2 units from M6, and also M1 requires 1 unit from M4. So we flush out those regions of M3, of M2 and M1, and then load the reagents required for M6 and M4 correspondingly, and then perform the operations. And then we backtrack and perform the mixer operation for M2 and M1, and finally we will perform the mixer operation for M0. So as you can see, if we place the modules in this way, there is no requirement to shift the intermediate fluids from one location to another location, and hence the objective can be achieved. Here are some results. I have considered, like here I have shown a subset of the results as in our paper, from our paper. So here 20 test cases have been chosen, 20 random target ratios, and for each target ratio we have prepared two different kind of mixing trees. One mixing tree which contains only mixer size of 4, which corresponds to 2 by 2 cells, and another mixing graph with 2 by 2 mixers and 2 by 3 mixers, that is 4 and 6. And then compare the method with the only existing method, that is NTM. And we can see on an average, the number of mixing operations has been reduced to 5.49%. And as I shown in the first slide, that the number of flashing, why this parameter is important. In the previous slide, I show that the number of mixing has been reduced. Actually, that will be helpful for scheduling purpose, and it also reduces the overall time. And the number of flushing, actually, in case the number of flushing increases, then the valve actuations will be required more, and also the valuable biosamples will be required more. So if we reduce the number of flushing, all these benefits can be achieved, and we can see on an average on these 20 test cases only, we can see a 58.93% reduction in the number of flushing. So in conclusion, in this work, we have considered both 2 by 2 and 2 by 3 mixers for PMD placements, and we can see that with the help of incorporating these 2 by 3 mixers, we can reduce the number of flushings a lot. Thank you.
Can you tell me what's happening in the test case 9, where the number of flushings have sort of spiked?
Can you show the slides? This one of the
Next
number
one,
of flushing,
yeah.
right?
Test case 9.
Yeah, test case 9. So what happens, as I said, for each test case, for each test case means for each target ratio, I have prepared two different mixing graphs. Okay, one mixing graph which contains all the mixing nodes of size 2 by 2, and another mixing graph which has both 2 by 2 and 2 by 3 mixing nodes. So the internal structure of the graph can be in such a way, like in the previous case, like with only 2 by 2, maybe it is very even. And while for the 2 by 2 and 2 by 3 mixing graph, the structure, the internal structure of the graph is very complex, relatively complex, and that affects the placement actually. So for the test case 9, we clearly the structure of the mixing graph with only 2 by 2 nodes is simpler. That's why we can see that the number of flushing required is less in that particular case.
And the second question is, most of these things would have been some sort of a simulation that you would have done, right?
Yeah, yeah.
So would it make sense to sort of also try some other ratios, like instead of 2 by 3, maybe 2 by 5 or something?
Yes, yes. As a matter of fact, our group and I'm also trying to incorporate, like to make this a general problem, like to make N by M mixers. But the problem is very similar to tiling problem. If you can understand, like we need to place different size of rectangles in such a way that they share the boundary in such a way that we can perform the dependency mixing operations also. So tiling problem itself is a NP complete problem, NP hard problem as far as you know. So then again, the problem is more tougher, harder, because of the dependency information also needs to be taken care of. So I'm actually working on that, but till now for the heuristic purpose, heuristic method, this is the work that I have achieved. But to make it general, I'm working on it.
And was it possible to sort of, divide? I mean, so clearly here you agree that at least for one particular test case, the number of flushings with 2 by 2 was better.
Yeah, yeah.
So is it possible that this is something you could pre-compute, of course, you could pre-compute number flushing and
Yes,
then
that's
decide.
why in our paper we have shown another results with only average results of 500 test cases, and we see that on an average for 500 test cases, incorporating 2x3 mixers shows better result. But here that's why I have shown this particular plot to get understand that for some cases maybe 2x2 mixers graph will be beneficial. But on an average for 500 test cases I have shown that the average on an average incorporating 2x3 mixers is beneficial.
From a power function, how do they compare?
So, sorry, can you please?
You've shown the efficiency from a flush perspective, but how about from residual droplets or basically power functions? How do they compare?
There are other parameters also, like we may consider about the reliability of the chip. That can also be an important parameter, but the overlapping number, the number of overlappings that can happen, those are the parameters can be considered. But here I have shown the flushing as one of the most important parameter, as because it will affect the reliability of the chip, as well as it will more number of valuable fluids will be wasted if the number of flushing increases. So that's why I have focused on this particular parameter. Does my answer suffice your question?
So you have not yet looked at those parameters, or that's your future work?
Sorry?
Is that your future work?
Actually, in this paper, I have shown the overlapping parameter, the number of cells overlapped, and because more the number of overlap, more will be the degradation of this biochip because of the more number of actuations. In the paper, I have shown that, but to make this presentation simpler, I have focused on this parameter only. But there are other important parameters which I am working on.
Any more questions?
Is it on? Yeah, okay. The next paper is titled Efficient 3D Modeling Methodology for High-Speed Channels. The authors are Shivalingam T, Desmond Tan Hai Peng, and Suresh Kumar Kopparthi. Little bit bio on the presenter, Suresh Kumar. He has been working as a senior engineer at Microchip, and his interests are on FPGA BU, exploring on cutting-edge technologies. He has been working for the last 9 years. The EMC, SI, PI domains. Before Microchip, he worked at Visteon, InnoSmarts, ECIL, and Powertronics. He developed intelligent, innovative, smart energy metering ecosystem for India market. His background is basically has a bachelor's in ECE in 2013 from Bhimavaram Institute of Engineering and Technology, affiliated to JNTU Kakinada. Thank you. I welcome Suresh.
Hello all, good afternoon. Today I would like to discuss here about efficient 3D modeling methodology for high-speed channels. So coming to the agenda, introduction, how the printed circuit boards are spread across the domains, and what does it consist of, and what methodology, what model should be required for this efficient 3D modeling methodology. And also, when we do the full system simulation, we do face some challenges. What challenges are we facing? That can be discussed in the challenges on full system simulation slide. For that, we took an example called twin stripline channel. And for that, we measured and simulated so how that setup looks like. And to prove this cascaded methodology, we did some modeling and analysis. For that, we made measurement and simulation correlations. And so we took an example, we went a step ahead further. We took one S parameter model from the library, as a plug and play. We improved the version of RF launch by using the cascaded model from that library and how that goes, and conclusions followed by the questions and answers. So introduction, so printed circuit boards are spread across all the domains, industrial, automotive, consumer electronics, networking, and defense electronics and all. So for a digital system to operate and transmits at high-speed data rate, the system designers must ensure that the signal between to and fro must be good in quality and integrity. So for a digital system that operates and transmits, it consists of single or multiple PCBs and numerous vias, several connectors, and active or passive components and ICs to ensure that the signal from one end to the other on the PCB without ringing, crosstalk, distortion, signal noise, power supply noise. So we should do some advanced integrity analysis that is needed. So this analysis can help in understanding and characterizing the system for optimal performance. And also, in this case, wave theory comes into picture, and scattering parameters, nothing but S parameters, plays a prominent role. So S parameters are very prominent role for PCB simulation and verification. So when we do full system simulation, we do face many challenges that can be addressed in the next slide. So, hey, when we are trying to do full system simulation, we have to characterize right from the stack up dielectric material, different ICs, different impedances, different traces, different connectors, different wires. When we try to do everything together, it makes a lot of time, which takes a lot of time and computational resource and a lot of bandwidth. So our goal is to reduce the time. The way how to reduce the time? How to be parameterized. That is how our effort into doing this methodology, efficient 3D modeling methodology. So, so we took an example called twin stripline channel, where the test structure board, which is built up with 14 layers, and it's a 2-inch 100 ohms, 4 RF SMA connectors, which are laid on the top to the layer 3, and the test structure has wire diameter with 8 mil dia and 50 mil as anti-pad, and the back drill which starts from layer 4. So the RF connectors performance specification which starts from DC to 50 gigahertz, and the insertion loss is less than 0.8 dB, and the insertion loss is less than 0.8 dB, and the return loss is less than 10 dB. So in the right, we can see similarly a 3D model was created in HFSS 3D layout with RF SMA connectors as HFSS 3D component. So for this twin stripline channel, we can see in the next slide measurement and simulation setup. So this is called measurement setup, the left side. The measurement setup consists of 50 gigahertz vector network analyzer. So vector network analyzer is used to measure passive interconnect features, and the coaxial cables are connected between VNA to the DUT, device under test. So VNA, which requires calibration, that is nothing but ecal calibration. Once the ecal calibration is done, it is able to calculate and measure extract the S parameter model that is stored in either in a VNA format, native format, or touchstone model. All these models and all extracted, like taken over the PLTS test system, nothing but physical layer test system. The post-processing of these models, PLTS, taken over from the VNA native format or touchstone model format, that can be processed for the insertion loss, return loss, and time domain reflectometer parameters. The extracted S parameter models are benchmarked for passivity, causality, and reciprocity. And when we see in the right side full model simulation, this is all we are talking about. This is what we are doing it right now. This is this is all everybody doing as per the industry norms, which takes a lot of time. So here we can see the full model meshing. It is not applying any cascaded methodology. It's a full system simulation, which takes 7 hours to finish this simulation. Whereas when we are applying the cascaded methodology, what we are going to propose, so that takes only 45 minutes to run the simulation. So in the coming slide, we can see the more analysis. So our methodology is efficient 3D modeling methodology for the cascaded model for the high-speed channels. So here we can see 2-inch RF SMA connectors. So it needs to cut into 3 sections. The first half-inch is 0.5-inch SMA connector, and the second half-inch is 1-inch tripline differential pair, and the third half-inch is half-inch SMA connector. The first half and the third half are same SMA connectors required to solve only once. Those models will be stored in the library, and the 1-inch differential pair is stored in the library. So these models, first half and the second half and third half, so all together we can use it for 2-inch, 4-inch, 16-inch, 32-inch. Wherever we need for our interface purpose, we can reuse the models, nothing but the experimental models. So these individual experimental models can be cascaded using the dynamic link, using the HFSS to the right side of the circuit environment, where the 4 ports are getting connected, port 1 and 2, 3, 4. So this methodology, using this methodology, I can use connectors, I can reuse the different traces, I can reuse the connectors, I can use the different wires for that required stack up. So using this methodology, we can save the time and computational resource. So hence, a lot of bandwidth also can be saved. So in the next slide, we can see the what and all objectives of this cascaded model. Our objective is to reduce the time and reduce the simulation time as well as the computational resource. Through that, we can increase the more number of simulations in less time. We made some correlations, measurement and simulation correlations for this 2-inch tripline channel. So here the measurement, it's a full model versus measurement. So full model, here we can see the 2 plots, like the blue one is the measurement one and the full model one is the gold one. So the full model is nothing but without using any cascaded model, just we did full simulation, full SMA to SMA simulation. So which takes 7 hours to finish the simulation. Whereas the measurement one, we fabricated the one printed circuit board with 14-layer board. For that, we made some measurement. So here we plotted between full model versus measurement. So right side we can see the insertion loss and the TDR plot. So here good agreement between both full model versus measurement. And also we can observe TDR at close to 100 ohms at 450 picoseconds. It's a 2-inch trace and which comes around 340 into 2. And coming to the measurement and simulation for the cascaded versus full model. So here the red color is the cascaded one and the gold color is the full model simulation. So here we can see it's a good agreement between the full model versus cascaded model. The results are pretty accurately aligned over the cascaded model with full model. We can see here the 2 plots, insertion loss, return loss, and the TDR plot. We can see the TDR is also exactly aligned on the full model. So here, full model required to finish the simulation, which is about 7 hours, whereas using the cascaded methodology, we can finish it in 45 minutes. In the coming slides, we can see some more analysis. So as we discussed in the previous slides, so here we can compare between the cascaded model, full model, and the measurement model. So we can see the plots, like the full model is in the gold color, cascaded in the red color, and the measurement is in the blue color. For the return loss, insertion loss, and TDR, all are pretty aligned. So all are accurately aligned. So, and this is improved version of RF launch. This is improved version of RF launch. So here, what we did, from the cascaded methodology, from the library, just we plug in the S-parameter model, we just analyzed and optimized a single model for a better results. Here, the improved version of RF launch, in our board, 4 SMA connectors are there. We took only one RF SMA connector using the using the cascaded methodology. From the library, we just plug in the model and we optimize the result and applied for the different SMA connectors. Through that, we saved time. We achieved with very less computational resource. So in the coming slide, we can see the analysis part. So here, which are simulation results for the like the original model versus optimized one. Here we can see the difference, like how we accurately simulated the model using cascaded methodology and applied on the board and achieved the result. This is all about what we are proposing, cascaded methodology for reducing the time. In the next slide, we can see on the conclusion. So using this methodology efficiently, we can solve the full system simulations with reduced efforts, like with less computational resource. Through that, we can achieve with limited bandwidth, we can achieve the results. This is all about efficient 3D modeling methodology. Yeah. Thank you.
Not, I have one actually. So with respect to the tool support, this cascaded methodology, there is wide tool support?
Yeah. It can support all the tools.
Oh, okay.
Where we can extract S-parameter model.
Okay.
So wherever we get S-parameter model, which supports all the tools. So. Thanks so much.
Our next paper is an improved slicing pair code for skewed slicing floor plan. Authors are Biswajit Nayak and BNB Ray. And our presenter is Biswajit Nayak. And he's currently the assistant professor in the Department of CSA at Utkal University, Bhubaneswar. And prior to this, he worked as assistant professor in the Department of CSC at GHIM, Puri, and currently pursuing PhD in the Department of CSA at Utkal University, Bhubaneswar. He received master's degree from NIT Roorkee, Roorkela, and a BTech degree from VSSV UT, Burla, in CSE. He cleared UGC NET in 2015 in his first attempt. He has published more than 5 papers in reputed journals and conferences. He's a member of IEEE and a life member of CSI. His current research interests include VLSI physical design, network security, and machine learning. He delivered more than 10 invited talks at different colleges and universities. So, welcome, Mr. Biswajit.
Thank you, sir, for introductions. So, today, my presentation is on improved slicing pair code for skewed slicing floor plans, and these are my agenda. So first we'll discuss the overviews on these problems, then we'll move to the problem statement, then what is the scope that available with the existing work, then we'll move to the methodology, then result, then finding, lastly we'll conclude this. So let us first understand what is floor plan. This floor plan is one of the problems on VLSI physical designs. And generally what happens in floor plans, we are finding, or generally it is used to design the layout of very large scales integration circuits. And in floor plans, it is we are doing horizontals as well as verticals partitions onto the chips to get smaller chips so that we can fit the rectangular blocks on the chips. Okay. So there are two types of slicing floor plans. One is, there are two types of floor plan. One is slicing floor plan, another is your non-slicing floor plans. So in case of slicing floor plans, we are recursively partitions the rectangles into horizontals as well as verticals. Okay. So, but in case of non-slicing floor plan, we cannot partitions. So in the tops, so there are two figures. So the top left figure is non-slicing floor plan. So here there is a wheels. In block 2 there is a wheels. So and the top right figures, that is a slicing floor plan. So my problem, so here we have proposed, whatever we have proposed is code for slicing floor plans. Okay, so then this slicing floor plan we can represent into by using a binary tree that is called your slicing trees. Okay, so that slicing trees is nothing but it is based on the codes. All the internal nodes are we are representing, so using star as well as plus. Star for vertical partitions and for plus for horizontal partitions. Okay, and all the leaf nodes are our blocks, electronics blocks. And that for a particular floor plans, there may be have many slicing trees, so that it is very difficult to optimize the VLSI floor plan problems. So later on, Wang and Liu propose a slicing trees that is called your skew slicing trees. So in skew slicing trees, the parents and the right childs should not have same operators like plus plus or stars. And if it is present, then that is called your non-skew slicing trees. Okay, for skew slicing, see, both parents and the right children have opposite codes or opposite partitions. Okay, so there are different types. So there are several problems that already proposed on skew slicing trees. That is coding problems. Two are the best first code. Another is your slicing pair codes. Okay, so this is my problem statement. Generally, my problem statement is based on your slicing pair codes. That is the existing work. So here we have designs a compact code here. So to represent this skew slicing floor plans, that uses less number bit as compared to the existing work, that is BFS code as well as SP codes. So our work is generally based on your slicing pair codes. So let us first understand what is slicing pairs. So slicing pair is nothing but it is a set of vertices or pair of vertices. They have same parents. Okay, so here in the top figures, it is represents or it is shown by using oval, that is the slicing pairs, and the bottoms tables that generally it is a slicing pair codes. Okay, so for the first columns here, there are two possible operators or two possible parents, that is plus or stars. So for a particular parents levels, there is a 6 possible slicing pairs. So here it is in the second column it is given, second column for the operator plus, there are 6 possible slicing pair, or star also have 6 possible slicing pair. And this slicing pair code assigns some bits. There are two group of bits they have assigned. One is for 3 bits that start with 0, and another set of bits they have assigned that start with 1, and it uses 2 bits. Okay. So since the VLSI's circuits is gradually increased, the density of this circuit is gradually increased, so that the number of electronics blocks is increased, so that it is when we are representing that electronics blocks, so that we require a compact code to represent. Okay. So that we have proposed a slicing pair codes. So that is based on your slicing pair codes, and that is compact as compared to the SP codes. Okay. So this is our proposed solutions. So it is same as your slicing pair codes. So the right-hand figures, so these are the slicing pair. It is represented by using ovals, and here we have changed the assign bit here. Whatever bits used for the each slicing pair, we have changed here. We have three group of bits here. One is taking 3 bits, and another is taking 4 bits, and last one is taking 1 bits. So generally in a slicing floor plan, they are using 2 group of bits. One is start with 0, that is having 3 number of bits, and another is some set of bits that start with 1, and they are using 2 bits. But here what, as the number of electronics block in VLSI circuit has gradually increased, so that here we are trying to minimize the number of bits that uses the blocks. So here, if you see the second columns, the slicing pair is LL. So that here what, when the number of blocks in VLSI circuits is increase, then your number of this leaf node also increase, because we are representing this leaf node by using blocks. Okay, so here we'll generally we'll try to minimize the number of bit in LLs, leaf nodes or blocks. So that is the difference as compared to the SP codes. So here we have used 3 group of bits. It's first 2 group, it is start with 0. And here, if it is first 2 bit is start with 0, 0, then we are reading next 2 bits. Then if it is 0, 1, then we are taking another 2 bits. And last slicing for pan, that is LL. So here we have used only 1 bits. So this is encoding algorithms. So first, this encoding algorithm, it will take the root of the skew slicing trees as inputs, and it will generate the encoded strings. So after taking the root of the skew slicing trees, so first it will encode the root bits. So root bit is, there are 2 possible bits, either it is plus or stars. So for plus or stars, we can represent by using all 1 bits, that is either 0 or 1. So here we have used 0 for plus and 1 for star. After that, rest of the slicing pair we have encoded by using a data structure, that is Q data structures. So here it is in line numbers, it is 8. It is initially we are inserting the root of the skew slicing tree into the Q data structures. Then after that, there is a encode functions. That encode functions will generate the bits, encoded bits of the current slicing pair for whatever the root slice. For first, initially it is for roots. What is the left child? Based on the left child and the right child, it will generate your generally what slicing pair is our children of a particular parents. So it will, by using that, it will return the code for the slicing pairs. And after that, we will dequeue the front of the queues. Then we are inserting the left child as well as right child into the, and this process will be repeated until the queue is not empty. And in case of decode algorithms, here first, this decode algorithms, it will take input as encoded strings, and it will generate the slicing pairs vertices label wise. So first bit is our root bits, either it is 0 or 1. So for plus, we have, so if it is 0, then we encoded so we decoded as a plus operator. If it is star, then we decoded as star vertex. So after that, rest of the bits were encoded by using these steps. If the bit is start with 0, then in case of if bit is start with 0, then we are reading 2 bits, then we are deciding. If it is 0, 0, then we have to read another bits after this root bits. If it is 0, 0, 1, then we are reading another two bits. So based upon that, we are deciding whether who is slicing pairs for a particular parents, which slicing pair is this. And if it is 1, if parents bits followed by the next bit, if it is 1, then it is slicing pair is LL. Okay, so this is our results. So we have compared this proposed coding techniques by using BFS code as well as SP codes. So in the first columns, we are generally taking a random slicing trees by different values of n or different number of blocks, and we'll find out the code of BFS code. In the second column, it defines the length of BFS code, and third columns, it defines the length of SP code, and last one is the length of ISP code or proposed code. And if you see the last row, so here we have normalized with respect to the proposed solutions, and finally we'll got that this proposed methods or proposed coding techniques is better, 49% better than BFS code and 20% better than SP code. So this is our graphs. So x-axis define the number of blocks, and y-axis define the length of bits that using for different schemes. So green line is for ISP code, and blue is SP code, and the red line is your BFS code. So here from this graph we are finding that your ISP is or improved slicing pair code is better than the other BFS and as well as SPS code. So from this experimentally or our theoretical finds showing that the SP code on an average we are getting 49% as well as 20% better than BFS as well as SP codes. So this is my conclusions. So since the VLSI circuit is extremely large, so it is necessary to design a compact representation of floor plans, as well as this we have also proposed this compact code for encoding skewed slicing tree of floor plans. Also we derive an expression for the length of ISP code, and also will prove that the skew slicing plan, the real length of ISP code less than the SP as well as BFA code. So and last one is our future work. We would like to design a compact code for non-slicing floor plans. These are my references. Thank you.
The result slide. Go to your result slide.
What's, sorry, slide?
The result slide. Where you showed the number of leaves.
Which slide?
Results. Showed, can you go to the slide for that? Yeah, so here, right, you have shown the increasing number of leaves, right? So what was the test case here in this, each of this? Was it the same test case that was partitioned multiple times, or was it different? So you have shown number of leaves differently. So what was the test case here? Was it the same test case that was partitioned multiple times, or was it a different independent test cases?
So actually we are generally randomly choosing the test cases. So by taking different skew slicing trees, initially we will generate the post-order traversal of skew slicing tree. From that post-order traversal, we randomly insert the operators. So after randomly insert, there is a condition that the number of whatever the positions we are getting are the random number generations. The left sides should have less number of operators as compared to the whatever at that positions. And after that, from that post orders, we'll convert into infix conversions, and from that we'll check whether it is a skew slicing tree or non-skew slicing tree. So based upon that, we are calculating the length of the codes by using BFS as well as SP code and ISP.
So when you calculate these, right, so there are other parameters that go into the floor plan, area, connectivity, and all that. And you shown a binary tree, but it's never really a binary tree, right? So how do you account for these variations?
So actually this floor plan designs, here we are not focusing on the areas here, sir. So initially a floor plan is given. From that floor plans we are representing by using coding techniques. We are generating a codes for that floor plans.
The bottom up,
Sir?
The bottom-up approach.
Sorry, sir.
The bottom-up approach, where your already floor plan is defined for the leaves. That
Yes.
And Samir Himadri. So the presenter is Raghavendra Nayak, sorry. Raghavendra Nayak completed graduation from KLE Technological University, Hubballi. He is currently working as an AMS engineer in Infineon Technologies. Welcome, Raghavendra.
Hi, everyone. Thank you, Sai, for introduction. Here I am presenting our paper on maximum power point tracking using buck-boost converter for EHPMIC. In this presentation, I'm going to talk about the overview of the paper, problem statement, scope of the work, proposed solution, and in that only I'm going to compare with the traditional solutions that we have, and then the methodology of complete implementation, then brief about results and conclusions. And coming to overview, like when I say maximum power point tracking, the first question comes, what is MPPT? That is the short form for maximum power point tracking. And in that, what is MPP? Maximum power point. Maximum power point for any energy source is nothing but a operating point of that energy source at which we can extract maximum energy from that source. And then what is the challenge when we are handling maximum power point tracking with PV cells, photovoltaic cells? In photovoltaic cells, the maximum power point is not constant, or it's not it varies a lot. It varies with the climatic conditions like intensity that is falling on the PV panel, the shades, and many other conditions. Then here is the problem statement. Problem statement is mainly to design a circuit, a complete analog circuit for tracking, that means finding the maximum power point of a PV cell, and also to implement that operating point on the PV cell. So these are the specs that we have used. The Vin is from 0.5 to 3.6. If you see here, the input voltage, which is nothing but the output of PV panel, is varying a lot, from 0.5 to 3.6. And also our voltage is varying from 1.3 to 3.5, which is the output of our MPPT. This is again processed using a EHPMIC that I am going to talk next. And we are targeting for an efficiency of 85% for a maximum input current, which is the output current of PV panel. Here all the specs are with respect to the MPPT circuit, not the PV panel, which is, whenever I say input to the maximum power point tracking circuit, that will be basically output of PV panel. So IIN, which is nothing but output of PV panel, current will be maximum 18.5 milliamperes. So we are targeting for a 10 microampere quiescent current, and when shut down MPPT, we are trying for a 250 nanoampere shutdown current. So here is the scope. Like EHPMIC, when it comes, it is a big block which contains maximum power point tracker and many DC-DC converters to process the output of it. So MPPT sits as the heart of EHPMIC. EHPMIC is nothing but energy harvesting power management integrated circuit. So MPPT is the heart of it, because whenever we are talking about energy, major task will be of extracting the energy. So MPPT does the task of extracting energy very efficiently. So EHPMICs are used in wide applications nowadays, like remote applications, wireless sensor nodes. Then going to methodology, in traditional maximum power point trackers, people use like direct output of PV panel current and voltage, and then multiplied it and then obtained the power output of PV panel and use the complex loops to identify the maximum power point and set it on it. So, but what we are proposing here is like we are not obtaining the value of power value of PV panel by calculating current and voltage, because as we know, detection of current is a difficult task when it comes to in-circuit implementation, and that is also like it consumes a considerable amount of power. So for that reason, we avoided finding current and voltage and then using multiplier. One more complexity which comes is implementing a multiplier in analog circuit, which will be not much linear and many other complexities will come in. And because of that, the output will not be very accurate. So for that reason, what we have used is instead of detecting the power from PV panel output side, we are detecting the power from the complete MPPT output circuit side. So if you see the circuit diagram at the bottom, there we are not detecting the power or current and voltage of PV panel. Instead, we are detecting the current of buck-boost converter, which is as a part of MPPT circuit. So we are detecting the output current of buck-boost converter, and that indirectly tells us what is the power that we are extracting from the PV panel at this current point in time. So we are using that data and processing that data using two-loop circuit. This is a two-loop circuit. One loop is tracking the maximum power point, and the second loop is setting that voltage as a PV panel reference, PV panel operating point. So this is a circuit in which we have shown the implementation, which you can see that PV panel's output is taken into input for a buck-boost converter, and inside buck-boost converter, it is a buck-boost architecture, I would say. It is not a regulating buck-boost converter. So that is the output of that buck-boost architecture, the power part of the buck-boost converter is used, and the output current of that part is used, calculated using a current finder. One more point here is like calculating the current output of a buck-boost converter will be quite easier compared to directly calculating the current of PV panel, which I said is a power consuming as well as a tedious task. Because buck-boost converter will include a diode, in which we can directly copy the current of diode and get that information readily available. So we are using that current data and we are sampling it. We are delaying that data because what we are implementing is a perturbed observe method of maximum power point tracking. For that purpose, we need data of current power and the power which was there in the previous time interval. So for that data, we are doing a delay. We are using a delay block, which is analog delay block. So that is implemented using a sample and hold circuit, and we are using these two data, the previous data, which is the output of sample and hold circuit, and the current data, which is directly calculated from the current of buck-boost converter. And we are comparing these two and feeding into the loop. That loop consists of comparator and some digital part, which consists of XNOR and D flip-flop, and that is fed into a charge pump. And this output of charge pump will be detecting the maximum power point voltage for us. So this voltage is taken into a PID controller and then PWM generator. So using these two, we are connecting it back to the buck-boost converter. And this buck-boost converter, when we change the duty cycle as per the VMPP that we have calculated from our first loop, we will be getting proper duty cycle to adjust that point on the PV panel. So because of that, this buck-boost converter, as I told, it's not a regulating buck-boost converter. It is just the power part of the buck-boost converter. So when you change the duty cycle of buck-boost converter, the input impedance of the buck-boost converter changes. Because of this change in the input impedance of the buck-boost converter, the load on PV cell changes, and PV cell will make sure that it will be working at the maximum power point. For that reason, we are also reading the voltage, PV panel voltage for the PID controller and feeding it back. So this PID controller and PWM generator in that part of the loop will make sure that PV panel's output voltage is set at the maximum power point voltage, which we have detected at the earlier part of the loop. Then going to result, to get the result, here we have modeled the PV panel using its equivalent model. We didn't calculate the PV, we had the data of actual PV panel and we modeled that PV panel, and that photovoltaic cell is modeled and that data is simulated to get what our expected result should be. So for that reason, the above diagram shows the equivalent model of the PV cell, and that below diagram shows the graph of power and voltage of that model of PV model we have used. And we have simulated this PV model across different conditions and then use this data as a reference data to check how our actual design is working. Yeah, coming to results, we are obtaining, as I told, we are using the model output, the simulation of model as a reference golden data, and comparing that with the actual result, actual circuit implementation. So here we can see that the actual MPP that we have calculated from model or simulated from model is 1.6 volts at 1.12 milliamperes of PV panel output current, but we are getting as a 1.52 from our circuit. This, there is a slight variation, but I'll tell you there is reason for this variation. And also we have taken one more point, which is at 7 milliamperes output current of PV panel, at which we are expecting 1.5 volt as the maximum power point voltage, but we are getting 1.3 volts, which is considerably varied because it is 13% variation from the golden data, reference data. So that I will talk about that variation, why that variation is coming in further slides. And if you see the diagram, the waveforms of this right side waveform show the corresponding waveforms for 12 milliampere and 7 milliampere PV panel current. And we are seeing a variation in that PV panel, that waveforms. That variation is a common part when we implement perturb and observe algorithm. Perturb and observe algorithm will detect the old point and current point, and because of that, that variation will be unavoidable in P and O algorithm. So here in the diagram, we can see the charge pump capacitors output here. Charge pump's voltage is half of the actual voltage which is set on the PV panel because we are using a voltage divider there. And the last curve shows the output of MPPT circuit, which is charging a storage element. In our case, it's a large capacitor. So it is charging the capacitor very slowly. Like it is slow because the capacitor is huge and the PV panel's energy is very less compared to the storage element that we have used, and simulation time is also just 5 milliseconds. So this graph shows the brief comparison of reference data with the simulated, implemented, the results obtained from our circuit. So here you are seeing at low power, low current inputs, that is 7 milliamperes and low, we are seeing a more variation as compared to variation in the higher current states. So this is mainly because we are not detecting the power of PV panel directly. Instead of that, we are detecting the power at the output of buck-boost converter. And at lower current stages, the buck-boost converter's efficiency will change and there will be internal consumption of the circuit. There is, as we have seen in the previous circuit, it's a quite big circuit for the current that we have. So because of that, at lower currents, the consumption, internal consumption will be significant higher compared to the higher load conditions. So because of that, there will internal consumption and nonlinear efficiency of buck-boost converter, we will be seeing some variation at the lower power, low current situations. But this is common feature in most of the MPPT algorithms. I would not say in all, but in most of the MPPT algorithms, because any MPPT algorithm, if we take, there will be internal power consumption and it will be taking out some power. Because of that, the power data we will be getting is not that accurate. And coming to conclusions, our loop is delivering buck-boost. We are using buck-boost converter, as I already told, which is, again, I'm repeating, it's not a regulatory buck-boost converter. The output of that buck-boost converter's power FET will not be constant. It will be varying as per its major target is to set the duty cycle in order to set VMPP on the PV cell, not to regulate the output. For regulating the output, we have other DC-DC converter which is regulating that output and giving that voltage into the load or the system that we are driving with this EHPMIC. And as I already discussed, the variation is mainly due to the efficiency of buck-boost converter, and the golden data which we have simulated assumes that the buck-boost converters are 100% efficient across loading conditions, but that is never true. So yeah, that point I already discussed. Because of internal power consumption, we will be getting variation in power data, and because of that, we will not be, there will be more variation at the lower current conditions.
What's the reason for using buck-boost instead of just
Yeah, basically, if you see our specification table, we can see that our input voltage, that is output of PV panel, varies from 0.5 volts to 3.6 volts. And our expected output voltage of the MPPT is 1.3 volt to 3.6 volts. If you see this region, we cannot obtain this region of operation using either buck converter or buck-boost or boost converter, because as we already know, boost converter can only increase the voltage or buck converter can only decrease the voltage. But since because of because of this wide range of operation of our application, we have to use buck boost converter, otherwise system will not be stable.
The next paper is GRILAP, Graph Representation Inductive Learning Based Average Power Estimation for Front-End AC RTL Designs. The authors are Rakesh MB, Pavitra Das, Sai Pranav KR, and Amit Acharya. A little bit bio about the presenter. Rakesh MB is a PhD research scholar in the Department of Electrical Engineering at IIT Hyderabad. And he's also an assistant professor at Department of Electronics and Telecommunication Engineering at CIT Tumkur. He has a work experience of 5 years and is currently on a deputation to pursue the IIT program at Hyderabad. Welcome, Rakesh.
Yeah. So as we all know, like estimation of average power is one of the essential performance objectives for any of the designers to meet at the different levels of design hierarchy. So, and also we know that actually if you have to get the exact average power estimation, so for that we have to do the post-synthesis simulation, that is what we call it as the gate level simulations. So why that gate level simulation gives us the accurate average power estimation, as we know that we get the toggling activities of all the intermediate wires also over a period of clock cycles, if I'm going to talk about the average power estimation. Whereas if we just do the RTL simulation, in that case only we come to know about the toggling activities of the input wires. We don't know how much the switching activities or toggling activities that occur in these intermediate wires. So that we come to know only if we do gate level simulation. But for that case, actually gate level simulation, as we have shown in this the diagram, that takes more time. So in this one, what we have shown is that actually the if you're going there is an increase in the average power estimation accuracy if we go down in the design hierarchy, whereas there is a decrease in the average power estimation time as we go up. That if we just do the RTL simulation and if we let the tool estimate the average power based on its own propagation algorithm, so that case actually definitely there is increase in the speed of estimation of the average power, but that accuracy will not be there. Whereas if we do the gate level simulation, the average power accuracy will be higher, but the speed decreases. It needs more time. So based on that one, actually we have like challenges are like, one is that we estimating average power early at the RTL, as I said earlier, it increases speed that around 1,000, 10,000 cycles per second that we could do it, but at the expense of accuracy that we have it. Whereas if you're going to estimate the average power after gate level simulation, it definitely increases accuracy, but at the expense of speed. So designers always wish to achieve a balance between the speed and accuracy, so that actually they could achieve better turnaround time or the time to market. So based on that one, we set two objectives. One is to accurately estimate the average power of any of the new netlist file from the RTL simulation itself without doing the gate level simulation. And the second objective is to achieve the better inference speed up than the traditional flow, what the tool does it using the to get the gate level simulation. Yeah. So based on these two objectives, actually there were some existing researchers. One is the Primal, which is an acronym for power inference using machine learning. The another one is the Granite, so graph neural network inference for transferable power estimation. So these two researchers have made a table here, making the comparison between what their approaches are. The first one, what it does is that actually it takes the ground truth values, what they call it as the labels, what they provide for their machine learning tasks. They employed different machine learning algorithms. One is the CNN, the gradient tree boosting, and the one is the random forest also they have employed. So they achieved better average power estimation. For example, they achieved an average power estimation of error of less than 5% and speed up also of greater than 50x when compared to commercial gate level power estimation tool. Same thing actually, if I just look into the granite architecture, they did not go with the traditional machine learning algorithms where they went with the graph neural network, and one of the graph neural network they chose it was the graph convolution network. So graph convolution network, and the method remains the same thing. There also, they took the, they trained the model with the intermediate wire toggling activities which they get it from the gate level simulation, and they infer the average power of any netlist file from the RTL simulation itself. But there were differences, as I pointed in the second point. There, primal, they could actually estimate the average power from the different workloads, from the RTL simulation. In a sense, different workloads means they had to train their model with any of the new netlist files. So it required the training in the case of primal model. Whereas the granite people, they didn't require the training. Means if I am going to train for some 15, 20 circuits, any new netlist file which is not trained, that they could infer it. Whereas the primal people, they could not do that one. Any of the new netlist file also comes, they had to train that one also. So, but different workloads, why I mentioned, because the new netlist file, anyhow, for certain set of cycles, like 1,000 cycles, they could, they needed capture the toggling activities, whereas other 1,000 cycles, they did not have to train it again, so they could estimate that one. So that they could achieve it. But any first certain 1,000 cycles, they definitely required the training. Whereas granite people were able to do that one. Any new netlist file, they could take it. That's what I mentioned there. The primal requires training, which restricted the transferability. So whereas granite were able to achieve that one. But the two approaches, whatever the networks they used it, they were transductive in nature. So basically, if I talk about the primal paper, so primal basically they employed the node-to-wake embedding method, where it was transductive in nature, so they could not generalize to unseen nodes. I'll explain about the unseen nodes later. So GCNs are also transductive in a sense that also they required the presence of all nodes during training. Nodes in a sense actually in our case is basically the logic cells that we get, basically standard cell based ASIC that we are doing. So we get different logic cells. So nodes in a sense, they are logic cells. So yeah, so primal didn't require the, I mean, they were not able to go for the untrained netlist file. They were not able to infer the average power from the untrained netlist file, whereas the granite people were able to do that one. But still, actually, there was one disadvantage with the granite people. The thing is that actually there was a possibility of reusing the trained logic cells. Though what happens is that actually in the case of new netlist file also they could get that one. But there also there was a possibility of the same logic cells which were trained in the training benchmark list that they had it. So that one disadvantage was there, and that might introduce bias in the graph learning while testing the model for a new netlist file. So based on that one, actually we proposed the Grille methodology, somewhat different. Yeah, so we proposed the Grille methodology. Basically, it's an, as I said earlier, it's an acronym for graph-based inductive learning-based algorithm estimation. It's a supervised learning. Why it is supervised? Because we are, during training, actually, we are providing the toggling activities from the gate level simulation. So I will, why it is better than, there is a difference actually, I don't know why that difference is there in the PPT, that slide it has come out. Okay. So Grille is more generalizable when compared to the previous machine learning methods. The previous machine learning methods that we had it like primal and the granite, it is more generalizable in a sense, more transferable. Why? Because we have used an inductive GNN architecture. So we have used inductive GNN architecture based on the graph attention network, so which could actually generalize to newer nodes or unseen logic cells. Hence, it could remove the bias of using the trained logic cells and also requirement of training the new design. Training the new design was the limitation of the primal paper, and using the trained logic cells was the limitation of the granite paper. So we were able to overcome both these two limitations of the granite and the primal. So this is the training and the testing flow that I mentioned. Basically, we take the RTL designs, we synthesize, we get the netlist files. We convert to graph object using NetworkX and the DGL package. NetworkX helps in converting netlist file to graph object. DGL package helps in assigning these node and the edge features, which I'll explain later. And then we do the gate level simulation, get the gate level size and toggle rates of all the wires, we take it and we train the model. Whereas in the testing flow, we can see that one, we are just doing the RTL simulation. We are not doing the gate level simulation, thus conserving time of going through the elaboration process of doing the gate level simulation. And we just give the input wires only, and we estimate the toggling activities of all the intermediate wires of the entire the netlist file. So that then what we do, we get the toggle rates that we convert to SCI using a small Python code where we convert that SCI file, we give it to the tool to estimate the average power. Yeah, this is a GLAPE architecture. So GLAPE architecture, basically we have four, like the first layer, it maps the low dimension input toggle rates features to 128 higher dimension, just actually two different learn switching activity embeddings to represent. And GNN model, basically it learns, we have used it to learn the complex nonlinear relationship, because input toggle rates, logic netlist structure, and the output toggle rates, the relationship is nonlinear. So the last two FC layers, they map the high dimension embeddings back into the, just actually bringing down the dimensions from 120 to 16, then finally we bring it to 4 dimension. Then so that we have used all these first 3 layers, we use ReLU activation function since the relationship is non-linear. So finally we have used the softmax so that actually we bring, so that all the 4 dimension toggle rate features, they sum to 1. Yeah, this is the main important thing that is there in the case of features computation. What features that we have to give it to our model. So basically there are 3 things. As we know, the evaluation switching activity always depends on 3 things. One is the logic function, another one is the signal statistics, and the one is the correlation. So say logic function, we have represented in terms of the truth table. So from the truth table, we are calculating there that p underscore 0, what I'm showing there, that is basically n0 by 2 raised to n. n0 is the number of entries. So all those 4 values that we have computed, the p underscore 0, p underscore 1, p underscore sw0 to 1, p underscore sw1 to 0. That p underscore 0, number of zeros entries in the truth table, number of 1 entries in the truth table. So those computation, basically we have done it actually to cater to the logic function. And the edge features that we have computed to consider the correlation factor. Basically, as we know, these correlations, that reconvergent fanouts which occur in the netlist. So to cater to that one, we derive it actually from the truth table itself. And the netlist, the sample netlist that has been considered here, so that has been converted into graph. And the one thing that we have to take care is that any of the cell that we have, for example, the half adder cell, that is simple cell, that is being converted to, if it is, there are 2 outputs, one is sum and the carry. So sum and the carry that we have it, so that is split actually there in the graph construction, so that only one unique output is there. And the node and edge features, they are all embedded to the graph based on the DGL package that we have used here. And the wire toggle rates, we have run it for 1000 cycles, and when we have these SCI files or the gate level SCI files, we get 4 like T0, T1, TC toggle count. So toggle count we have split up into 2, so that actually we have like 4 dimensions. I'll skip those things. Yeah, this is the GNN message passing mechanism. GNN message passing mechanism, basically one thing that I'll just briefly summarize that one. Message passing mechanism, because we know that actually in the netlist file, whenever the values, the toggle rates have to propagate from input to the output, and it has to traverse through the netlist. So that it has to do it, then only finally after certain cycles we can estimate the average power. So input actually traverses through. For the traversing mechanism, we have employed this algorithm. So basically there are 3 steps. One is message sending, message reduction, and the node transformation. Message sending, we concatenate the node features and the edge features. So, and then in the reduction, we aggregate it. So finally, actually in the node transformation, we concatenate, and based on the weights that we have it, we update it in the using the small feed-forward neural network. So basically, the attention coefficients and all those things we that is calculated here. So Yeah, so the results we have it is the training and the testing benchmark circuits. So basically we have taken 19 benchmark circuits, few from the ISCA certified and then few from the EPFL and a few from the open course. Basically we are training all these things in parallel using DGL.batch. So that actually all the 19 circuits we have trained and also tested, making sure that actually no of the testing circuit is there in the training circuit whenever we do that one. That is tested basically in the K-fold validation. Yeah, so let me. Yeah, this is the novelty that we have it here. So basically, these are all logic cells untrained. So what these unseen logic cells means, because whenever like if I say, for example, some 18 circuits I consider for the training list, the another new circuit that is there in the testing thing, that any of the cells that we obtain after the netlist, it is not at all part of all the 18 circuits. So that we took care of it, and I have summarized all these cells of few few circuits. And in that one, what we found out was that actually our model Grillip was able to better estimate because of this inductive nature that we had, whereas Granite used that GCN, which was transactive nature. So average power, you can see that one 16.16 error is there, whereas the Granite had 30.52%. So only case actually with respect to MOA222D1 that is there, that probably that aggregation that they use it where the average one, not the scaling factor which we employed for the aggregation. So that somehow for only one cell. But average wise, we achieved a better results in predicting the toggle rates of all the unseen logic cells, which were never part of the training list. So which indicated that the inductive neural network that we employed was really very good. Yeah, so results of estimation of average power. Some of testing results, basically that toggle rates that I showed it earlier. This one is the average power that we estimated. So based on that one, we can see that one. Whenever we have estimated average power, the Grillip has done comparatively better than CRPT. Okay, CRPT is basically the tool, the commercial tool that we have used it. We give the RTL SIFE itself. That is not the no neural network, that is a tool itself. There we just give the RTL SIFE and its own propagation mechanism that it employs, so it was able to estimate the average power. As we can see, the CRPT was able to estimate the average power with an error of 29.65%, whereas Granite 7.65% and Grillip was 6.25% error. And in order to indicate that and show that actually whether we did perform better than the Granite or the unseen cells, the toggle rates that I showed in the previous slide, validation results, what we made was that we included that testing circuit in the training circuit, in the training list, and we estimated the average power for second set of 1000 cycles. And we could see that one, both Granite and the Grillip were able to perform on the same, with the same error. So this showed us that actually that whatever that previous slide I showed where the estimation of the toggle rates of the new cells, which was not a part of the training list, that was better in the case of the Grillip, which our neural network architecture that was able to perform better. So this is finally the inference throughput comparison, because I mentioned earlier that the traditional flow of using gate level simulation for that CGPT, what we call is the gate level, because from the ground truth that we get it. And that, if you could see that one, so both Grillip and the Granite, they were to perform better overall. So with 2.01 samples kilohertz, whereas with the Granite 1.96 and CGPT with the 0.13. So finally, I can conclude that Grillip, it performs better than the state-of-the-art Granite in predicting the output toggle rates of new nodes or unseen logic cells to demonstrate transferability and achieve better accuracy with a mean improvement of 14.36%. And also it performs the commercial RTL power estimation tool, as I showed in one of the earlier presentations, for average power estimation by achieving a mean improvement of 23.4%. And Grillip does better than the commercial gate level power estimation tool, CGPT, for inference throughput, which is an average 15.46 faster. So we also acknowledge support from the Ministry of Electronics and Technology, Government of India. These are all the references. Thank you.
Average power, I'm assuming that it's leakage power and dynamic power.
Yes, yes. Yes, the thing is that actually, we are, whenever we predict the average toggle rates, that is we convert that average toggle rates into a SCI file. So we convert that T0, T1 and toggle count, whatever that we have it in the SCI file, we convert using a Python code, because all the wires information, we'll get that one. Each wire, how much toggling activities it has it, so we get the Excel sheet, we'll convert to SCI file. When you feed that SCI file, there are average power, what you mentioned, that is absolutely right, that we have it switching power, leakage power, and the internal cell power that we have it. So all these things are included in the final estimation of the average power. But the major contribution what that average toggle rates that we are doing, it is related to the switching power only, because that SCI file, we are feeding it to the tool itself to estimate the average power.
See, this is a topic of interest to us, obviously. So you have taken this further to really look at the entire design. Looks like you have gone through cell by cell. I could see from your graphs. But our interest is, let's say, given a design, the early prediction of the average power estimate, actually. Because, for example,
yes,
we use PTPX, post power, the GLS, you have UPF, all these elements are there, we compute. It's quite late in the design, actually, as such. But can you extend this to very early and then get the entire design's average power?
That we are not doing the gate level simulation when we are inferring model. Training, we are doing that one. But once the model is ready, it will infer from the RTL simulation itself. We are not doing gate level simulation, but we are doing synthesis. That we are doing, but the post-synthesis simulation is not required. We are taking the RTL design, we are synthesizing that one, because the netlist only will convert to graph. And then we'll train using our model. But for that training, once the model is ready, it can infer any of the new netlist file you give us. So that will infer the average power of that netlist file by just doing the RTL simulation. You don't have to do the gate level simulation to get the most very accurate average power estimation.
You run the tool on the RTL directly and then you get the...
Yes, RTL simulation, we just do it and give the input toggling activities. We will predict the toggling activities of all the intermediate wires and give it the complete SCI file, and then we can estimate the average power of that one.
So what's your reference actually for various, from 65, 7 nanometer, 11 nanometer,
yes,
what's your reference?
We can do that one. Basically, that portability definitely can be done. The thing is that whenever we go for this, we have done it using 65 nanometers. So when we go for other nanometer like 40 nanometer, any of the nanometer, the only thing is that we have to add those cells to our code. Because what happens, because these logic cells that we are training, because different process corners we can have that one. So from the process corners, we'll pick up these cells. We'll pick up the cells and include in our code. Only thing is that logic functionality we have to add, because our code that I explained in the node features, it is based on the logic function only, that truth table. The truth table, we can get it from the library, so that we will feed the node features and the edge features, and we'll train that one. So in a new netlist file also, if it is going to have the new cell, we have to just add that one. That is fine. That's why in inductive architecture, we'll do that one.
But you have to add during the training process?
No. That training process is not required. New netlist file, if you give that one, we'll add these cells. Because when you say, for example, 65 nanometer might bring out some set of cells that we have added. If you go 40 nanometer from the different process corner that we have done it, there could be the variation in the name of that one. So that we have to add to our code. That's it.
No, but variation in name is one aspect, right? The variations, variations between RCs and other estimates.
Logic functionality, we'll add it to the code. So that we can make the entire base of that one.
But the leakage also dependent on all these other parameters.
Absolutely,
right?
leakage depends on that one.
And switching power.
Yes, absolutely. Leakage power depends on that one, but we are not estimating the leakage power here. We will convert the toggling activities to the SCI file. That SCI file will feed it to the tool. That tool will estimate the average power. We are predicting the average toggle rates, and then we are estimating the average power from the tool itself.
Based on netlist.
Absolutely, based on netlist.
You're extracting the toggles from RTL and using the netlist to get your...
Yes. So because we have, when we have to feed the netlist, and then we'll estimate there we are feeding the library information. Library information is fed when we are estimating the average power.
So why couldn't you do just at the RTL level, right? You could, you don't need to go to the netlist. You could bring those netlist related parameters into your training and then infer
that we are,
directly from RTL.
yeah, that is right, that we are planning, but thing is that somehow from RTL to graph, that we have to do it. Because cells information, at least we'll get the cells information, logic cells. Somehow RTL to graph, that has to be looked into it.
You showed one of the approaches used in the industry, right? Simulation-based. But there are other heuristic-based models also. Have you looked at those models?
No, they have not used they have used netlist only. All the existing approaches have used netlist only. Yeah, they have a primal, granite, they have used netlist. And primal requires training also.
But there are other heuristic models also. Have you cross-checked how these align?
No, they have not. They have used regression models. They have not. I don't think they have used the heuristic models like that way. They have used the regression models and the CNNs. But they require training for all the new, even the inference model also. We don't, any new netlist file, if you just give us, the new netlist file also has to be trained in the case of primal.
That I understand. We can take offline, but there are heuristic models available in the industry.
Yeah, that maybe I look. Actually, we are planning that. Actually, that's a good idea. The thing is that we have to, if you could do from the RTL, convert to graph, that is a good step actually. Thank you, sir. Thank you. Thank you.
Well, we have almost come to the end of the conference. End of the session has completed. Just a moment. We should actually thank the session chairs for doing a wonderful job. So, if you could actually come onto the dais, please. 1 hour. Looks like there is a lucky dip that's pending, so I was asked to take. Pavan Kumar G, Qualcomm. And then Anusha. Are they here? I mean, so Pavan Kumar, Anusha. I was asked to take 2 more. I'll try. Dushant Namani. Wow, good. And then V. Anil Kumar. Okay. This gift is actually sponsored by Western Digital. Okay. Thank you.